Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Vous allez sucer un enfant.
Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
you.
Tu es trop grand pour comprendre des choses aussi petites.
स्क्रीन देखो. Good morning. Good morning to honorable dignitaries, delegates, faculty members, staff, and students. I, Tapan Mankodi, on behalf of the Department of Mechanical Engineering, IIT Guwahati, welcomes you all to the 8th International and 47th National Conference on Fluid Mechanics and Fluid Power being held at IIT Guwahati from December 9 to 11th, 2020. It goes without saying that we are in extraordinary times. But what is even more crucial is our ability to adapt and flow through the hurdles and challenges of prevailing pandemic situation. We are here for organizing the FMFP conference in virtual mode for the first time. Let us begin this conference with a soulful invocation song.
Professor Mankari, let us wait
Yes.
for director to join.
Okay.
Director sir, let him join, then we'll start.
Okay.
Our HOD has already joined. You please check from the list.
Yes, Professor Senthilvelan has already joined. Good morning, sir.
Professor Arakeri also joined.
Good morning. Good morning.
Yeah, good morning.
Good morning, sir.
Good morning, Amresh Dalal.
Good morning, sir. Welcome.
Yeah.
So, Tapan, Professor Tapan Mankari, you please start from the beginning.
Yes. Good morning. Good morning to honorable dignitaries, delegates, faculty members, staff, and students. I, Tapan Mankodi, on behalf of the Department of Mechanical Engineering, IIT Guwahati welcomes you all to the 8th International and 47th National Conference on Fluid Mechanics and Fluid Power being held at IIT Guwahati on December 9 to 11, 2020. It goes without saying that we are in extraordinary times. But what is even more crucial is our ability to adapt and flow through the hurdles and challenges of the prevailing pandemic situation. We are here organizing the FMFP conference in virtual mode for the first time. Let us begin this conference with a soulful invocation song. Now I would request Professor Amresh Dalal, Organizing Secretary, to deliver the welcome address.
Thank you, Professor Mankuri. Respected Professor T.G. Sitaram, Director of IIT Guwahati, Professor Jayant Arakeri, President of National Society of Fluid Mechanics and Fluid Power, Professor S. Senthil-Belan, Head, Department of Mechanical Engineering, all dignitaries, researchers, scientists, academicians, students, and the entire fluid mechanics community. A very good morning to all of you. On behalf of the organizing team, it is our privilege to welcome you all into this inaugural session of the 8th International and 47th National Fluid Mechanics and Fluid Power Conference. As the premier conference in the domain of fluid mechanics, it is organized annually under the aegis of the National Society of Fluid Mechanics and Fluid Power, and this is the first time this conference is being held in Northeast India. Of course, we are slightly disappointed for not having the option of organizing it physically. However, we are delighted to have it on virtual mode. We are happy to have received tremendous interest from researchers in the form of paper submission. After a stringent peer review process, a total of 240 papers spanned over 12 tracks has been selected for presentation. The presentation will take place across 36 technical sessions over 3 days. We also have 2 plenary lectures and along with 12 keynote lectures. There are 4 parallel sessions for paper presentations, and pre-recorded presentation videos will be played in all the sessions. Additionally, all the sessions will be live streamed through YouTube and Facebook. We are happy to inform that the selected presentation of the conference will be published in reputed journals like Physics of Fluids, Journal of the Institute of Engineers, India, and Sadhana. There will be 4 awards to be announced during the valedictory session. 2 awards will be from the National Society of Fluid Mechanics and Fluid Power, one for Professor M.G. Deshpande Award for Best Paper from Academia, and one for Professor Y.B.N. Rao Award for Best Paper from Industry Institution Interaction. 2 more awards will be from the journal Sadhana. This is for most innovative research and for best presentation. We have put in lots of efforts over last few months, and we are eagerly looking forward for your active participation, and we hope that the conference would be a grand success. Thank you. Thank you all.
Thank you, sir. Thank you, sir. Now I would request Professor Jayant Arakari, the President of National Society of Fluid Mechanics and Fluid Power, to address the conference delegates.
Yeah, Professor Sitaram, Professor Santavalan, Professor Dalal, and all the participants, I extend a warm welcome to this conference on fluid mechanics and fluid power. First of all, I should appreciate the effort put in by Professor Amresh Dalal and his team and congratulate them on organizing this event in these exceptional circumstances. In fact, a couple of months ago, we were still discussing in what form we should hold the conference. And it is to their credit that they could come up with this format in a short time. And as all of us know that this fluid mechanics and fluid power conferences give a platform for researchers, in particular students from a variety of disciplines, civil engineering, mechanical engineering, aerospace, chemical, to interact in a wide-ranging topics that constitute fluid mechanics. So fluid mechanics is a very classical subject, but it is still a very exciting one. And in fact, if you look at the range of scales in length, for example, it goes from microns to kilometers. In speed, it goes from a few centimeters per year in geophysical systems to thousands of meters per second in aerospace, and densities and viscosities again ranging in orders of magnitude. And that is what makes, I think, fluid mechanics has made fluid mechanics and continues to make fluid mechanics an exciting subject to study. And that's what attracts the brightest students to this area of fluid mechanics. And of course, fluid mechanics plays a very important role in almost all parts of our life, natural and industrial lives. And in fact, for example, new and challenging problems, whether it is combating climate change or the coronavirus, whether it is designing hyperplanes, better heat management system for the smartphones or for the electric vehicles, or designing new ventilation protocols to reduce infection. So fluid mechanics plays a very, very important role. And in fact, I'm very happy to note that there is a talk on fluid mechanics of COVID transmission here in this conference. And I think all the young researchers which are participating in this conference will realize the importance of fluid mechanics, and I hope they rise to the challenge of the many problems I think that we will face as a country, and in fact in the world, to overcome these challenging times and problems. And as Professor Tapan mentioned, we are in exceptional times. And one thing which we will miss this time is, of course, the personal meetings, which are so important for scientific interactions. It's often the chance meeting next to a coffee table, which gives rise to new ideas. And of course, most of all, we'll be missing the picturesque IIT Guwahati, which was, we were all looking forward to be present there. But I guess there is some advantages also. This new platform of holding conferences virtually has advantages, especially of having larger participation. And this experience, I think we should make use in our future fluid mechanics and fluid power conferences. And perhaps we can conduct them in a hybrid mode. And we can come up with new ideas which will benefit everyone. And I'm looking forward to a very successful and fruitful conference. And again, I welcome all the participants and I hope they have a wonderful time. Thank you.
Thank you, sir. Thank you, Professor Jayant Arakeri, for your valuable remark. Now I would invite Professor S. Senthilvelan, Head, Department of Mechanical Engineering and Chairman of the conference, to say a few words.
Very good morning to all. On behalf of Department of Mechanical Engineering, I welcome you all to this wonderful conference, and it is a very privilege for us because this conference, as it was mentioned, like it's more than 50 years old. We are just 25 years old, like mechanical engineering, and IIT Guwahati is just 25 years on mechanical engineering. Just graduated about 180 PhD scholars and about 1,100 BTech and 1,100 master students. So in front of this society, we are very humble and we are small in the size. But I take this opportunity to congratulate this committee, this organizing committee, Professor Amaresh Dalal and his team. It is a wonderful opportunity to show our the attitude and our capabilities. Though we are all telling it is a challenge and difficult situation, but IIT Guwahati and mechanical engineering is looking this as a opportunity rather than the problem. So we are in fact looking this is a great opportunity to contribute to the society, either in the form of organizing the conference or disseminating the knowledge. And as everyone mentioned, the dignitaries have mentioned, this is a classical area where we have to contribute to the society by through this. And I also take this opportunity as we started with the invocation. We must have seen that we have a classical systems like musical systems or systems. And I also extend you to appeal you to look into this area which we have forgotten. Like there are wind instruments where this fluid mechanics plays a major role. Because music is not just controlling our emotion. We know that it changes our chemistry. So people can really think about contributing the area which is not even touched upon. So we normally bothered about a classical space or aircraft related applications, but I appeal to this community to contribute to the area which is not even touched so far. And not only to that, normally there is always a myth in the society, like IIT does research only for another 20 years back or 20 years far ahead. But let us also contribute to the common people, our own common countrymen, so that they can immediately utilize our contribution. So some of our effort we can really contribute. Definitely it is a need of this day to contribute to publish in a high reputed journal and all those aspects. But let us also contribute to our countrymen, so that it is a today problem, as we are all today we have so many problems around us. Let us also contribute to this to the common man, and which are some area which are not touched upon. It is not we are not touched upon because it has not reached to the the potential. That is a point I just wanted to make. Again, congratulate to this team as well as all the participants. And as I mentioned, we are not looking this as a problem. This is an opportunity. Let us not bother about what is missing. Let us see what we are going to gain from this. Like typically a conference organizing, it's a big problem in arranging the logistics, the food, the accommodation. Now you see that those aspects are not at all needed. Now they have to just bother about organizing an online thing. other aspects which where we can concentrate more on the core area rather than supporting, because organizing an Indian conference, we know how the Western other countries organize, but Indian conference we take care every participants so nicely, but that much of effort we are basically avoiding. Not only that, the participants have to come across at different places and different climate. Now we know that there is a fog, flight delay, so much of other aspects we are able to avoid now due to this situation. So let us look into the positive aspects and know the gain at this moment. And I wish all very best to the both the all the members as well as the committee. Thank you very much.
Thank you, Professor S. Senthilvelan, for your thought-provoking proposal. I now request Professor T.G. Sitaram, Director IIT Guwahati, who also happens to be the patron of the conference, to share his wisdom with us.
Namaste. Very good morning to all of you. Professor Jayant Arakeri, President of the National Society for Fluid Mechanics and Fluid Power. Professor Senthilvelan, Head of the Department, Mechanical Engineering, IIT Guwahati. Professor Amaresh Dalal, the organizing secretary of this conference, and others, colleagues of IIT Guwahati, and all the distinguished speakers, delegates, and participants, and ladies and gentlemen. It gives me great, immense pleasure to inaugurate this conference, which is the 8th in the series in the international level and 47th in the series at the national level. The topic of fluid mechanics and fluid power, it's a very fundamental topic for most of the engineering department, whether it is civil, mechanical, electrical, electronics, anything, for that matter. Fluid mechanics is the branch of science where studies the behavior of fluids when they are in state of motion or rest. So you can now imagine the kind of varied problems which engineers have to solve. Instance of generation of electricity in hydroelectric power, which is a huge. In India, particularly, we are heavily dependent on that. And today we are also talking about the fluid power. Fluid power, even though I just talked about hydroelectric power, but it means many other things. A huge area. Is not the primary just dimension of fluid mechanics itself, but in fact, in terms of mass, length, time, and temperature, the dimensions are varied. So it's a matter of immense pride that the Department of Mechanical Engineering, which is only 25 years old, is holding this 8th International Conference on Fluid Mechanics and Fluid Power. Why I said that is because this area, is so niche, and to get such conferences by younger institutions is very difficult. So only thing is we are now having in the virtual, as this pandemic has not allowed us to really come together. But as my earlier speaker was highlighting, I think it's also a blessing in disguise so that we can concentrate more on the technical matters. And also, you can bring in all kinds of experts, even the very senior most expert in this area, very easily for this kind of conference than a physical conference. So I saw very distinguished people speaking, even including my previous predecessor, Professor Gautam Biswas. I think he's delivering the first talk. Very happy to see that. So in the backdrop of our 25 years of celebration of Silver Jubilee, we just completed actually Silver Jubilee celebration in the month of September of this year. So on behalf of this entire IITG community, I extend a heartiest welcome to the eminent speakers, delegates, and also the young researchers participating in this conference. So this is being organized with an aim to bring together renowned researchers. I think is the key aspect of it, and that is also became much more viable and possible because of this pandemic. Otherwise, I think India would have taken another 5 to 10 years to come to this stage if this pandemic would not have been there. You see, we save a lot of money now Not only in this conference, I'm talking about the travel and many things, many board meetings happen online, many selection committees happen online. And also not only the money part, it's also the strain on the human body, that also is reduced. So I wish that this conference will have a greater deliberations. Only thing is, I wish even the organizers could use many other, breakout sessions. And there is a lot of things are possible today in this virtual realm. Okay, I don't know whether you could do that with Teams, but there are other tools where you can have a breakout session, you can have an exhibition, you can have meeting of the experts and the young people online. I think those things should be explored more and more now, because this is going to be the new order for us. Okay, this is going to be the new order. Online conferences are going to be the new order. So the plenary sessions are fantastic the way what we are doing it. But if you want to have parallel and then other sessions like exhibitions or the display or the poster sessions, and all that can be done using this online platform, so that we should explore that. And I keep on telling from the beginning in IIT Guwahati, when we sent out our students, all students on March 18th, I told our faculty saying that we can't run offline classes or offline examination simply online. So that we should actually innovate new way of doing these things online, because online attention spans will be very small. So you should divide. Even the lectures of the keynote lectures could be little differently done. But anyway, we are learning. Nevertheless, I'm very confident that with the constant support of all the distinguished people towards IIT Guwahati, we will be able to achieve the set agenda or set objectives with this conference, what is meant for. In future, I'm quite sure of holding this conference also in physical mode. It is not that we're going to only shift to the totally, but as my earlier speaker, Professor Harikeri said, we would like to come to IIT Guwahati, beautiful campus. Yes, definitely, we welcome all of you to the beautiful campus. And that too, this is the period to visit Guwahati. It's very beautiful, green and cooler, and campus is also very cleaner, and air is also very clean in this area, this part of the year. Anyway, coming back to this event, I hope this event will facilitate a stimulating forum for scientific discussions, professional networking, research collaborations, interdisciplinary education, and dissemination of the most recent scientific and technological advancement in fluid mechanics and fluid power. At the end, I would also like to take this opportunity to congratulate the entire team of fluid mechanics and fluid power organizing team at IIT Guwahati for organizing this conference at this scale, and also wish the event a grand success. With these few words, I thank again the organizers for inviting me to say a few words to all of you. Thank you. Namaskar. You are muted.
Tapan, you are muted.
Okay, I'm extremely sorry. This will keep happening during the conference for many of us. Sorry. Thank you, Professor T.G. Sitaram, for your kind words. I would now like to invite Joint Organizing Secretary, Professor Dipankar Basu, to share the vote of thanks.
Thanks a lot to Dr. Mankodi, and good morning to everyone. Successful organization of an event demands selfless support from a varied group of individuals, and we, the FMFP organizing committee, is blessed to receive the same from all possible corners. So we feel it is the perfect time to say thank you to each and every such personnel, but of course I am trying that with a bit of apprehension, as I am surely going to miss a few. So I'd like to apologize beforehand to them for missing out unintentionally. First and foremost, I would like to express our sincere gratitude to Professor T.G. Sitaram, Director IIT Guwahati, for kindly accepting our invitation to address this occasion despite his busy schedule. He has been the driving force behind this whole process, being the patron of the conference. We would also like to acknowledge the support received from the IITG administration and also from the computer center right from the beginning. We used to thank NSFMFP for giving us the opportunity of organizing this event and also for persuading us to adopt the online mode amid the pandemic scenario. We would like to express our gratitude to Professor Jayant Arakeri, President of NSFMFP in particular, for gracing the occasion. We extend our sincere thanks to Professors S. Senthilvalan, present head, and Professor S.K. Dibedi, the former head of the Department of Mechanical Engineering, for helping us in all possible ways, for extending all possible help on behalf of the department and also for their presence here. The support received from many of our colleagues, both from IIT Guwahati and elsewhere, are also worth mentioning here. We would like to express gratitude to all the track chairs and reviewers for helping us in identifying the papers submitted for presentation here and also for completing the task within a short time frame. And also to all the plenary and keynote speakers for accepting our invitation to share their views, share their research here in this platform. We thank our sponsors, TSI Instruments India Private Limited and Tescon Aerofluids INC for their financial support, and also to all the registered participants, of course. We must acknowledge the support received from the web administrators and the student volunteers for helping us in setting up and managing the online platform. We must mention our faculty and student volunteers for their relentless effort, particularly over the last 3-4 weeks. However, we need much more from them in these 3 days, and so I am holding on there. Thank you for the moment. The final thanks to all the participants, as this conference is meant for them, and also our success will be gauged only by their active and enthusiastic participation and involvement. So, with the request for your continuing support for a final time, I thank you all.
Thank you, Professor Basu. The plenary lecture by Professor Gautam Biswas will start soon. And with this, I conclude the opening ceremony. Thank you, everyone.
Thank you. Thank you, all dignitaries.
Thank you.
So, Professor Atul Sharma. Yes.
To hear me?
Yes, you are audible. Let us take Professor Biswas also once. Sir.
Sure.
Sir, can you please unmute, and if anything we need to check your presentation and other.
I am online. So
good morning, sir.
Good morning to everybody. Good morning to Amresh. Good morning to Atul. Good morning to everyone present. All the dignitaries, whoever is present now. So we will start now. If some testing can be done, but probably, do we have time or we have to immediately start?
You just please check whether you can share your presentation, then we'll start.
So I will. I've already opened, but I have to see. So, is it to be brought to full screen mode, or otherwise? See, okay, probably. Now, is it visible now?
Yes, sir. Yes.
Okay, so icons are slightly different. It is coming.
You can minimize it.
No, what is happening? That whenever I'm sharing, this icon is, my God. share.
Yes, sir, it is fine. Means it is coming at the corner. Yes.
Okay.
So it is over to Professor Sharma, Professor Atul Sharma. You please start.
I will be excused for 2 minutes because see, this is my office. Somebody is knocking at the door. I mean, let Atul take over. I'll just take 2 minutes to come back. Just I'll shut the door and come back.
Sure, sir. Please take it.
Okay.
Amresh, shall I start the introduction?
Yes, that you can.
Okay. Good morning, and I welcome all of you for the Professor Sudhirkar plenary lecture by Professor Gautam Biswas. Now I'll present a brief bio-sketch of Professor Biswas. Dr. Gautam Biswas is presently a professor of mechanical engineering at IIT Kanpur. Earlier, he has been the director of Indian Institute of Technology, Guwahati, and director of CSIR Central Mechanical Engineering Research Institute at Durgapur. He was the GD and BM Mehta and Tour Chair Professor and Dean of at IIT Kanpur. The research group of Professor at IIT Kanpur has made a significant addition to the classical theory based on Taylor-Helmholtz instability. Mr. Biswas is the author of more than 150 publications in international journals. He has completed guidance of 23 PhD theses. He was a Humboldt Fellow in Germany in 1987 to 88 and JSPS Invited Fellow in Japan 1994. He is the Fellow of American Society of Mechanical Engineers. He has served a full term as the Associate Editor of Journal of Heat Transfer Transaction of SME. He was a guest professor at the University of Erlangen, Nuremberg in 2002. Currently, he is the Associate Editor of the well-known CFD journal Computers and Fluids. Professor Gautam Biswas is the Fellow of all three major science academies of India. He is a Fellow of Indian National Academy of Engineering and Institution of Engineers India. He has been awarded the esteemed J.C. Bose Fellowship by the Department of Science and Technology, New Delhi in 2011. Professor Biswas was bestowed with Distinguished Alumnus Award by Bengal Engineering College, now IEST Sirpur, in the year 2013. He has been awarded the Distinguished Alumnus Award from IIT Kharagpur in 2016. Professor Biswas was conferred honorary doctorate by NIT Agartala in 2007. He has been conferred doctorate also by Aristotle University, Greece in 2018. It's indeed a matter of great pleasure and honor for me to chair the session of Professor Biswas, who had been my CFD teacher at IIT Kanpur. I'm always grateful to Professor Biswas for his continuous and kind support in my professional endeavor. Before I hand over to Professor Biswas, may I request all of you to write down any query or your questions in the chat box of the MS team that I'll take up at the end of the talk, since I do not want to disturb the complete involvement of mind, body, motion, energy of Professor Biswas during his talk. So with this, may I request Professor Biswas to get started with his talk.
Thank you very much. Am I audible?
Yes. Please.
Thank you very much, Professor Atul Sharma. Thanks to the organizers, Professor Dalal and all my former colleagues of IIT Guwahati. It's a real pleasure to be back to the fold of IIT Guwahati, and I deem it a very rare fortune to deliver the plenary talk of this coveted conference. And all the dignitaries who were present during inauguration, including respected director of the institute, president of FMFP society, head of the department, and our senior colleagues who were there, and all the attendees. For very warm greetings from IIT Kanpur. So today's talk is about dynamics of drop coalescence and entrapment of large bubble. Now, these are very common scenarios what we can see when a drop falls on a liquid surface. If it is splashing, then splashing crown is visible. It may be partial coalescence, it may be complete coalescence, and if it falls on a solid surface, depending on the hydrophobic or hydrophilic surface, we can see different forms of drops which at times look like emeralds. Now, specifically, it has many applications: spray cooling, inkjet printing, atmospheric and oceanographic sciences to investigate phenomena of rain and the outcome of rainfall on the ocean surface, creation of air cavities and mist formation. Now, when a drop falls on a liquid surface, today we are focusing only on the liquid surface. It is equally interesting when we consider falling drops on solid surface. And it may, after falling, depending on the size and the momentum, that means the velocity of the drop, it may float, it may bounce, it may coalesce, it may splash. There may be formation of vortex rings, and also there may be formation of jets and secondary drops. Now, these first two areas, floating and bouncing, these are really, very, very challenging, even connecting to quantum mechanics. So I will not touch these two, although research is underway in these two areas. But I will primarily focus where we think we have done something at least, remaining four areas like coalescence, partial and complete, splashing, vortex ring, and jet formation. Now, I'm coming down to the formulation of the problem. We can consider a liquid drop. Liquid is having density rho L and viscosity mu L, and it is falling on the liquid pool of same liquid, but while falling, it is crossing a matrix liquid or matrix fluid, surrounding fluid. The surrounding fluid may be gas, surrounding fluid may be another liquid, which with the condition that these two liquids are immiscible. But in general, it is gas, and we will be considering here primarily, air-water system. That means water drop falling in water pool, and it is crossing the ambience, which is air. And with such studies, the parameters which are of prime importance are Onesogge number, which is viscosity of liquid 1 or viscosity of fluid 1 divided by mean density, coefficient of surface tension, and the drop diameter. Onesogge 2, the viscosity of the matrix fluid, and divided by the similar parameters. Bond number, which is rho C. Rho C means rho 1 minus rho 2. In this case, rho L minus rho gas, rho liquid minus rho gas, or rho air, d square G by coefficient of surface tension sigma, and attitude number, which is basically rho 1 minus rho 2 divided by rho 1 plus rho 2. Now, before entering into the physics part, I would like to address this paradigm, which is called volume of fluid, because all these flows are basically, interfacial flows between two fluids. So the boundary is not well defined. Boundary evolves, and boundary evolves through application of proper physical conditions. Now, if we think about one such domain where this blue part is maybe a color function or liquid, whatever we call, and the white part is basically air or gas or another liquid. Now, in this case, let us call it air. And so, here we will define the liquid void fraction in such a way that in gaseous region it will be 0, in liquid region it will be 1, and all interfaces it will be having a fractional value. So we will mention little bit about volume of fluid method, what we have followed here, together with level set method. This was a great mathematical discovery of Professor Stanley Osher, who got Gauss Prize because of discovery of level set function. I will basically any geometry can be represented. Even now, instead of drawing a circle or giving an equation x square plus y square equal to r square, we can describe it through a mathematical function 0 and 1 and draw the circle. So now this VOF and level set both are basically dependent on a basic method which is called Click algorithm, piecewise linear interface construction method of Young's. So if we had, for example, a trapped liquid, which is or a colored fluid, with blue color, and we have to describe that through the mathematical functions. We can describe them by piecewise linear segments, and each interface cell will give correct representation of the occupancy of the cell by the liquid and air. This was done, this can be done rather through properly describing the surface normal to the interface and the offset distance of the interface from the center of the cell. And in order to do that, we have to calculate direction cosines. From there, we can calculate surface normal and finally offset distance. And direction cosines are evaluated from a cluster of cells with the cell of interest keeping at the center all its north, south, east, west, northeast, southeast, northwest, southwest neighbors, and the volume fractions of those cells. Now, after having done that, we have to apply another algorithm which is called Elvira. This is basically least square volume of interface reconstruction algorithm, and basically in 2D or axisymmetric, it is a 3 by 3 block, and in 3D it is 3 by 3 by 3, 27 cell block, where we optimize a function, and that function is optimized in such a way that the approximated value tends towards the real value. This is the basically approximation, and this is the finally real value, and this has to be minimized. Physically, if we say, it is something like this. See, for example, this is pure vapor cell or air cell. This is pure liquid cell, and these are interface cells. And at the interface cells, we optimize this function so that error is minimum. And for example, here, actual volume fraction is 0.93. But if we go by this tangent, then it will be 0.98. We have to bring the value of 0.93 through this optimizer. So, I don't know. Okay. Now, having done that, we get to know the cells, those are occupied by liquid, and cells, those are occupied by vapor, or occupied, in this case, occupied by air. And then we assign level set function, which is a very small value, and we assign minus d. D is a small quantity in the gaseous region, 0 at the interface, and plus small positive small quantity, small value in the liquid region. And then we try to have a smoothened interface based on which we recalculate the surface normal given by grad phi, by mod of grad phi, and then the actual curvature of the interface in each cell. So, and then the real interface is described. But if you recall, we have to correctly calculate void fraction in each cell. For that, basically what we do, void fraction based density and void fraction based viscosity we define. Here you can see, based on the void fraction, if void fraction is 1, it will be liquid density. If void fraction is 1, it will be liquid viscosity. If void fraction is 0, it will be air density, and it will be air viscosity. and in between it will be having the fractional value. So we redefine our momentum equations in x, y, and z direction, or whatever is the coordinate system in all orthogonal directions, and this is modified inertia term, and you can see we are using basically void fraction based density and void fraction based viscosity, but the momentum equations are augmented by another term, which is basically sigma, surface tension coefficient, the basically grad alpha, and our curvature, radius of curvature. So basically this term is, we can say that's surface force, but the surface force arising out of the interfacial surface tension, and then this force can have two components, normal components and tangential component. Tangential component is present when surface tension is having gradient. Surface tension can have gradient when it is flow, non-isothermal flow, but in this case, since it is isothermal flow, the surface tension doesn't have temperature gradient, so Marangoni term is dropped, and only we have the normal component. And the normal component, as we know, the surface tension coefficient is basically a force per unit length. So in order to convolute it to fit in the momentum equation, we have to multiply it with delta Dirac function, which has a non-zero value only at the interface. Now this formulation is primarily based on Bragg-Bill's formulation, and as I said, after calculating the void fraction, new void fraction in each cell, we assign basically the level set function and calculate the sharp interface. And while doing that, at the interface cells, we define Heaviside function. So again, so to say, the level set function is redefined at the interface cells through the Heaviside function, where it is having a value of 0. Instead of very small negative quantity, we assign now 0. And instead of a small positive quantity, we assign a value 1. And this transition between 1 and 0 is brought about by this level set function. And then we redefine the densities and viscosity based on the Heaviside functions and recalculate the advection of the interfacial front. So we use basically staggered grid arrangement, uniform grid spacing, finite difference discretization, and the discretization scheme is INO scheme, essentially non-oscillatory scheme of Professor Stanley Osher, and we use for the pressure solver biconjugate gradient method. Very recently, we have changed it to HiPre, basically a multi-grid based pressure solver. Numerical scheme is based on explicit time advancement, and we use operator split advection scheme for advecting the interfacial front. And as you can see, solution scheme is second order, strictly second order in space because of INO scheme. And then we do some test problems. As you can see, this is a circle. This circle is given anti-clockwise rotation 1,000 times, and then it gets into this shape. And then again we give clockwise rotation so that we get back the circle. Indeed, this test is successful. We got back the surface, but as you can sense, very small amount of mass loss can be seen here. Then we went for another test case where interface of two immiscible liquids is undulated, and then undulation at a point is monitored. It has analytical solution given by Prosperity, and we validated our CLSBF algorithm driven solution with that. You can see very accurate accurate presentation of that. Now, third case is basically something is close to Rayleigh-Taylor instability. Basically, a heavier liquid is kept through a separating plate on the top of a lighter liquid, and then all of a sudden that plate is removed and the heavier liquid starts penetrating into lighter liquid, and at different instance different penetration fronts are obtained. This also has analytical solution of Bellman and very accurate numerical solution, which is called today benchmark by Murray Rudman. Now, this Rudman solution and Bellman solution both are validated through our algorithm. Now we will go for the real problem that we are concerned about today. Just look at falling drop on a liquid surface. After falling, see this column formation and then subsequent detachment, formation of secondary drop. Secondary drop oscillates with the oblate and prolate shape. Again, it comes back and touches the liquid front. Again, through the aperture, some liquid is drained out. Again, pinch off takes place and the tertiary drop forms. Finally, the tertiary drop you will also see will touch the liquid front, and some amount of liquid will be drained out. But now further formation of the column and pinching off will not take place. So this is a two-stage cascade. As such, several experiments have been done. In one experiment, Professor John Bush of MIT, he could show some such 8-stage cascade. So here, depending on the drop size and its initial velocity, we could see two-stage cascade. That means formation of secondary drop and tertiary drop. And this is called partial coalescence. So this is basically the exact results. That was the animation, and here we have shown the exact result for specific Unisorge number, bond number, attitude number, and as you can see that non-diamond first detachment, that is secondary drop formation, took place at t equal to 0.75 Tc. Tertiary drop formation took place t equal to twice Tc. This is non-dimensional time. And this case is basically, we also confirmed the experimental results of a very active group. I am just, the name I have to recall. This was basically Professor Kovepur of UCLA, Hani and Kovepur's experiment with 1.2 millimeter water drop falling through air through the liquid pool, and he got secondary drop diameter as 0.64 millimeter and tertiary drop diameter as 0.32 millimeter. And in our case, if we say non-dimensional initial drop diameter is 1, d2 by d1, that means secondary drop by primary drop diameter, we got 0.54, and tertiary drop diameter by secondary drop diameter, we got 0.47. We exactly reproduce the same result. Now we'll come to another very interesting case. You can see this is basically water drop falling through benzene media. And this, you can see that this pool liquid is coming down, getting depressed, and then finally it is touching the front, and you will see again the column formation, and you will see the pinch off. But after pinch off, this liquid column undergoes instability. This is Rayleigh-Placet instability. Forms two drops, and again they come back and rejoin as one drop. This was also basically motivated by the experimental result of Charles and Mason, and we could exactly reproduce Charles and Mason's results with 6 millimeter dia water drop falling through benzene media. This result I will not, show in detail, but let me tell you briefly. This is a drop of 18% polyethylene oxide solution falling through decant medium, and as we can see from the picture that it is completely drained out. There is no formation of secondary drop. The drop liquid is completely drained out, and this is a typical example of a complete coalescence. So basically, this was our very interesting finding that this partial coalescence regime can be defined through viscous regime, inertia capillary regime, and gravity regime by defining the two extremes of drop diameter. Beyond the, drops larger than this diameter, which is 1 centimeter, you will see that there will be no partial coalescence. It will be always complete coalescence. And drop less than this diameter, you will see that there will be basically column formation, but pinch off will not take place. So secondary drop will not be formed. Because today's main topic is slightly different, so I'm not elaborating much on that. But I can tell you about our specific contribution for this partial coalescence physics. This is Nature paper, Blanchetti and Bigioni, where they made responsible for this capillary pool for a partial coalescence. So here we reproduced their interpretation. As you can see, after drop falling, the capillary waves are being generated, and obviously there will be capillary pool from the top of the liquid column. But together with that, there will be creation of horizontal momentum and vertical momentum within the drop liquid, and you can see the color code. Red is positive value, blue is negative value. So as you can see that negative horizontal momentum is also a responsible factor, rather very, very important responsible factor for pinch off. So from our study, the important criteria for partial coalescence is the increasing horizontal momentum of the drop relative to the vertical momentum. This can be accomplished either by changing the viscosity or by changing the gravity within limits. So another very important findings of this study, I can just briefly tell you that if you look at when the secondary drop is forming, right from formation of liquid column to pinch off, you will get different interface profiles at different times. And this is one case, this is another case. All these interface profiles can be collapsed on a single profile, confirming self-similarity of the solution. Only thing, you have to have correct transformation. So Z is the axial direction. It is non-dimensionalized by D, Z star. R is the radial direction, non-dimensionalized by D, R star. And then time is non-dimensionalized by viscous time. Viscous time means, rho m d square by mu m. This gives the, if you can calculate back of the envelope, this gives the viscous time. So if the time is not dimensionalized by viscous time, and we sort of transform it into Z star by T star into alpha and R star beta, then you will get the self-similarity solution. And as I said, that all the interfacial convolution or development of the interfacial profiles will collapse onto a single curve, confirming the self-similarity, which is basically, very important finding. Now, I'll quickly go to the transition from partial coalescence to complete coalescence, and it is accompanied by, this is one case of complete coalescence, and this is experimental result, if you look at the complete coalescence, also you'll be able to see that air bubble is trapped in the liquid pool. Now, this was basically very faithfully reproduced that result by us. You can see formation of air bubble and basically formation of liquid column. So this now we come to our specific contribution of this identification of large bubble entrapment zone. Now, traditionally, this is very, you can perhaps understand that it's very important area. One of the thought leaders like Professor Prosperity or Professor Gary Lill, several other, such eminent people, they have worked in that area. And this is basically two groups, August and Prosperity and Pumphrey and Elmore, they confirmed these results. Basically, the air bubble entrapment scenario. So this is a zone of regular entrapment, and this is a zone of large bubble entrapment. By large bubble, basically bubbles which are having size more than 5 millimeter or so, and regular bubble entrapment or small bubble, the bubbles which are having size 1 millimeter or below. Now, because of probably a paucity of time, I cannot, discuss certain things in greater detail, but maybe during question and answering session, I can reply if you have queries to that. Now, this can be plotted on Weber number Froude number plane, and you can see that these are the basically smaller bubbles, and these are the zones of large bubble. Now, Professor Angbang Wang did very thorough experiments with this scenario, and he redefined the entire velocity and diameter, which is called VD map, and he redefined this zone, which earlier was defined as, this zone, regular entrapment zone, as S regime, smaller bubble regime. And this is, if you transform this into this map, this zone, this is a large bubble regime. But while doing experiments, he got many such points where he, found formation of large bubble entrapment. And that triggered the interest. So I will just show you what we are calling as large bubble entrapment, and this is Professor Wang's experiment. You can see air has been entrapped and it is basically oscillating, and finally you can see the mechanism of trapped air bubble and formation of vortex stream. Now we reproduced that. As you can see, that we will be able to get this again, exactly formation of air bubble with little liquid trapped inside, and then finally it is the trapped air in the liquid pool. Of course, trapped air finally will go out. So these are the important results in parametric form. This is basically the liquid drop of 5.65 millimeter diameter with a velocity 953 meter per second falling on the liquid pool, and you can see Professor Wang's results and our numerical results. Now, what is not available in Professor Wang's result, that if you see our numerical results, that we have shown the formation of jet formation, thin jet formation, and then basically entrapment of also within the entrapped bubble, we could show a small liquid has been entrapped. Now, this liquid entrapment is not seen here, but these results were further confirmed by the published result of Professor Thoravel and Professor Thorudson. Professor Thorudson is very well known experimentalist or very well known researcher in this area. Now, yet another case where we are showing basically a drop of diameter 4.42 millimeter with velocity 1.136 meter per second falling, and again, as I said, you can see formation of jet and basically entrapment of the air bubble, and also within the air bubble you can see some liquid has been entrapped. This was also found by Professor Wang, and finally you will see this is the large bubble accompanied by a very small bubble. And this is not any artifact, experimentally it was found, and also numerically we have found, and this is basically bubble pair, you can say. And as I said, that we used 6 million grid points and this very effectively. And another thing I have just I have not mentioned, this is basically formation of Worthington jet. See, when a vertical jet goes in the outward direction, another component of jet goes in the inward direction, and this liquid jet penetrates the air bubble, and this is the root cause for small liquid getting trapped inside, and this is basically formation of Worthington jet. So have you Atul, probably okay, do you have to say anything?
Yeah, we have 5 more minutes. Thank you.
Okay, I'll try, but give me a little more.
Sure.
Now, what I was, important thing I was trying to say, that while reproducing basically Professor Wang's some of the experimental findings, we calculated about 200 plus simulations with 6 million grid points, and we found that the real zone of large bubble entrapment is this. You just try to identify the earlier belief was that large bubble entrapment takes place only in this zone. And we could see large bubble entrapment over this zone. The red circles are, although 200 simulations were done, we cannot, represent all 200 simulations. These red circles are our simulations, and these blue squares are Professor Wang's experiment. So the Professor Wang's experiment and our simulations confirm the enhanced zone of large bubble entrapment, both on PD map and Weber number Froude number map. And with a little, humble way, I can say that this was also acknowledged by the journal Physics of Fluids in this particular year. At the end of the year, they announced, a few best papers. This work was included in the list of best papers. Now, I will just, since Atul is saying time is very less, I will just give you one reason for large bubble entrapment, mechanistic viewpoint. As you can see that after the drop hitting the water pool, this capillary waves are generated and the vortices are formed. And these vortices, basically, you can see they curl up. And it depends that how this rolled vortex finally behave. The coalescence of a drop of 4.2 millimeter diameter into a liquid pool at impact velocity of 1.236 meter per second, showing the evolution of roll jet. And this roll jet, also you can see, finally this roll jet has to evolve as a liquid tongue. But before that, I will just mention about two special cases. If these two special cases happen, then even if the bubble drop is large, having adequate momentum, the bubble entrapment doesn't take place. So this is one such case where you can see one sheet is forming. This is called ejector sheet. And when ejector sheet forms, you will see the cavity gets enlarged, but doesn't close in a way that it traps air. Similarly, lamella is formed, which is basically capillary induced thick liquid sheet, and then also the cavity closes at near the interface, and we do not get the phenomena of large bubble entrapment. So today time is not sufficient to explain all these in minute detail, but I will at least give you another few reasons. Say if we experiment with a drop with oblate size or shape, perfect spherical shape and prolate shape, here you will see with the oblate shaped drop, the cavity opens up and doesn't close. Similarly, and this is given by aspect ratio, the major axis by minor axis. So when this is basically 1, Then also you can see the water cavity and its shape. But if it is a prolex shaped drop, then you can see these rolled up vortices finally create liquid tongue. And these liquid tongues from the periphery meet at the center, and then the air is trapped. And this we have experimented the numerical experiment with 5 millimeter drop, same velocity, same Webb number, same Froude number, but different shapes, and revealing the formation of the phenomena of entrapment. So as I said, that if you go to the mechanistic viewpoint, that tongues from the periphery, they meet. After meeting, thin jets are formed. Now these thin jets, one is upward, another is inward. This inward thin jet is called Worthington jet. And Worthington jet basically penetrates the trapped air or trapped gas, and some amount of liquid stays within the trapped gas, within the large bubble. Now, I will have to finish it. So, we did this in conjunction with some experiments, and these experiments, as I have mentioned, that these experiments have been done by Professor Dr. Peshun Shai with under guidance of Professor Anbang Wang. So these are our numerical result for the enclosure depth. Now enclosure depth is the depth from the initial liquid pool interface to the point where the emanating liquid tongue from the periphery first merges on the axis of symmetry. And this, you can see variation of this enclosure depth with the impact velocity. And we did for numerical experiments. Numerically, we can use different drops. We can create different drops. But experimentally creating different drops and monitoring is a difficult job. So we did it only with one drop size, 5.65 millimeter. And similarly, another important point, that pinch of time. By pinch of time, what we mean this time. After these two tongues, not two tongues, this from periphery, one tongue, merge and the pinch off takes place, giving rise to outward jet and Worthington jet. Now, this plot is basically the pinch of time. This is physical time for different drops versus velocity. And you can see with the increasing velocity, pinch of time decreases. And if we not dimensionalize the pinch of time, basically you can see actual pinch of time into velocity by the drop diameter is a non-dimensional time. Then all the curves, come very close, and specifically you can see validation of our numerical result with the experimental result. Here also you can see very close confirmation. Here also you can see very close confirmation. So when liquid drop, I'm coming to conclusions. When liquid drop impacts on a liquid-liquid or liquid-gas interface, for very small drops and for very large drops, the phenomena of partial coalescence do not occur. In between, it is the partial. I have showed you the minimum drop size and the maximum drop size. Within the range of partial coalescence, the process can be divided into three regimes depending on different forces, namely viscous force, surface tension force, and inertia force. Partial coalescence occurs in liquid and air medium for very, very low velocity, and as the velocity increases, complete coalescence takes place. Now, transition to partial coalescence and complete coalescence, we can see, a galaxy of phenomena like small thick jet formation, thin jet formation, large bubble with thin jet, small bubble with thick jet, etc. And these are within this a very important phenomenon is large bubble entrapment, which is observed in a wide range on the VD map. The regime of large bubble entrapment on the VD map and on the Weber number food number map has been identified. So we have also seen that shape of the drop must be prolate at the time of impact for large bubble entrapment. Now, we have seen the vortex ring formation and its interaction with the interface to form a roll jet. And the vorticity strength must be strong enough to make the roll jet merge at the center line. That means the tongue, which we are referring as tongue from the periphery, should come and merge at the center line. The emergence of ejector sheet merged with the lamella prevents the separation and penetration of the vortex ring onto the pool, which in turn prevents the entrapment of large bubble formation. Within the large bubble entrapment regime, the enclosure depth, crater depth, and pinch of time decrease with the increase in impact velocity of the drops. The same parameters increase with the increase in size of the drops. So, at the end of the talk, I would like to acknowledge the researchers who directly and indirectly helped me, or rather together, developing this field. The research is ongoing, but this part of the talk, as I said, I am indebted to Dr. Hiranyo Deka, who completed his PhD from IIT Guwahati under the joint guidance of me and Professor Amores Dalal, then Dr. Bonni Ray, Professor Amores Dalal, Professor Sam Welch, Professor Stefan Zaleski, and Professor Anbang Wang. I'm really, I have enjoyed working with all these people, and this group is greater actually. We are still working on this, I should say, very challenging and kaleidoscopic physics. Still many things are to come up. Thank you very much. Thank you, Professor Sharma, for your patience. And thanks to all the listeners for their patience hearing. For their patience and hearing.
Thanks, Professor Biswas, for the wonderful lecture.
Professor Sharma,
your research.
Please go ahead.
Yeah, thanks, Professor Biswas, for the wonderful lecture. We highly appreciate the contribution of your research group, especially on the large bubble entrapment. With this, I open the session for any question and answer session. I regret that the chat box was inactive. However, feel free to raise your hand and then I can call you one by.
Professor Sharma, there is one announcement. May I announce it?
Please.
Professor Lin Chen, I request you to join in Hall 4. Professor Lin Chen, I request you to join in Hall 4. Thank you.
Okay, so with this, I request the audience to please raise your hand for any questions, and then I can call you and you can unmute and ask your question. Okay, let me take the opportunity to ask the question is, Mr. Biswas, I'm wondering, it's a very wonderful, and I appreciate numerically, it's a very challenging and hard problem to capture the bubble entrapment because the velocities are extremely large. And although we say it's a large bubble, but still it's quite small enough. I am wondering whether instead of air, if you take another liquid, whether it's reported in the literature that that continuous liquid gets entrapment analogous to the large bubble that you had shown?
This is extremely interesting and important question. I mean, so far, nobody has very specifically reported this entrapment of surrounding liquid in the host liquid. So in the liquid-liquid system. As such, this study can be extended to liquid-liquid system, but you can understand that liquid-liquid system, if we transfer it, so basically the pool liquid has to be heavier than the matrix liquid, and then probably it is possible, because all we are playing with basically, Monesorg number, bond number, and attitude number. Now, these are basically, density related, parameters, where density of both the fluids are interrelated. Now, if we can maintain the same attitude number, same bond number, same Monesorg number, probably it is repeatable in a different way. Means the values will be different. The entrapment diameter, entrapment velocity, size, all these things will be slightly different. But I have really not found anything so far in literature. The people who are working on this, to start with Professor Gary Leal or Professor Prosperity or Professor Ang Bang Wang or Professor Thoroddsen, Professor Thoravel. Professor Thoroddsen has done enormous number of investigations, but mostly I have found studies with the air water system.
Okay, thanks. So that gives us some message that probably that is one area where there is a future scope. And
yes,
it's interesting.
Yes. Very, very interesting and very important question. Very, very nice and very important question. With two immiscible liquids, if it can be repeated.
Yeah, thanks. Can I take this further? Is based on your understanding, how do you envisage whether if you have a lighter fluid, although heavier from the pool fluid, although lighter from the pool fluid, but it is heavier as compared to air. How do you envisage whether the bubble entrapment, the liquid droplet entrapment will be smaller or larger, or it's little more involved probably?
That is again difficult to predict in such a way. One has to really do calculations.
I understand that. Thanks. Any questions from the audience? Yeah, Dr. Shyam Shukla has a question. Please raise your hand and ask a question.
Sir, thank you very much for your great insight about the large bubble dynamics. If you can tell something about effect of gravity, which you have mentioned in your lecture, gravity change on this bubble dynamics, and how we can relate it to the real life situation, if some practical aspect we want to see in this.
See, first of all, let me tell you, this practical aspect is happening every day, right? These controls basically entire sort of weather prediction related to oceanographic paradigm, right? We have this rainfall on ocean and amount of air entrapped and that air release. This controls the surface, above the sea, and above the sea surface, and our all navigation of ships and all which are sort of naval vehicles over the sea, are affected by that. But I mean, it's very straightforward application, I can tell you. But there are certain other applications in chemical engineering area where basically the surrounding gas and the liquid, they interact, and gas absorption in that liquid finally results into another product. So those are all applications. I have not gone to the application side in detail. This is understanding the fundamentals, and gravity has definitely very, very important role, because drop is falling on the liquid surface because of gravity, and its penetration, its finally creation of gravity, and the mechanism of gravity collapse. That means how the cavity closes and the secondary drop forms. All these are basically because of gravity. As I said, it is even very important if you go for smaller and smaller and very, very small drop, where the drops, do not coalesce, float or walk or bounce. That is yet another very challenging paradigm to understand, that part. But everywhere, gravity plays the main role.
Thank you, sir. Thank you.
Yeah, we have a last question from Mr. Rao, Mr. Koteshwar Rao. You can raise your hand.
So thanks for a very good presentation. So just I want to know what is the minimum computational cell size to capture this phenomena, and which CFD software used for this work?
My dear friend, first of all, let me tell you that we do not use any CFD software for this work, right? This is our own program, right? Most of the CFD researchers, the chair of this session, like Professor Atul Sharma, or many of us, we, mostly work using our own code. Okay, these are the codes, which are, of course, we are extremely indebted to all our students. There was a basic code, and it is, for example, if you look at this study, this code was basically developed by Dr. Bonni Ray when she did her PhD at IIT Kanpur. Then she was also given my basic code. Anyway, I'm not going to that total history. But then this code was transferred to Dr. Hiranyodeka, who did PhD in IIT Guwahati. And he modified it. It's not, it will be unfair to say that, he, minimize his contribution, because he had to modify in such a way after understanding the physics that almost it is his own code. So this is where the code is evolving. It is not any software used from outside.
Yeah, cell size here was.
Cell size, as I have said, that this non-dimensional domain, I can tell you that. Are you able to see me, or
yes,
I am visible?
Yeah, if you switch off your screen, then we'll be able to see you better. Although we are seeing a small screen.
Okay, so that's what I do not know that how to really go about it. Okay, I will just go to the domain better since this you can be better answered with the domain.
Yeah.
Yeah. So see, this is the domain, right? So this H is the height, R is the radius, and of course this H varied for large bubble entrapment. We had to this H1 depth had to be increased, but as I have said that we have, and if D is the diameter, then this is maybe 4D, and this H1 may be 2D, 3D, or not 2D, 3D. We have gone up to 7D, and this R is basically 5D, and this domain we have taken 3 million grid points.
Okay. Yeah. Maybe probably we can take one more question from Mr. Vivek Mishra. Mr. Vivek, can you unraise your hand and ask the question?
Probably mic is muted.
You can unmute yourself. Yeah, your mic is muted.
So thank you for the presentation, sir. Sir, I want to ask that in the same computational domain that you have explained, the drop is falling and the pool is of height h1. Which, if h1 is very shallow.
No, yeah, but H1 I have drawn it here very shallow. It need not be shallow. It can be very, as such for all large bubble entrapment cases, H1 was, greater than H2. Anyway, tell me.
Sir, I just wanted to ask that if H1 is shallow, sir, is there any result available, like how that terms are interacting and how that...
Yes. That is a very, very interesting paradigm. If H1 is shallow and, this usually if H1 is shallow, very shallow, then the question of entrapment doesn't arise. Most of the cases will be similar to splashing, and this splashing will have a different variation of its crown. It will be primarily splashing.
Okay, sir. Thank you, sir.
Okay, thanks. There is no further question. So I would like to thank Professor Biswas for the wonderful lecture. And I'd also like to take this opportunity to thank the organizers, especially Professor Amrish Dalal, for giving me this opportunity. Thanks a lot to all of you for your attention and attendance. And I now hand over this to Professor Amrish Dalal to take the proceeding. Thanks.
Thank you so much.
I'm hand over to the organizers to take it forward.
Oh, Professor Sharma.
Yeah.
So any other questions are there?
Focus only on the pressure measurements, steady and unsteady, and time resolved Schlieren. And it's on the Schlieren that we want to obtain a phase average momentum picture. which one may think would be qualitative, but which is the first step in identifying that we have in fact obtained a true phase average picture in order to apply that to PIV data. So why is the phase averaging so challenging in this kind of flow? So consider this imaging at 7.5 approximately kilohertz of the flow, and this, as you can see, this is the schematic of the oscillator, which is opaque till the exit, and this is what you see on coming out. These two pins mark the exit, and when you look at this and you look at the histogram, you can see that the 1 sigma is quite broad. So it's not, as one would have thought, a precise frequency of operation. And it is this very jitter which makes it inherently difficult to obtain a phase average picture of the flow. Now, phase determination has been around for a while, and there have been many methods ranging from the hardware method, which is just a phase lock method depending on hardware, to mathematical approaches, to signal processing approaches. The hardware, of course, depends upon a signal from inside the oscillator, and so does the signal processing approach, which looks at zero detection. In the next few slides, we will look at what happens when you compare the phase lock approach against the mathematical approach and the signal processing approach. In the mathematical approach, the approach is that of proper or orthogonal decomposition, wherein we have looked at different types of PODs, whether on the global flow field or on the reference pressure signal inside the oscillator itself. Now, the reference pressure signal comes from the feedback channels from the top and bottom, which you see here on the left, and the difference in them is taken as the reference pressure. Obviously, this is not going to be a clean signal, as is evidenced by inspection of the raw blue trace, and we band pass it with the f0 plus minus 8 hertz filter in order to obtain a sinusoidal variation as seen in the spectral plot on the right. So, of course, we need to do image pre-processing. I will not bore you with the details. These are fairly well documented in image processing textbooks, and we can do any of these. These are only performed on the final average images, and not on prior to doing the averaging, so as not to skew the outcome. So let us first look at those which deal with the mathematical approach, that is the global flow field. The first of the mathematical approach for proper orthogonal decomposition starts with the intensity field and subtracts the time average field from it to obtain the intensity field fluctuations. We essentially need a snapshot POD. So we need to obtain the spatial modes and the temporal coefficients. And we have employed this on approximately 10,000 images. In this particular ensemble, there are only 8,25,000, because sometimes it also depends upon the processing time you require. So essentially, you compute the scaled coefficients. So from the lambda 1 and lambda 2 are their corresponding eigenvalues. So why do we choose these two? We will come to that in a moment. So the phase angle is computed as the inverse tan of the ratio of the scaled coefficients. Now, the window size was chosen as 3 degrees so that we have 120 windows in one cycle, and the phase averaging ends up allocating images to respective bins. So we can very quickly see by an inspection of these that the first two modes which you see, which have a phase shift of 90 degrees in their temporal coefficients, basically are orthogonal to each other, account for the bulk sweeping motion of the jet, and they account for most of the energies in the seen in the flow. So if you were to take those as seen in the SPOD plot on the right, you would account for pretty much all the energy acquired in the process. So once you do these, you distribute the images corresponding to the modes in their appropriate phase bins. So this results in a highly uneven distribution of images, as we shall see shortly. The second method is you do whatever you did in the method 1 and then you sort them here, and you allocate a fixed number to each bin, because as we already concluded, there's a problem with having varying bin image size. So we want to have equal numbers, so we sort them and allocate them. The problem with that, of course, is the starting and ending degrees in each bin vary vastly. We will come to what is the implication of this second. There, of course, after you define this, there is a third approach. Suppose you did a POD on the pressure signal itself from the inside the oscillator. We took those two pressures, as you saw in the feedback channel top and bottom, divided it into two parts, assume two observers, and assume the two observers are simultaneously recording this data, and do a POD of the observer's data. So the first thing you find that the eigenvalues are very different of the two observers. We'll come to why that happens in a moment. We proceed by finding the phase angle of these and again attribute them to their respective bits. The final method is the signal processing method, and the signal processing method is essentially a zero crossing detector, where again using the data from the feedback channels, and this is a typical cycle seen by the sinusoidal almost variation of the filtered data, and each of the circles depict a time location of the image. A delta t can be defined between any two images over half cycle, and the phase angle theta is given by 360 times delta t by the total time period of time. So these are going to be compared against the hardware approach. The hardware approach is very familiar to most in the audience, so I will not dwell too much on it. Essentially, it takes some kind of signal. We have taken the same signal for consistency, run it through a signal filter and amplifier, find the rising edge by using a zero crossing detector, have a delay generator to set the phase, because essentially it's if you take a sinusoid, you can depict it as a ramp and you divide that into equal parts in time, and the cycle start is measured in real time. The phase is set by varying delta t times t naught, so which gives you the timestamp of the zero crossing, and the assumption is that the period length is fixed, which turns out to be a crucially fatal assumption, as we will see. So now that we have these four methods, how do we compare them? What is the metric for comparison? So the metrics chosen are image distribution of across phases. So you have say 120 or so bins, and do you have equal images in them? Are they distributed uniformly? Statistically, one would want a uniform distribution. So, having 10,000 images, we would think is a good enough number to have statistical convergence. The second is the centerline intensity profile of the phase average image. Higher the intensity, the better it is, because then you have bright areas coinciding with bright areas and increasing it with intensity. Finally, a correlation of each image in the bin against a reference image. So have they been identified correctly? Have they good and high correlation coefficient or not? So the first thing is the image distribution, and we right off the bat see that there are only two which make the cut. That of the phase locked, of course, as it's a hardware driven preset number cycle, and that of the second type of POD, because we decided that we are going to sort them and give equal numbers to each. So the flip side of that is the image count in this is very small, because we are distributing equally. Is a socialistic distribution, if I may. And the other things we see that the POD, the method 1, has a highly uneven distribution, because you have a non-circular phase portrait, because the mode energies are not equal, either in M1 or in M3, like we had already seen earlier. The eigenvalues were very different. The zero crossing has a surprisingly and comparatively smoother variation, and there's a maximum of 10% of the deviation. And the window for all of these is plus minus 1.5, as I already mentioned, 3 degrees in width. The second metric to look at would be a centerline intensity profile. So if we took from each of these methods the case of the max deflection of the oscillating flow and drew the center line by standard means looking at gray levels, so how would it go? So here we would expect this being a supersonic flow on the exit, that we would expect that you identify the peaks properly from each of these corresponding to the shocks which you see in the flow. So we see here again that the phase lock performs exceedingly well, followed by the second POD method, the zero crossing method, and the POD M3. But the POD method 1, which is a standard POD method, performs poorly. What happens if you take the case of the center line? So at the mean position, zero deflection. So this is where the velocity of the sweep actually happens to be the highest, like a simple pendulum. And we see here that in this case,
Hello, good morning all. So welcome to session 1B in hall 2. So this session will be shared by Professor Sandeep Sarkar from Jadavpur University. So I request Professor Sarkar to please start this session.
Good morning.
Good morning.
I think am I audible?
Yes, sir, you are audible. Yeah, you can start the sessions.
Acceleration and component fluid and gas dynamics.
Yes.
We have a first presentation by Mr. Milan Kumar Mondal. So may I ask Mr. Milan Kumar Mondal to start his presentation on MSD mixed convective heat transfer in a partially driven cavity, filled cavity, copper or nanofluid, saturated porous media. So Mr. Milan Kumar Mondal, please.
Okay, sir. Myself, Dr. Milan Kumar Mondal. My paper entitled MHD Mixed Convective Heat Transfer in a Partial Heated, Partial Driven Cavity Filled with Copper Water, Nanofluid, Saturated Porous Media. And this is my paper ID, and my co-authors are the Dr. Paparesh Dotto, Dr. Nirmalendu Vishwas, Professor Dr. Nirmal Kumar Manna. I am from Department of Technical Education and Training, Government of West Bengal, in Mednipur Sadar Government Party Unit in the Mechanical Engineering. My presentation plan, the first of all introductory section, next of the objective and scope of studies of the problem geometry and some boundaries, conditions, mathematical models, analysis, results and discussion, which includes effect of Richardson number, impact of Hartmann number, nanofluid particle volume fraction, impact on the flow, and heat transfer characteristic analysis. Finally, that is the concluding remarks. The introductory section, MHD mixed convection, is the key challenges in the budding engineering problems, includes porous media, and translatory motion also includes the influence of magnetic field. There are several applications in the engineering problems that like MEMS, heat exchangers, etc. And all translation motion also induce the shear flow structure. Usually in many applications, the conventional working fluid like air, water, and glycol fails to fast response in the thermal process like heating, cooling. But with the inclusion of nano-sized conducting materials like copper, alumina, etc., with the base fluid shows considerable improvement in the heat transfer process, and also the imposed external magnetic field can effectively control the hydrodynamic behavior. It has also lessens the heat transfer rate, but it has got several industrial applications. On the perspective of the above, MHD combined free surface as well as forced convection, free or forced convection of a nanofluid filled porous cavity called PDC in partial wall heating. Objective and scope of work in that MHD mixed convection in that PDC with nanofluid saturated porous structure along with the externally imposed magnetic field has not yet been studied as far as our literature survey concerned. So our present work is formulated and motivated by the need to analyze the thermofluid flow and heat transfer performance of such PDC under various pertinent parameters. To improve the thermal performance of the system undergoing shear driven and buoyancy induced flow so that heat transfer can be enhanced. Geometry of the classical problem is also chosen with the consideration of the working nanofluid, boundary conditions, flow geometries and flow regimes. In that cases the insight of the heat and fluid flow characteristic is explored along with heat transfer enhancement features which can be computed with respect to best cases. Geometry and boundary of the physical problem, that is the square geometry. In its side wall, upper half portion is moving in both the side, and lower half portion is the heated heat source, means differentially heated with temperature TH, and top wall is the TC cooling and bottom wall is adiabatic. Here entire cavity is filled with copper water nanofluid saturated porous media, and in an externally imposed magnetic field of string V0 is imposed on the entire cavity. And boundary condition, the side hot walls no slip and theta equal to 1, side moving wall, upper direction is moving, gradient, temperature gradient equal to 0, bottom wall is also adiabatic with temperature gradient 0, no slip, top wall it is the cold, theta equal to 0, and geometry of the wall is defined by the xy coordinate. And mathematical modeling, the governing non-dimensional form equations are taken. First one is the continuity equation, and then two are the both x and y momentum equation, and this is the energy equation. That equation is used on the dimensionless variables in the length parameters, velocity parameters, temperature and pressure, pressure parameters, non-dimensional parameters, and the dimensionless parameters are the Reynolds number, Prandtl, etc., that can be defined in that way. And some assumptions are made during the analysis, that is the fluid may be taken as the steady, incompressible, laminar, Newtonian single phase homogeneous condition, uniform spherical nanoparticles, local thermal equilibrium, BFTM model. In safety structure, the uniform grids are chosen 200 by 200, FVM simple algorithm, ADSweep, TDMA, and error of the mass defect that is taken as less than 10 to the minus 10. In the result section, there are wide range of parameters have been varied. For first effect is the Richardson number, which is varying from 0.1 to 100. Impact of hardware number, that is no magnetic field 0 to 10 up to 100. Impact of the nanoparticle volume fraction, that is no particle, and then increasing to 0.05, that means 5% as well. keeping other parameters fixed value, that is Reynolds number have fixed value 200, and frontal, Darcy, and also the porosity and the velocity concentration upward in the positive relation. Heat transfer characteristic analysis that can be discussed later on. The results are illustrated using combined streamlines and isotherms, heat lines, contours, and average. The effect of Richardson number is visualized by the thermal field and fluid and energy flow patterns. The top panel shows the combined structure of the streamlines and isotherm, and the bottom panel shows the energy equation and energy lines in terms of heat lines contour. In the Richardson number, when less 0.1, the hot plumes from the heater region to going upwards and reach to the top panel, top walls, and after cooling, that fluids going downward, such that two vortices, symmetrical vortices with respect to the vertical plane, vertical mid plane are observed, whereas the symmetrical patterns also observed in higher Richardson number, and such that the higher Richardson number, the stretching of horizontal of the flow is observed, but congested in nature. In the hot region, the isothermal distribution are observed also. Isothermal distribution is symmetrically processed in entire region of the cavity. Here, with the increment of the Richardson number, Nusselt value is highly increasing in nature. Effect of the Hartmann number, visualization thermal field and fluid energy flow pattern. There is no magnetic field in the first column, then higher magnetic field. In the higher magnetic field, almost nature is same, symmetrical structure, but at higher magnetic field, the OAV-like structure in the flow as well as the thermal, isothermal and energy structure is observed, and here the Nusselt value is quite decreasing because the buoyancy effect in counteracts due to buoyancy effect, it counteracts due to the magnetic field, so that the heat transfer rate is decreases. Inclusion of the nanoparticles impact is visualized. There is no particle, and there is a particle in 2% and 5% of the copper metal particle. The structure of the flow and isotherm or energy almost same, but here the Nusselt value is increasing. That means some enhancement in heat transfer due to the particle inclusion of the with the base fluid water. Heat transfer characteristic features with the varying Richardson number with Hartmann and nanofluid particles. Here, with the increment of the Hartmann number, Nusselt value decreases, and with the increment of the nanofluid particles, that is the heat transfer characteristic means Nusselt value increases. That increment, that means the enhanced features of the increment of the copper nanofluid particles is about 7.5% at higher Richardson number, whereas the 13.45% decrement occurred in the heat transfer in the Hartmann number. Concluded, buoyancy effect is stronger and associated with the heat transfer rate is maximum at higher Richardson number compared to lower Richardson value because of the initial convection occur at higher digestion number. Almost 13.45% decrement of heat transfer occurs in higher atomic number, H equal to 100, compared to the no magnetic field. In addition, inclusion of the as well as the substantial increment of the heat transfer due to the increase of effective thermal conductivity, heat transfer enhancement rate is 0.77 to 7.51 compared to base fluid. In the entire analysis, subject PGC can afford valuable insight for conducting and controlling the heat transfer process in the thermal cavity and have a potential future work under multi-physical conditions. These are the references. Any question, please?
Thank you, Mr. Mondal, for this nice presentation. We may take maybe one or two short questions. So, any questions from the audience?
Yeah. Okay, sir.
Yeah. Please.
May I audible, sir?
Yes, you are audible.
Okay, sir. Any question, sir? You ask me a question, please.
Maybe one or two short questions.
Yeah.
From the audiences. Okay. I think if there are no questions, so from the audiences, I may ask one question. Like it is observed from your simulation results that I can see that effect of Hartmann number is less at a higher Richardson number. For example, Richardson number may be nearer to 100, but effect of Hartmann number is less in compared to if you compare the heat transfer enhancement or reduction in heat transfer. So why it is so?
Sir, actually Richardson number enhancement means that is the buoyancy effect in the thermofluid flow that is increases. That is why the increasement in the heat transfer rate. Buoyancy effect is with respect to the shear driven flow. Here shear force and buoyancy force both are actually applicable, but when Richardson number increases, that is the buoyancy effect is also increases. That is why that heat transfer enhancement is featured. But in case of Hartmann number, when there is no magnetic field, there is no imposement of that means enhancement in the heat transfer rate. But whenever magnetic field is increases, that means Hartmann number increases, that counteracts the magnetic field with the velocity component, vertical velocity component. That is why the reduce the heat transfer rate. This actually features is available from the governing equation. It is a negative term appear in that equation. That is why with the increment of the Hartmann number, that value of heat transfer decreases. That is that.
Okay. So I think some question. Dr. Uttam Sharkar. Yes.
Good morning to all of you. Am I audible?
Yes, sir.
Yes. You are audible, please.
Yeah. Thank you, Dr. Milan Mandal, for presenting such a nice work. I have one question. As you have stated that if you increase the Hartmann number, Nusselt number decreases because the heat transfer rate decreases. As the buoyancy, the buoyancy effect get nullified by the effect of magnetic field. Can you reverse the applied magnetic field direction so that it will assist the buoyancy field? That can be possible, isn't it?
No, it is not incorporated in our present work. I think your suggestion will be I am accepting. I think that will be incorporated in our future.
It is not included in present work, but whether it is possible, that is what I mean.
I think as per our concern, this is I think it is not possible. I think I will not talk about that. But we are not aware about that.
Okay. Thank you.
We have another. I can take another more question. So, Mr. DSI. Yeah.
Yes, sir.
Any question? Yeah. I can see there is. Okay. So if there are no other questions, let us thank the speaker So
thank you, sir. Thank you very much.
Okay, thank you. So let us move to our
Yeah.
next presentation by Mr. UK Sharkar and Dr. Nirmalendu Vishwas. The title of his talk is Natural Convection in a Semicircular Enclosure. So Mr. Sharkar, please.
Good morning to all of you. I am Professor Uttam Kumar Sarkar from Mechanical Engineering Department, Technomin Salt Lake. Today I am going to present my work on natural convection in a semicircular enclosure. So, internal free convection has been a topic of intensive research because it has ubiquitous presence in natural processes, engineering applications, biomedical systems, and so many other applications. Further, it presents an intricate coupling between the flow and transport processes, which often lead to a rich variety of flow patterns. There is an enormous pool of literature on the natural convection of different rectangular or square enclosure. In comparison to that, natural convection heat transfer on different non-rectangular enclosure is a relatively new subfield in the heat transfer research. It is to be noted that the enclosure with non-rectangular cross sections such as triangular or parallelogram section have several practical applications. Recently, Das et al. Reviewed the natural convection in different non-rectangular cross sections such as triangular section, trapezoidal section, or parallelogram section. With that, we come to the main motivation of this study, that is, after a detailed literature review survey, it has been found that natural convection in a semicircular enclosure which is being heated from the bottom is not studied yet. It is to be highlighted that the analysis of natural convection is not a matter of course. It has important applications for the design of nuclear reactor, heat exchanger, electronic cooling system, etc. So the main objectives of the present study can be summarized as follows. The first one, to numerically analyze the natural convection phenomena in a semicircular cross-sectional enclosure which has an isothermally heated flat base and isothermally cooled semicircular top surfaces. Further, the study presents the effect of variation of Rayleigh number on the evolution of velocity and thermal field inside the enclosure for a fixed value of Prandtl number, that is Prandtl number equal to 1. And last but the most important objective of the study is to determine the different steady solution branches that evolve as the Rayleigh number is varied. So with that, we come to the problem formulation. Figure 1 presents the schematic diagram of the problem. So there is a semicircular enclosure, the bottom flat surface of the enclosure is heated and the top surface is cooled as shown in the figure. And gravity vector is from top to bottom as shown in the figure. We assume a steady laminar two-dimensional flow of an incompressible Newtonian fluid and we apply the Bouchnik's approximation. With that, the non-dimensional governing equation can be given in a standard form, and equations 1 to 4 is governed by two non-dimensional parameters, that is Rayleigh number and Prandtl number, and for this study Prandtl number is fixed, so the solution is mainly governed by the Prandtl number, and the boundary conditions are for the flow is already specified in the dimensional form in the equation, and non-dimensional form it is given in the bottom of the slide. Now coming to the numerical procedure that is used for obtaining the solution of the problem. So solution of the thermofluidic problem is obtained using the finite volume code of ANSYS. A representative course matrix that is used for discretizing the computational domain is shown in the figure, and it can be seen that the computational domain is partitioned so that we can obtain a structured mesh, and the mapped phase meshing technique of ANSYS is used to generate the structured mesh with all the quadrilateral elements. And the grid independent study is conducted, and the study is conducted for the maximum value of Rayleigh number that is studied, and that value is R is equal to 10 to the 5. And for that maximum value of Rayleigh number, it has been found that if the number of elements is approximately 1 lakh, then the error in the solution is less than 1%. So this particular grid is used for all values of Rayleigh number which is less than equal to r is equal to 10 to the 5. The second order Upwind method is used for the discretization of convective terms, and the simple algorithm is used for pressure velocity coupling. Phase to interpolation scheme is used to compute the phase values of the pressure from the cell values, and to ensure the accuracy of the solution, iteration is continued till the residuals of all the governing equation is less than 10 to the minus 6. So with that, we come to the results of this study. First, it is noted that for all values of Rayleigh number that is studied, the flow structure appears in the form of a pair of counter-rotating convection cells. So the two-cell solution, which is found for all the values of Rayleigh number, is shown in the figure 3. So in figure 3, we present the contours of steam function as well as contour of static temperature. So first column presents the contour of steam function, and the second one presents the isotherm for different values of Rayleigh number. So the top row represents the lowest value of Rayleigh number, that is Ra is equal to 10 to the 3, and the bottommost row refers to the maximum value of Rayleigh number, 10 to the 5. In between we have the intermediate values of Rayleigh number. So if we refer to the Ra is equal to 10 to the cube, 10 cube isotherm, it immediately appears that the temperature conduce is due to the conduction heat transfer. Now as Rayleigh number is increased beyond 10 cube, and we can see that the temperature distribution gets deviated from the case of conduction dominated case of R is equal to 10 cube, and the deviation is becoming more and more as the Rayleigh number is increased. Further, it is noticed from the contour of steam function, as the Rayleigh number is increased, the convective motion, intensity of convective motion inside the cell increases. And at last, we can see that the x is equal to 0 line represents a virtual wall, adiabatic wall, which doesn't allow any cross flow and it doesn't allow any lateral heat transfer to take place. Next, we come to the most important finding of this study, that is, as we increase the Rayleigh number, after a critical Rayleigh number equal to approximately equal to 22,000, apart from the two-cell solution, there is a second steady solution which appears in the form of two pairs of counter-rotating convection cells. So the fourth cell structure that is obtained beyond R is equal to 22,000 is shown in the figure 4. And if we refer to the streamline and the isotherm for this fourth cell structure solution, we can see that as the Rayleigh number is increased, the shape and size of the convection cells are changing. Particularly as the Rayleigh number is increased, the size of the central convection cell continuously increases, whereas the cells which appears at the side of the enclosure get squeezed. Along with the increase in size of the convection cells, it is further noted that with the increase of Rayleigh number, the intensity of the convective motion also increases inside the convection cells. And if we refer to the contour of the isotherm, we can see the upward and downward plume-like structure, and this upward and downward plume-like structure can be correlated to the lines of stream function which have 0 value. So for psi value of 0, we can have this upward and downward plume-like structure, and this upward and downward direction is further correlated to the direction of the flow. If the direction of the flow is vertical or upwards along the psi is equal to 0 line, then there we have a upward plume-like structure, and vice versa. Okay, and further it is noted that with the increase in Rayleigh number, the isotherm gets progressively crowded near to the boundaries, and that can be very much evident for higher values of Rayleigh number. So with the increase of Rayleigh number, the temperature gradient near the wall increases, which implies the heat transfer also increases near the boundaries as Rayleigh number is increased. So here in this slide it presents the summary of heat transfer characteristic for the two-cell solution and the four-cell solution. And from the figure 5 we can see that average Nusselt number always increases as the Rayleigh number is increased. However, the rate of increase varies for different range of Rayleigh number. Particularly, it is noted that for a very low value of Rayleigh number, that is, say Rayleigh number is less than 2000, Nusselt number remains almost constant with respect to the variation of Rayleigh number. So this insensitivity of Nusselt number with respect to Rayleigh number for a small value of Rayleigh number may be correlated to the heat transfer characteristic that is present for low values of Rayleigh number, and we have already discussed that for low values of Rayleigh number, heat transfer phenomena is dictated by the conduction. And further, it is noted that Nusselt number for 4-cell solution is always less than the Nusselt number for a 2-cell solution, and this fact is further corroborated from the contours of the Cymax, that we have seen that for 2-cell solution the Cymax value is always higher than the 4-cell solution, which means that intensity of convective motion is always greater for 2-cell solution as compared to 4-cell solution. Consequently, the rate of heat transfer and the Nusselt number is higher for the 2-cell solution. With that, we come to the conclusion of this study. So the first conclusion is that steady state solution with 2 counter-rotating convection cells exists for all values of Rayleigh number that has been studied in this investigation. Secondly, it has been found that steady solution of the problem is non-unique. Particularly, it has been noted that as the Rayleigh number exceeds the value of 22,000, there are 2 solutions. Apart from the 2-cell solution, there is another solution with 4-cell appears, and that persists as long as Rayleigh number is greater than 22,000. And from the graph of the average Nusselt number, it has been noted that Nusselt number always increases with the increase of Rayleigh number. Further, it is noted that for very small value of Rayleigh number, for 2-cell solution, Nusselt number remains almost constant with respect to variation of Rayleigh number. And the last one is that the value of Nusselt number, average Nusselt number for 4-cell solution is found to be smaller than the corresponding value of 2-cell solution. So these are the references. Thank you. Now I open the session for question and answer.
Thank you, Dr. Shakar, for this nice presentation. So we may take maybe 1 or 2 quick questions from the audiences. So please.
Yeah.
Any questions from the audiences?
Shayathan, you show your screen and then I will listen to the answer.
Okay, so I have one question, Dr. Shakar. Yes. So it is found that from your numerical simulation data that for the 2-cell solutions, you have got higher heat transfer rate compared to the 4-cell solutions. So why it is so? Why it is so? Can you please explain a bit?
Yeah, actually, am I audible out there?
Yes, you are very much audible. Please.
Okay. Actually, from common sense, from intuition point of view, actually, if the number of cell increases, the heat transfer coefficient should increase. As a result, Nusselt number for 4-cell solution should be higher as compared to 2-cell solution. But in this simulation, we have got the reverse one, and for that, we check the contours of stream function. And when we when we compare the contours of stream function for given value, for a fixed value of Rayleigh number, say Rayleigh is equal to 20,000 or 50,000. If I compare the Rayleigh number 50,000 case for 2-cell solution and 4-cell solution, then we can see why it is happening. For 2-cell solution, the maximum value of Cymax, that is the maximum value of stream function that we have obtained, that is much larger as compared to the 4-cell solution. So which implies that if the stream function value is more, that means the volume flow rate inside the convective cell is high. That means the convective intensity inside the cells are much higher as compared to 4-cell solution. So in case of 2-cell solution, even though we have less number of cells, it compensates for the less number of cells because of its increased intensity of convective motion, and that ultimately increase the heat transfer rate for 2-cell solution. So
okay.
Okay.
Yeah, I got it. Thank you for your explanation. So let us thank the speaker. Now we'll move on to our next presentation by Mr. Sujit Kumar and Mr. Sushil Kumar Rathar. The title of the presentation is Computational Study of Flow and Heat Transfer Characteristics of Oblique Laminar Slot Jet Impingement on Isothermally Heated Moving Flat Plate. So, Mr. Sujit Kumar, please.
Hello everyone, I am Sujit Kumar from NIT Rourkela. Today I am presenting my first conference paper on the topic Computational Study of Flow and Heat Transfer Characteristic of Oblique Laminar Slot Jet Impingement on Isothermally Heated Moving Plate. Now in this presentation, I will discuss the following section: Introduction, Problem Specification and Methodology, Validation of Present Work, Result and Discussion, Conclusion and References. Let's come to the brief introduction of the impingement jet cooling. The impingement method is one of the efficient methods for cooling of a heated item, heat treatment of the metallic product, tempering of glass, drying textile and foodstuff. It also enhances the cooling of efficiency in the electronic industries nowadays. The cooling depends upon the geometrical condition of impingement jets. The flow and heat transfer characteristic of multi-jets can highly differ from a single jet. The main objective of the research is to study of flow pattern and thermal characteristic of laminar twin oblique jet impingement over a moving flat plate, and also to perform the parametric study by varying the following parameters: Reynolds number, velocity ratio, angle of impingement. Now, problem specification. The domain is restricted by two parallel plane surfaces as shown in figure 1. The lower surface is known as impinging surface, and the top confined wall holds the twin slot jet at some inclination with upper surface. The inlet velocity is uniform and the inlet temperature of jet is 300 Kelvin. The normalized dimension is used to define the geometry of the problem domain. The normalized width between upper and lower surface and normalized length between the innermost point of twin slot jet are H and L respectively. This is the schematic diagram of the domain. Here theta is the impingement angle from the upper surface, this is the inlet temperature, and plate velocity is u infinity, and total span length is 60 dh. Dh is the normalized header diameter of the slot jet, W is the jet width, H is the normalized width between upper and lower surface, L is normalized length between innermost point of the twin slot jet, and 0.5 is the normalized hydraulic diameter of the slot jet. The following assumptions were taken while solving the computation. The flow is assumed to be laminar, incompressible, steady, and two-dimensional. The working fluid is air, and its thermophysical properties are assumed constant. The following non-dimensional governing equations are used to solve the problem. First one is continuity equation. It shows the conservation of mass. It means the rate of mass enter in the system is equal to the rate of mass leave the system. The second equation shows the momentum equation in x direction and the third in y direction. The fourth equation shows the conservation of energy. In the above equation, there are many non-dimensional variables are used, which are following: x, y, u, v, p, etc. The velocity ratio. It is the dimensionless parameter defined by the ratio of plate velocity and jet velocity. In this study, the value of velocity ratio is considered in range r is equal to 0 to 2.0. Mathematically, it's given in equation 5, and the local Nusselt number is obtained by the following equation: Nux is equal to minus d5 by dy in equation 6. And now move to the boundary condition. No slip boundary condition are imposed on the walls. The top wall, which contains the impingement jet, considered as adiabatic. The impingement plate is considered as isothermal and moving with velocity u infinity. Both sides of wall flow boundary imposed by constant pressure outlet. The computation of various combination of parameters were performed by taking one parameter as a variable, while others were keeping constant. The combination of parameters was tabulated. The total 75 combinations were computed and results were observed. Now come to the solution methodology. The solution was performed in ANSYS 18.2. An algorithm was selected PSOAN in which momentum and energy discretization scheme power law were selected. The residual was set 10 to the power minus 6 for all cases. Grid independent tests were performed for the different combination of a grid, a stationary plate. 4 refinement levels were selected for the grid independent test. For all cases of refinement, the variation of local Nusselt number curve along its axial length are computed and plotted in figure 4. And peak value of local Nusselt number and average Nusselt number are tabulated in table 1. It can be seen that beyond the third refinement, 74 into 250, the change in Nusselt number distribution is insignificantly. So the grid size 74 into 250 is selected for the present study. And the figure 3 shows the sample base used in the computation of the flow domain of full domain. Now validation of present work. The strategy is followed to solve the problem include the validation of numerical solution for the twin slot Z impingement. In this, the result were obtained from the given parameter Reynolds number 100, L is equal to 4, H is equal to 8 at different angle at theta, compared with the result of series for a stationary plate condition as shown in figure 5. Overall good match has been obtained. Now comes in result and discussion section. First we discuss a streamline pattern. Figure 6 and 7 show the streamline pattern for a stationary plate at Reynolds number 100. It can be seen for a stationary plate condition. The symmetric flow field is obtained when the impinging jet divided into two walls. The formation of multiple recirculation occur. Figure 8 to 13 represent the streamline pattern for moving plate condition at different Reynolds number and different velocity ratio, and also at different theta impingement angle theta, in which the streamline pattern different for different velocity ratio and different for different Reynolds number. It can be seen that multiple recirculation are occur in left side region. Now comes to the temperature contour. For a stationary plate condition, symmetrical pattern of temperature distribution is observed as shown in figure. The region surrounded the jet interest has significantly lower temperature, which indicate the existence of recirculation region. Temperature of the domain is more uniform at the case of lower impingement angle. For a moving plate condition, it also seen that the temperature distribution is different at different location, and at lower impingement angle, the temperature distribution is more uniform in this. Now comes to the Nusselt number distribution along plate length. Figure 20 shows the distribution of local Nusselt number along plate length. It can be seen that at high value of impingement angle, more localized cooling at jet region occur. At lower impingement angle, more distribution cooling occur. And the curve at an angle 45 is higher than all cases. Hence, for more distributed cooling for a stationary plate condition, impingement angle 45 prefer. And the figure 21 shows that one of the combination of moving plate condition in which impingement angle is taken as a variable. The overshoot in local Nusselt number near the left region is due to pressure outlet boundary condition and negligible a small boundary thickness. And figure 20 shows the Nusselt number distribution for various velocity ratio at constant impingement angle and constant Reynolds number. And it can be seen that higher velocity ratio, high value of heat transfer occur and it more uniform. Figure 23 shows the variation of local Nusselt number for a various Reynolds number. While other parameters are kept constant, it observed that the value of local Nusselt number increases when increased the Reynolds number. Hence, heat transfer increases with increased Reynolds number. And figure 4 shows the comparison a study of average Nusselt number for a different Reynolds number at different impingement angle. It can be seen that when Reynolds number increases, the average Nusselt number increases too, and more heat transfer occurs at greater impingement angle. Conclusion: for a stationary plate, a symmetric pattern of temperature distribution and a streamline are observed. For a more uniform cooling, the value of theta should be in between 30 to 55. At higher value of Reynolds number, the peak value of NU exhibited toward the jet region. As the Reynolds number of the jet increases, there is increase in the value of Nusselt number. This trend is even followed when the velocity of the plate increases. For the range velocity ratio, consider the study with increase the plate velocity, the value of Nusselt number jet inlet region decreases. The value of Nusselt number increases with increase the Reynolds number for the given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. And thank you.
Thank you, Mr. Kumar.
I'm an undergraduate.
Thank you, Mr. Kumar. Thank you, Mr. Kumar, for this nice presentation. So we may take maybe one or two quick questions from the audiences.
Okay. Thank you, sir.
Okay. Any questions from the audience? Okay, if there are no questions from the audiences, I have one short question for you, Mr. Kumar. So it is observed that, like in general, your average Nusselt number, that is heat transfer, is increased with increasing the jet impingement angle. For example, at impingement angle 90 degree, you have got a maximum heat transfer. So why it is so? Do you have any explanation on that?
Yes, sir. When increase the angle, the Nusselt number also increases, and the heat transfer directly proportional to Nusselt number. So when increase the angle, the jet directly are striking on the moving plate, moving plate, so that the more velocity of jet at that time at lower inclination angle, the velocity in y direction is a composition is less as compared to E. One component of jet is less, I think.
Okay. Understood. We have understood. So let us thank the speaker. Thank you, Mr. Kumar. So now we will move on to our next presentation by Mr. Ansh Patel. The title of his talk is Performance Enhancement Analysis of Diffuser Augmented Wind Turbine Duct. So Mr. Patel, please.
Good morning. My name is Ansh Patel and I'm an undergraduate student at VJTI Mumbai. Today, I'll be presenting the research done by me and my fellow classmates under Dr. Mandar Tendulkar at VJTI. The title of our paper is Performance Enhancement Analysis of Diffuser Augmented Wind Turbine Duct. We'll start with a brief introduction to the topic. Since large wind turbines are difficult to install in populous cities, modular wind turbines are becoming more and more suitable for small-scale power generation. The diffuser augmented wind turbine is one type of such a small-scale turbine. As it is surrounded by a duct, it can produce up to twice the power of a bare turbine. Because the duct helps accelerate the incoming wind, which increases the power output. The duct also helps reduce the aeroacoustic noise generated by the blades, which is another issue in populous cities. The aim of our project is to enhance the performance of the duct of a previously designed diffuser augmented wind turbine. This is achieved by integrating two aerodynamic devices, namely the vortex generating flange and the flow deflector. We have used the ANSYS Fluent software to gauge the effects of these improvements. We have selected a previously designed diffuser augmented wind turbine as a baseline model. It was designed by the alumni of our college as part of their undergraduate thesis. This thesis can be found from reference number 4. So the operating principle of the flow deflector is that it is placed in the upstream region of the turbine and it diverts the incoming wind to the outer regions of the blade. Due to the continuity equation, the decrease in flow area that results from such a diversion increases the velocity of the incoming wind. Thus the lift force, torque, and power output of the turbine increase commensurately. Moving on to the vortex generator, it is the flange on the outer surface of the duct. Due to its blunt shape, it causes flow to stagnate in front while a wake is created in the downstream region. This causes vortices to shed from both the internal and external flows. The lower pressure wake is spread over the outlet plane of the diffuser, creating a lower pressure outlet. This will accelerate the incoming wind and hence increase the turbine power output. I will now talk about the computational modeling. We carried out flow simulation on ANSYS fluid from which the throat velocity was computed. This parameter was used to select the optimal configuration of the two devices. We simulated two-dimensional turbulent flow at steady state using the K omega model. This model was selected as it has become the industrial standard for external flows. We used the pseudo transient solver settings as the under relaxation of the method allowed convergence for all cases. We used a rectangular flow domain of length 31.5 meters and height 10.5 meters. The mesh settings were as shown in the slide. To obtain convergence, we decrease the mesh size for subsequent iterations. In this slide, the boundary conditions are shown. The incoming wind speed is the yearly average speed in Mumbai. The governing equations solved by the software are the continuity equation and the Navier-Stokes equation. We began by optimizing the flow deflector geometry. First, we selected the optimal overall shape. We considered a flat plate, a solid body with slots, a NACA 0012 F-oil, and an F-oil rotated by 180 degrees with respect to the flow. A decision on the optimal geometry would be made by considering the average velocity in the concentrated region, shown by these yellow lines. As we can see in the table, NACA 0012 F-oil rotated by 180 degrees gave the highest increase in VCONG over the baseline model. Hence, it was selected for further analysis. The solid body performed poorly as it caused significant wake formation. The NACA 0012 F-oil, due to its aerodynamic shape, had minimal separation and hence gave the best results. Now we look at the optimization of the flow angle of the F-oil. This is the angle between the wind velocity and the chord of the F-oil measured in the clockwise direction. We also considered the size of the wake formed behind the F-oil. This was measured along the yellow line in the figure. The results indicate that a 10-degree flow angle gives the best compromise between higher VCONG and smaller wake size. Also, increasing the flow angle results in a greater blockage and diversion of the flow, resulting in better flow deflection but larger wake size. The next geometrical parameter considered was the chord length of the F-oil. Our analysis showed that 25 cm chord gives the best VCONG and a wake size of 6 cm. Since the difference of 0.5 centimeters is not deemed very significant, the chord length is fixed at 25 centimeters. Lastly, the radial span of the flow deflector is optimized. It is the radial distance between the centerline of the duct and the upper edge of the flow deflector. A decision on the optimal radial span is not made here, but is deferred to a later section, which I'll be moving on to shortly. Now we move on to the geometrical optimization of the vortex generator. As was the case with the flow deflector, we first optimized its shape. Although previous studies on the topic have optimized the vortex generator for other geometrical parameters, different shape profiles have never been considered. Thus, we analyzed the flat profile, the semicircular, and the mirrored semicircular profile. The flow parameter used to select the optimal configuration is the average velocity over the entire throat of the duct. From the table, we can see that the flat profile gives the highest throat velocity. The semicircular profile also performs similarly. On the other hand, the mirrored profile performs poorly. This can be attributed to the trapping of the vortices and the cavity created by the semicircle, seen in this vector plot. There is less interaction with the internal flow and hence the throat velocity is less. Moving forward, the flat profile was selected for further analysis. We'll now look at the optimization of the angular inclination of the flat profile. The manner in which the angle is measured can be seen in this figure. The results indicate that as the angular inclination increases, the vortex shedding becomes more effective till it reaches the optimal value. In this case, that value is 12 degrees. Finally, we take a look at the optimization of the radial span. The radial span is the length of the vortex generator measured along the vertical axis. We see that as the radial span increases, so does the average throat velocity. The maximum is reached at 20 centimeters of radial span, after which there is negligible change. This result agrees with that obtained by Oya et al. The final geometry of the vortex generator is shown in this figure. We have also analyzed the duct performance in terms of the rotor equivalent wind speed, or REWS. This parameter is used to determine the effective incoming wind speed for non-uniform wind profiles. Due to the wake behind the flow deflector, the wind profile incident on the turbine in this case will also be non-uniform. REWS is measured by taking the average wind speed in each section over which we can assume the wind velocity to be fairly constant. We have taken 5 such sections as shown in the figure. Additionally, the wake size is also chosen as a selection factor for the optimal design. Now we shall see the results for different flow deflector configurations and show our final selection. A 10-degree angular inclination is optimal in terms of REWS and average throat velocity. A radial span of 30 centimeters is reckoned to give the best compromise in terms of REWS, and it is selected as the optimal configuration of the flow deflector. Additionally, we also analyzed a slotted airfoil to determine whether it would give a smaller wake, but this caused the REWS to decrease as well. Thus, the slotted airfoil was discarded. We also carried out a mesh size independent study on the final model. As shown in the table, the flow parameter V average becomes fairly constant with smaller mesh size. Thus, the results have achieved convergence. We shall now compare the optimal duct containing the selected flow deflector and vortex generator geometries with the baseline model for different wind speeds. As shown in the table, the augmentation factor is about 1.63. This means that the incoming wind is increased by 1.63 times its inlet value. The incoming raw wind power to the turbine also increases by 62 to 65% of the baseline value. The graphs indicate a fairly constant difference between the design and the baseline model over different wind speeds. I will now summarize our work and conclude this presentation. We integrated 2 aerodynamic devices to optimize the performance of a diffuser augmented wind turbine. These devices were the vortex generating flange and the flow deflector. The flow deflector is selected as an inverted NACA 0012 airfoil with flow angles of 10 degree and chord 25 centimeter. The radial span was 30 centimeter. The vortex generator has a flat profile with 12-degree angular inclination and 20 centimeters of radial span. The optimal geometry has a 64% increase in REWS, 25% increase in magnification factor, and 25% decrease in the cut-in speed with respect to the baseline model. Thus, because of the decrease in the cut-in speed, the turbine is able to operate for a larger portion of the year, increasing annual energy production. These are the references which we used for our research. Thank you for staying with us. We will now address any related queries.
Thank you, Mr. Patel, for this presentation. So we may take maybe 1 or 2 quick questions from audience. So any questions?
Yes.
Yeah, Mr. Saraj Kumar Panda. Yeah.
Yes, a very nice presentation. What I have seen, you have used a SST K omega model, right? So have you checked any other turbulent model for your simulations, or if you have used only one model, then how you have ensured that this model is working fine for your simulations?
Sir, so good morning. Sir, so our paper is an extension of the work that has already been done by some of our seniors, and their paper can be found in the reference. So they use the K omega model and the Spallet-Allermas model and they found that in the K omega model, they could validate the study with a previous paper, and they would find that the wind speed and the induction factors of the turbine were matching a previous study. So that's why we also selected this model.
Okay, okay, nice. Thank you. Okay.
Any other questions? Okay, so if there are no questions from audience, so let us thank the speaker again. Now we will move on to our next presentation by Mr. M.A. Jashant. Started off his talk is a new efficient flux limited hybrid scheme for the 1D Euler equations. Mr. Jashant.
Yes, sir. Good morning to everyone present here. I am Jashant MS, co-author of the paper, A New Efficient Flux Limited Scheme for 1D Euler Equations. We are grateful to FMFP and IIT Guwahati for giving us an opportunity to present our work here. The objective of our work is to create a hybrid scheme that incorporates the advantages of the parent schemes it is based on. We have compared the result of this hybrid scheme with its parent schemes for standard one-dimensional test cases involving shocks and discontinuities. The hybrid scheme is observed to perform better in handling numerical anomalies such as overshoots, undershoots, wiggles, and also demonstrates better shock capturing abilities. The parent schemes which we have chosen are the Lax-Friedrich scheme and the Lax-Von scheme. The conservative form of the two schemes are shown in the slides, and we have used the Richter-Meyer method for Lax-Von scheme. Here, U is the conserved variables vector, F is the flux vector, and lambda is equal to delta T by delta X. The reason for choosing these schemes are that the Lax-Friedrich scheme is an explicit first-order accurate scheme, so the results of the Lax-Friedrich scheme may not be accurate because of the diffusion, but the solution has no spurious oscillations. The Lax-Von scheme is a second-order accurate scheme, therefore the solution is more accurate, but it has spurious oscillations at the discontinuities and corners. As mentioned before, the objective is to develop a hybrid scheme that has an improved accuracy comparable to the second order scheme, but without the spurious oscillations typical to a second order scheme. We have used standard shock tube test cases for validating our results. Totally, we have used 3 test cases for validation. The first 2 test cases are standard shock tube test cases which we have taken from the paper published by SORT. In the first test case, the shock tube is 20 meter long and it is divided into 2 equal sections, that is the working section and the driving section, with the pressure and densities as mentioned in the table. The interaction between the 2 sections is studied after the partition is removed. The second test case is similar to the first test case, but the length of the shock tube is now 25 meters and the sections are divided as 10 meter long section and a 15 meter long section. The pressure ratio between the left and right sections is now 100:1 and the density ratio is also now 100:1 compared to the 8:1 density ratio in the test case 1. Test case 3 is a blast wave problem and we took the test case from a paper published by Woodward and Colella. In this test case, the shock tube is divided into 3 different sections as shown in the slide and the properties are as mentioned in the table. The distinction of this test case among the 3 is that there are multiple interactions of shock waves and contact discontinuities which are captured in the results. Unlike the other 2 test cases, the interaction of strong shock waves and discontinuities were not captured well with the coarse grids. Therefore, we had to use a finer mesh in order to capture the results better. The hybrid scheme, as mentioned, is a combination of Lax-Friedrich scheme and the Lax-Von scheme. The Lax-Friedrich scheme is modified before using it in the hybrid scheme. This is done in order to reduce the step oscillations produced in the result. This is achieved by introducing the artificial viscosity in the conservative form of the equation, and the result produced was smooth without any oscillations. The epsilon in the original equation is changed into a weighted average function in order to introduce the artificial viscosity. In the weighted average function, the variable A is the fluid velocity at the node I plus half. and theta is the weightage factor such that the value of theta lies between 0 and 1, and it is determined by trial and error method. The lax Van scheme is used as it is without any modification. The conservative form of the hybrid scheme is given in the slide. The parent schemes are incorporated in the flux term of the equation. The flux in the hybrid scheme has a character phi, which ensures that the scheme doesn't produce spurious oscillations. The function phi used is taken from a paper published by Zalesek on multidimensional flux-corrected transport algorithms. After using the phi from the paper, the character term turns out as a min-mod function of 3 variables. Here, the flux terms with superfix 2 and 1 are conservative fluxes of the second order Lax-Van scheme and the first order Lax-Friedrich scheme respectively. So the flux term of the hybrid scheme turns out as shown in the slide. At corners where there is spurious oscillations in the second order scheme, the min-mod function turns the flux character into 0, thereby making the flux of the hybrid scheme fully dependent on the modified Lax-Friedrich scheme. So there will be no spurious oscillations. At rest of the places, the equation is a combination of modified Lax-Friedrichs and Lax-Van schemes. The value of theta and mu are found out using the trial and error method. And the value chosen is such that it works in all 3 test cases. The codes for all these schemes are written in C++. The following slides contains the results of all 3 test cases, and the graph in the top left corner is a pressure graph, and the graph in the lower right corner is a velocity graph. So for test case 1, we can see that the Lax-Friedrich scheme is less accurate, and the Lax-Van scheme has some spurious oscillations at the corners and discontinuities. But the hybrid scheme incorporates the advantages of both schemes appropriately. And for the test case 1, the CFL value is 0.2, nu value is 0.3, and theta value is 0.5. Similarly, for test case 2, we can infer the same points, but the test case 2 has a CFL value of 0.1. From the results, we can see that the flux limiter works as intended and the hybrid scheme does not produce any spurious oscillations. Also, it maintains the accuracy of the second order scheme. In the test case 3, the oscillatory Lax-Van scheme produced fluctuating results and therefore was not plotted for comparison. But the hybrid scheme was more accurate than the Lax-Friedrich scheme and the Lax-Van scheme. And the CFL value for test case 3 was 0.2, and the nu and theta value remained same for all 3 test cases. In conclusion, the hybrid scheme is able to produce accurate results without spikes or oscillations. When compared with the Lax-Friedrich scheme, it is less diffusive and therefore more accurate. However, the addition of artificial viscosity makes the scheme diffusive at the discontinuities and shocks, thereby reducing the accuracy at those particular places alone. But it is still more accurate than the spurious second order Lax-Van scheme. The advantage of this scheme is that for different test cases and different scenarios, the 2 parent schemes can be combined appropriately with the variable theta as the handle. And similar to theta, the mu can be used as a handle for adjusting the artificial viscosity. When compared with more sophisticated schemes like row solvers, the hybrid scheme has a comparable accuracy and can be developed into a multidimensional scheme. Once again, we thank you for this opportunity to present our work at this conference. Thank you.
Thank you, Mr. Jashan, for nice presentation. So maybe we may take maybe 1 or 2 questions from audience.
Sure, sir.
Any questions from audience? Okay, I think there are no questions from audience. So I have one question for you, Mr. Jashan.
Okay,
so,
sir.
What what is your expectation if we change the value of mu and theta? So
Yes, sir.
would that like, for example, while calculating the pressure and velocity variations for
Yes, sir.
with different schemes, so would that give you some different kind of scenarios if we change the values of mu and theta?
Yes, sir. For these three test cases, value of 0.5 for theta worked well, sir. If we would have changed, let's say for 0.6 or 0.4, maybe, the result would be more dependent on lax Fredericks if it is for 0.5, and it would be more dependent on lax Vendroff if it is on 0.4, sir. So if the value was 0.4, the value will be more accurate, but the results will have little spurious oscillations than the optimum value of 0.5. Similarly, if a value of 0.6 was used, the solutions will be less accurate compared to the optimum value of 0.5, but it will be more dependent on Lax-Friedrichs schemes.
Okay, I have understood. So, yeah.
Yes.
Any questions?
Yeah, Dr. Sandeep, this is Ganesh from IIT Palakkad.
Oh, yes, Mr. Dr. Ganesh, please.
Yeah, I have just one quick question. Jaswant,
yes, sir.
Yeah, so I was just wondering, there are other hybridization schemes available. So how does your current approach compare against them? And
Yes,
second
sir,
thing is that what
yes.
is the influence of these choices on the overall accuracy of the scheme? Because typically, if you switch from lax Vendroff to lax Fredericks, you are going to locally lose out on the order of accuracy. Even though you are having lesser oscillations, you will lose out on the order of accuracy. So can you comment on these 2 points?
Yes, sir. As I have mentioned, there are a lot of other sophisticated hybrid solvers, sir, like the row solvers. But those have the hybrid scheme which we have developed has a closed form equation. So it is very easy to code and it is very basic.
No, there exist other hybrid solvers as well. I mean, while lax Frederick and lax Vendroff, can't you choose any two schemes?
Yes, sir.
I mean,
So
there are other hybridizations available, not just with Riemann solvers. You are having other solvers available,
yes, sir.
which can be hybridized. So
Yes, sir.
what's
So
the motivation behind the specific choice?
we wanted to combine a first order scheme and a second order scheme, sir. So we wanted to check negate the disadvantages of both schemes by having that adding the advantages of two schemes.
That is true, but how does it impact the order of accuracy? I mean, were you able to look at that?
Yes, sir. At the corners, as you mentioned, at the discontinuities, because of the diffusion, we were losing the accuracy, sir, of the second order scheme.
Right.
But as I was saying, to so much extent only we can negate the disadvantage of the scheme by adding the advantages, sir. So the optimum value which we found out for theta value was 0.5. If it was either a higher or lower value of theta was used, the scheme was less accurate, sir.
Okay. I mean, just one quick final question. I mean, why do you want to combine it with lax Frederick when you already have a limiter in place?
Yes, sir. When the limiter turns out, when the limiter is written in a different form, it turns out as a lax Frederick scheme. So that's why we thought we'll use lax Frederick.
Thanks, Jashwant. Thanks, Dr. Sarkar.
Thank you, sir.
Okay, thank you, Mr. Jashwant. Well, so let us thank the speaker. Now we'll move on to our next presentation by Mr. Binod Kumar Saini. So the title of his talk is Fin Effectiveness and Efficiency of Air-Cooled Condenser, a Numerical Approach. So Mr. Saini, please.
Yes, sir. Sure. Greetings to everyone. My name is Binod Kumar Saini, and I am here to present numerical study of fin effectiveness and fin efficiency of air-cooled condenser under the guidance of Dr. Hardik Kotadia, Department of Mechanical Engineering, IIT Jodhpur. This is the outline of the presentation. Heat transfer is widely used in almost every type of industry to to remove the heat from the machinery parts. Heat can be transferred between two different temperature fluids via direct contact in between them or without direct contact in between them. But most of the application in industry require no direct contact between both the mediums, like in the condenser, where both like one fluid flow inside the tube bundles and the another fluid flow at different temperature outside the tube bundles. And in the whole process, heat is transferred via surface of the geometry. So if we will increase the surface area of the geometry, the rate of heat transfer will be increased, but it will restrict the flow of the fluid. Heat transfer was always a topic of interest from the early times, and many techniques was found for enhancement of heat transfer. Huffman et al. Studied the effect of fin geometry and fin dimensions on heat transfer and pressure drop. Yuldage and Yunchu experimentally investigated free convection characteristic on annular fins on a horizontal cylinder. Liu et al. Performed numerical investigations to determine the air side performance of heat exchanger. Hossein Nemati performed numerical simulation for different turbulent model on fin tube heat exchanger. Lane et al. Studied the air side thermal performance and overall cycle efficiency for different type of air-cooled condenser. The objective of present study to study the enhancement of heat transfer coefficient in the air-cooled condenser and compare the performance of the air-cooled condenser after the enhancement and observe the behavior of heat transfer and the performance of air-cooled condenser with the mass flow rate. These are the geometrical parameters of air-cooled condenser, in which stainless steel 30 mm inner diameter pipe was used with the pipe thickness of 2.5 mm, and fin inner diameter was 35 mm and outer diameter is 70 mm, and fin was used tapered. So the fin tip thickness was 0.15 mm and fin root thickness at the surface of the pipe was taken 30 mm, 0.30 mm, and the fin pitch is taken 2.3 mm. And here we can see this is the inlet of the air in the direction of flow. The pipe longitudinal pitch was taken 67, and in the transverse direction of the flow, the transverse pitch is taken at 77 mm. And there are 3 row of tube bundles is taken, and number of tube in each row was 13, 14 and 13. And for the original view we can see the 3D models, which is the complete view of the air-cooled condenser. There are many turbulent models available in the ANSYS Fluent, but K omega shear stress transport model was used for the study because it is mostly used or best predictable model in this field, and it gives the close approximation of flow separation near the wall for y plus less than 1. And for analysis, unstructural mesh was used, and mesh was performed fine near the wall to observe the separation phenomena. And grid size was selected such that the y plus should be less than 1 near the wall. Result of the simulation in the ANSYS converged with the mesh size. So over result should be independent of the mesh size. But increasing the number of elements will also increase the simulation time. So to find the optimum grid size, mesh independent test was performed from coarse to fine mesh, and at 3.7 lakh number of elements, it was found that there are no much changes in the results. Boundary condition at inlet was given as air inlet velocity and temperature of air was given at 298 at room temperature, and the boundary condition at pipe hole was given no slip condition, and pipe inner wall temperature was given as 318 Kelvin, which is close approximation of 95 millibar steam pressure. And at outlet, outflow condition was given, and to reduce the simulation time, symmetrical condition was given in the axial direction of the pipe. To validate the turbulence model, the numerical simulation was performed without fin tube bundles with K omega models, and the result of the simulation was compared with the formula given by Dukaskas, which is depend on Prandtl number and Reynolds number. For a range of 2000 to 11,000 Reynolds number, the Nusselt number and was calculated for Dukaskas formula and from the simulation also, and the error in between two was around 2.5 to 5%, which is in acceptable range. And this is the graphical representation of Nusselt number with the Reynolds number for calculated and simulated cases. Heat transfer rate was calculated by m dot Cp delta T, in which m dot is the mass flow rate of air at inlet, and Cp is the specific heat of air, and delta T is the temperature difference of outlet and inlet of the air. In the first table, the heat transfer without fin tube bundle was calculated, and this is the temperature difference for the given mass flow rate of the air, and corresponding heat transfer rate was calculated. After that, for same mass flow rate of inlet air, the temperature difference for actual and ideal case was calculated. In the actual case, the pipe inlet temperature is given, and the fin surface temperature will vary according to the conduction. And for ideal case, the fin surface temperature is given same as the pipe temperature. So in this case, the ideal heat transfer rate will be found, and from both the data we will calculate the fin efficiency and fin effectiveness. Heat transfer rate is calculated with fins and without fin cases for a range of mass flow rate, and it was found that rate of heat transfer increases with the increase in the mass flow rate, and fin effectiveness is the ratio of heat transfer rate with fin and heat transfer rate without fin, and fin efficiency is the actual heat transfer rate to the maximum heat transfer rate can be possible. So for this range of mass flow rate, the fin effectiveness was found with the range of 7 to 10.8, and fin efficiency was calculated around 98 to 91%. And this is the temperature contour comparison and pressure contour comparison without fin and with fin cases. And here in the temperature distribution, we can see that the temperature changes around average temperature changes 3 to 4 degrees centigrade, and here is around 16 degrees centigrade inlet and outlet temperature difference. But for the same case, here is the pressure drop is less, and with fin case it is more pressure drop in the inlet to outlet case. The whole study shows the numerical analysis of air-cooled condenser with fin and without fin cases, and fin efficiency and fin effectiveness was calculated. And from the study we observe that fin effectiveness is maximum for higher mass flow rate, and fin efficiency is maximum for lower mass flow rate, and it decreases with increasing in the mass flow rate. And for air, volume flow rate of 4,890 meter cube per hour to 18,335 meter cube per hour. Fin effectiveness lie between 7 to 10.8. And fin efficiency for the same volume flow rate lie between 91 to 98.5, where 98.5 is fin efficiency is at lower mass flow rate.
Thank you, Mr. Saini, for this nice talk. So, any questions from the audience?
Hello, good morning. Yeah, I have a question. Like,
please.
Is my voice audible?
Yeah, you are audible.
You are audible now. Yeah.
Yeah. Okay. Good morning. Yeah, Mr. Saini, I have a question that, as we know, there are many models, but what is the significance that you have used the K omega model for your problem?
Yeah, there are many turbulent model available in the ANSYS, but the K omega model is mostly used and gives close approximation to flow behavior and the flow separation near the ball surface. So I use the K omega model, and for that my results are validated with the Joukaspev formula for without thin tube bundles, which are the results are in like within 6% error. So that is acceptable range, and like the simulation result and the calculated results are compared. So the K omega model is close approximation of my simulation. That's why I use K omega model.
Okay, okay, thank you.
Any other questions?
Yeah, hello everyone.
Yeah.
Yeah, I have one question. That whether you have a quantified pressure drop while using fin?
Yeah.
So what was the value?
Yeah, in the pressure drop, like without fin case, the pressure drop is around 10 Pascal, and when I use the fin, the pressure drop increases to 52.2 Pascal. So that is around 5.5 times the like previous case. But in the study that I can further in the future study I can include that to calculate the thermal performance factor, which include the enhancement of heat transfer to pressure drop. So that will be like more comparable study in both the cases.
Okay, thank you.
Fine. So let us thank the speaker, Mr. Saini. We now move on to our next presentation by Mr. Shiva Kumar Bathina. The title of his talk is Numerical Assessments of Thermal Radiation from Large Kerosene Open Pool Fires. So Mr. Bathina, please.
Hello, greetings to all. My name is Shiva K. Battina, working with Professor Sudhir Siddhap Reddy from Indian Institute of Technology, Dharwad, India. Today, I am going to present a study on numerical assessments of thermal radiation from large kerosene open pool fires. The outline of the presentation is motivation and objective of the study, numerical simulations, semi-empirical modeling, resultant discussions, conclusions, and references. Motivation and objective of the study. Fire is the most common accident in process industries. Among all fire accidents, 44% of accidents are caused due to pool fires. The thermal radiation and convection contribution from such fires are 92 to 100% and 0 to 8% respectively. So it can be seen that thermal radiation is the primary source of open pool fire accidents. The experiment studies pertaining to measure the thermal radiation from a large open pool fire are limited in the literature. Moreover, conducting such big experiments are difficult, expensive, cause environmental degradation. However, few semi-empirical models are available to estimate the thermal radiation, but these models have its own limitations. Computational fluid dynamic studies have emerged as a promising tool to overcome these limitations. Using CFD as a tool, the thermal radiation from the fire source to the adjacent object can be assessed. So in this work, along with numerical simulation, semi-empirical modeling is also done, and results are compared with previous reported experimental data. Numerical simulations. In the present work, the numerical simulations are performed using Fire Dynamic Simulator version 6.7.0. FDS is a CFD code. It consists of large HD simulations and direct numerical simulations. The present work is simulated using LES model, which offers less time demand than the DNS. Some of the major default features of the FDS are low Mach number LES, explicit second order energy conserving numeric, structured uniform grid, lumped species approach, diode of eddy viscosity closure, constant turbulence limit and Prandtl numbers, fast chemistry for single step reaction between fuel and oxidizer, gray gas radiation with finite volume solution to the RTE. RTE is radiative transport equation. Computational setup and boundary condition. Figure shows the typical computational domain having dimensions of 300 by 300 160 meter as width, length, height as dimensions. A uniform structure grid is applied in all the directions. The pool diameter considered in the present study are 30 and 50 meters. Mass loss rate per unit area is prescribed as a boundary condition, that is 0.063 kg per meter square second. All sides are set to open and the ground is set to inert. The soot yield and radiative fractions are considered at 0.042 kg per kg and 0.08 respectively. Radiative heat flux to the surrounding is measured by keeping the virtual radiative heat flux meters at a non-dimensional distance y by d equal to 1, 2, 3 and 4. These figures are taken from the present study. These figures show evolution of fire and smoke from the growth to steady state period with respect to time. Grid independency test. The resolution of the flow field of the fire depends on the number of grid cells that span the characteristic diameter d star. The grid resolution is expressed in non-dimensional form, that is R equal to d star by dx. The d star not only represents the impact of the grid size but also the fire size. From the figures, it can be seen that the estimated results show the reasonable accuracy for the range of R values 4 to 16 for the 30 and 50 meter pool phase respectively. Hence, in this study, R equal to 4 and 16 are considered for 30 and 50 meter pool phase respectively, as it offers relatively less simulation time and a reasonable accuracy in the results. Semi-empirical models. As I mentioned, in this work, semi-empirical modeling is also done to estimate the thermal radiation. So the applied models are point source model, Mudan model, Shokri-Baylor correlation, Shokri-Baylor detailed model. Coming to the point source model, this model assumes the flame as a single point source and the flame radiates the thermal energy from the geometric center of the flame equally. This model doesn't consider the atmospheric radiation and it overestimates the near field fire radiation since the geometry of the flame is not taken into account. This model predicts the far field intensity of radiation with reasonable accuracy. Shokri and Baylor correlation. Based on the large poolful experimental data, Shokri and Baylor proposed a simple correlation to calculate the radiative heat flux to an object located on the ground level at a distance of r from the center of the pool fire. The correlation is given in the equation. Coming to the next model, Mudan model. In this model, flame is assumed as a vertical or tilted, that is radiation from the flame is with or without wind. This model also considers the impact of atmospheric transmittivity, configuration factor along with effective emissive power. Shokri and Baylor detailed model. In this model, the flame is assumed as cylindrical black homogeneous radiator with average emissive power. This model also considers the configuration factor between the flame and the receiving object. The configuration factor is the function of diameter of the pool, flame height, and target distance. Resultant discussions. The figure shows the comparison among the previous reported experimental results, numerical simulations, and semi-empirical model results of 30-meter kerosene pool fire. In the figure, x-axis, a non-dimensional distance y by d is shown. In the y-axis, incident heat flux to the surroundings is shown. From the figure, it can be seen that the simulated results are in good agreement with experimental results, and the simulated results are deviated 20% from the experimental results, and the deviation lies within the experimental uncertainty of 30%. Figure also shows the comparison of reported experimental results with semi-empirical models. Among these models, two are simplest and two are detailed models. Point source and Shokri and Baylor correlations are simplest models, and the detailed models are Mudan and Shokri and Baylor detailed model. Point source and Mudan models have better agreement with experimental results. And one more thing, except point source model, all other remaining semi-empirical models are overestimating the thermal radiation from the fire source. The estimation made by the point source model is better than the Mudan model. The deviation of point source and Mudan model from the experimental results are noticed as 0.6 to 19% and 1.3 to 5.8%, 58% respectively. The remaining two models, Shokri and Baylor experimental correlation and detailed models, are overpredicting the thermal radiation from 90 to 145% and 40 to 120% respectively. The reason for overestimation in Shokri and Baylor correlation is because of considering only the pool diameter and length between the source and target. While coming to the Shokri and Baylor detailed model, this model considers the flame as black and homogeneous radiator, but the majority of the radiation comes from the soot and it has a spectral dependency. Resultant discussions are continued. The figure shows the comparison among the previous reported experimental results, numerical simulations, and semi-empirical models results of 50-meter kerosene pool fire. It can be seen from the figure, the simulated results are slightly overpredicted at the near field of the fire, and the simulated far field radiation is well agreed with experimental data with the deviation of 8%. Coming to the semi-empirical models, for both the fire sizes 30 and 50-meter kerosene pool fire, point source model has given better estimation in thermal radiation from fire source. Conclusions. The present study assessed the thermal radiation from 30 and 50-meter open kerosene pool fires and compared the numerical results with various semi-empirical models and previous reported experimental data. The conclusions can be drawn from the present study are as follows. The deviation of simulated results of 30-meter pool fire is 20%, and the deviation lies within the experimental uncertainty of 30%. Coming to the 50-meter pool fire, the deviations at near and far field are 188% and 8% respectively. Coming to the semi-empirical models, among the various semi-empirical models, the point source model shows better agreement with experimental results. In summary, the simulated results are more accurate for semi-empirical models. These are the references cited for the present presentation. Thank you.
Okay. Thank you, Mr. Batina, for this nice presentation.
Thank you, sir.
Let us take a couple of maybe 1 or 2 questions from audience. Any questions from audience? Okay, Mr. Batina, I have one question. So,
yes,
can
sir,
you
please
can you please shed a light on what is this, like, why you are calling it fire dynamic simulator? Is it an open source software?
Yes, sir.
Yes,
sir. It's an open source code.
So, like, how did you use it for your case? So, is it like something like open form or no, some kind of those on like?
It's like an open form software, sir.
So, if you want to implement your own model, can you implement it?
We can edit the source code, but in this work, I have not done any modifications in the source code. I have used as a default models.
As it is.
As it is.
In the maybe 3rd or 4th slides of your presentation, you showed some volume fraction of your fire, right? In a 3-dimensional box.
Volume fraction of the fire, sir.
Was it volume fraction or some kind of
Soot yield, sir. Soot yield.
Soot yield, right?
Soot yield. kg per kg of the fuel.
Okay, sir. So
mass fraction.
How did you calculate it? So you have solved some.
Sir, it is. I have taken that value from reported literature.
So it was not your own simulation results, right? No, or you have used.
Sir, those are given as input to the simulation, and I got these results.
Okay. Understood.
And along with these results, I have compared with semi-empirical models as well.
semi-empirical model and also some experimental data available in the literature, I guess so.
Semi-empirical modeling and numerical simulations are done by my side, and those two results are compared with the reported experimental result.
Okay, okay.
Along with simulation, semi-empirical modeling is also done, and those two results are compared with the experimental results, which are reported in the literature.
Understood, understood. Thank you, thank you, Mr. Batina. So let us thank the speaker again. We will now move on to our final presentation of this session. It is by Mr. Frank Steve.
Yes, sir.
The title of his talk is Introduction Effects of Radiation and Turbulent Natural Convection in Enclosures with Discrete Source Sink. So, Mr. Steve, please.
Professor attendee. I'm Frank Steve, and I would like to open the presentation Interaction Effects of Radiation and Turbulent Natural Convection in Enclosures with Discrete Source and Sink. This work was carried out with the collaboration between and Indira Gandhi Center for Atomic Research. Time is limited. Let me go straight into the presentation. Points of my presentation are the literature survey, followed by the problem definition, the objective, the model validation carried out, the work done, and conclusions derived from the work, the future scope of this work, and the references. However, a vast literature survey has been carried out in order to define the problem statement, and from the detailed literature survey, it is concluded that no research has been carried out on the study of natural convection heat transfer in the turbulent regime for 3 source and 3 positions. Benchmark validation studies have been carried out in air medium by referring the AMP4 and the Cariamis literature. And the definition of my study is to investigate the interaction of surface radiation and turbulent natural convection in enclosures with different source and sink positions. As you can see in the figure, the source is considered on the left wall of the enclosure, while the sink on the right wall. The top, bottom, and the parts of side walls, other than the source and sink, are well insulated. The positions of the source and sink are equidistant between walls and to each other. The change in density with temperature is incorporated using the Bosonisk approximation, and it is mentioned that only a pair of source and sink is considered per study, so you will get 9 possible combinations. The acceleration due to gravity is considered in the negative y direction in order to mimic the real conditions. Natural convection heat transfer and fluid flow in enclosures has been a subject of interest in many diverse fields of applications, namely building and thermal insulation systems, solar engineering applications, effective cooling of electronic components and machineries, and even in nuclear reactor cooling applications. So based on the current state of natural convection investigation, the knowledge gap lies in the calculation of heat transfer by natural convection, and hence the same has been done by me for multiple source sink arrangements in enclosures with involvement of surface radiation. Now it's important to understand how different turbulence models behave to different Prandtl number fluids. Hence, the sensitivity studies are carried out for different commercially available turbulence models and are validated against the available experimental benchmark literatures. Here, the 7 commercially available turbulence scores, namely the K epsilon standard, K epsilon RNG, K epsilon realizable, K omega standard, K omega BSL, the K omega SST, and the 1 equation Spalart-Almaris model available in the Fluent software are compared for air, water, and liquid sodium. And these are the literatures that I have referred. Since my study mainly focuses on air as a medium inside the enclosure, I have presented only the results of air in the coming slides. The enclosure given by AMP4 et al. Literature is a square geometry consisting of air as the medium. The boundary conditions are employed according to the criteria of the literature as shown. A standard 100 by 100 quad mesh was generated for the geometry, and the computational grids are found to be clustered and staggered towards the walls. Here, the local Nusselt number along the horizontal walls is displayed. So the graph displays the experimental results with a dotted line, and these are the numerically generated values. You can clearly infer that the K epsilon models was able to predict a very good closeness compared to the K omega model and the Spalart-Morris model. So hence the K epsilon models can be preferred for these kind of problems. Furthermore, we can see from the next slide, the K epsilon standard model was able to predict the velocity field much more accurate as compared to the other models due to the least deviation from the experimental value. And also performing thorough grid sensitivity analysis, the K epsilon standard model was giving very good desirable results. Hence, the K epsilon standard model can be used for this study. Since my study mainly focuses on the turbulent region, 4 Rayleigh numbers of order 10 power 9 to 10 power 12 are chosen. The source is maintained isothermally at temperature of 343 Kelvin and the sink at 303 Kelvin. The 2D enclosures of length L and depth H are modeled with an aspect ratio of L by H 0.5, 1, 1.5 and 2. The depth H is varied accordingly in order to achieve the desired geometry. For the inclusion of surface radiation, 3 emissivity values, namely 0.3, 0.5 and 0.7 are taken. And since 3 sources and 3 sink positions are considered, a total of 9 possible combinations of source sink positions has been studied. From the model validation studies, that is the sensitivity studies, the K epsilon standard turbulence model is chosen. And for the inclusion of radiation, the surface to surface model available in Fluent is taken from thorough literature study. This is the standard 100 by 100 grid mesh which was employed during the study for different aspect ratios as shown here. Similar to the referred literatures, the computational grids are clustered towards the wall to capture higher gradients close to the wall. The inclusion of radiation with convection plays a crucial role in determining the heat transfer occurring inside the enclosures. So it is essential to understand the radiation effect of natural convection heat transfer. It is important to note that the results presented here are valid only for the boundary conditions used. For the effect of emissivity, the Nusselt number increases linearly for increasing emissivities. It is minimum for all aspect ratios having lower emissivities, and maximum heat transfer occurs for emissivity 0.7 for all aspect ratios. As you can see in the graph, the transfer of heat is higher and much efficient when the position of source is below the sink or when the source and sink are exactly opposite to each other. However, for other cases where the source is at the top and sink at the bottom, a comparatively lower Nusselt number is obtained. Effect of aspect ratio is considered with respect to the Nusselt number for different emissivity values. The maximum Nusselt number is obtained for aspect ratio 0.5 for emissivities 0.3 and 0.5 respectively. However, for emissivity 0.7, we are getting a maximum value at aspect ratio of 1 as seen in the figure. So it is important to note that the source at position 1 and source at sink at position 3 displays the least Nusselt number for all aspect ratios. So upon observing the effect of radiation with emissivity 0.7, the Nusselt number obtained is significantly higher compared to the lower emissivity values. This is the effect of Rayleigh numbers, for which the comparison has been made for Rayleigh numbers of order 10 power 9 to 10 power 12 for different Nusselt numbers and aspect ratios. So for all cases, the Nusselt number is increasing for increasing Rayleigh number for all aspect ratios, and all cases irrespective of their source and sink positions exhibit a very high Nusselt number. However, again the source 1 and sink 3 reports the least Nusselt number for all aspect ratios. So this result can indicate the importance of surface radiation for aiding the heat transfer. The flow as well as the temperature fields have been analyzed using the streamlines and isotherms. The figures show the variation of temperature and flow characteristics for aspect ratio 1 and emissivity 0.5 for different locations of source and sink. The fluid flow is found to be more dominant near the walls as indicated in the streamlines for most source sink positions, and the influence of surface radiation definitely reduces the effect of stratification. The following conclusions can be drawn from this study. The K epsilon standard model along with the surface-to-surface radiation model is an efficient and accurate numerical model which can model the airflow and heat transfer inside enclosures. In my study, it was found that the Nusselt number was increasing linearly for increasing emissivity and maximum heat transfer was occurring for emissivity 0.7 for all aspect ratios. The Nusselt number was also found to increase monotonically for increasing the numbers, and the Nusselt numbers were higher when source is below the sink or when source and sink are placed opposite to each other. The isotherms and streamlines along the walls of the enclosures also indicate the progress of the airflow for different source sink configurations. The numerical correlation was developed between Nusselt number and Rayleigh number for the following condition for Rayleigh numbers of order 10 power 9 to 10 power 12 and for aspect ratios between 0.5 and 2 and for emissivities of 0.3. So this correlation was found to agree with 8% of the numerically generated values and hence can be used to predict the heat transfer coefficient and airflow field in enclosures for different sourcing configurations. This study can be further extended by experimentally verifying the numerical solutions obtained in order to measure the accuracy of the numerical solutions. In addition to altering the positions of source and sink alone, the number of source and sinks used per study can also be varied in order to check for the effectiveness of heat transfer occurring inside the enclosure. These are some of the references which I have used during my study. And I would like to thank you all for your time and would also thank the FMFP Chair Committee for providing me an opportunity to present our study. Thank you.
Thank you. Thank you, Mr. Steve, for this nice presentation. Now
Thank you,
it's
Professor.
time for questions from the audience.
I have one question.
Yes.
Please.
Actually, the problem is very nice and presentation is also very good. But my simple question: you have presented Nusselt number. Nusselt number nothing but a dimensionless number, but the magnitude is in the range of 10 to the power 2, 10 to the power 3. Could you please clarify how you have obtained this?
Actually, what I did was with the Fluent software, I measured the heat flux, and Nusselt number is given by HL by K. So with the help of the heat flux obtained, I calculated the heat transfer coefficient, and with that, I calculated the Nusselt number. But
have you checked with the benchmark result available in the open literature? Experimental
the model validation. Yeah, the model validation done, which was it was an experimental benchmark literature for the Rayleigh number that I have chosen, that is 10 power 9. So this results can be cross verified by comparing the conditions of both the papers. So this was thoroughly checked before performing the study.
No, that is fine. I have just pointed out your result, what you have present. Please cross check that. And one more thing is that you have carried out turbulent analysis, but could you please clarify from practical point of view in a closed cavity, closed ambience, how this kind of turbulent flow can be generated from practical application point of view, and how it could be efficient for application?
Okay, the applications can mainly be used for a diverse field. For my example, I'm considering the enclosure inside a nuclear reactor, for example. So in the nuclear reactor, these temperatures are prevalent inside the building. So the cooling is mainly done by pumps, which are prone to failure. So introducing these kind of natural convection can eliminate the use of the active systems such as pumps. And with the help of passive cooling, we can remove the heat.
So it depends on what kind of application you would like to use. Like if you want the temperature or the heat transfer to occur more, you can alter the positions of the source sensing in such a way that you are able to achieve your desired application.
Actually, this is theoretical explanation what we have given, but in practice, something may be different. Okay, you can see literature more. Thank you for your explanation.
We may take maybe one more question.
Yes, Professor.
Any question? Okay, so I think there are no other questions from audience. Let us thank the speaker, Mr. Steve, for this nice presentation.
Thank you, Professor.
With this presentation, we are concluding the session on computational fluid and gas dynamics. Thank you all for attending the session.
Thank you, Professor Sandeep sir, for conducting this session. So, and thank you all the participants. Hope you enjoyed this session. So now we'll take a lunch break for 1 hour. So we'll assemble here again at 12:30 for a keynote lecture from Professor Ang Bang Wang. So see you at 1:30 then. Thank you.
Thank you.
Tu es trop grand pour comprendre des choses aussi petites. papillon. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Vous allez écrire un instant.
हाँ मैं एक ही
Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
you.
Tu es trop grand pour comprendre des choses aussi petites.
This looks okay.
Hello.
Hello.
Yes, so can you hear us?
Yes.
Okay, so we'll start our presentation at 1:30. We are waiting for the session chair.
Okay. Yeah, how are you? You hear me?
Yeah, we can hear you perfect.
Okay, good. Okay, good. But I heard echo from my
Sorry, sir?
from
Now is it fine, sir?
I'm trying to testing the sharing of my slide.应用程式整个画面。So,
Yes, sir, we can see your screen.
you can see my screen, but I cannot see my screen.
Okay.
I don't know why. I cannot see my screen.
Okay. Can you stop sharing and share only the presentation?
Share only the presentation. Probably I need to ask Hiraya to help me. One moment.
Taiwan.
It should be very easy, but when I share the screen, and then yes, yeah, Hiraya is telling me about testing. Come to here.
Okay, but like this is
screen.
So excuse me, can you see the screen?
No.
No, we cannot see.
No, because I close the sharing again.
This one?
Yes.
Okay. This
one? Yes, sharing.
And
that one.
This one?
Yes.
And where is PowerPoint? This one?
Yes.
So can you see the screen now? Yes, now we can see it is perfect. Okay,
very good.
So this one?
So come back. Yes.
Yeah. So now this is.
So now it's okay.
Yes, sir. It is absolutely fine.
Good.
Okay.
So very good.
Good luck.
Have you heard the talk by Professor Bishop?
Yes, I heard that talk.
Yeah. Okay.
Yes.
You was inside.
Yeah.
Okay. Good. Okay. Yes. Thank you.
Yeah, thank you.
Okay. Good. This camp.前次分享记忆，完整任务就那个很有的事情。 停止分享。Why can I see the screen? Strange.
But sir, we can see your presentation perfectly.
When I share the screen and then I could not see you use the camera, is that it? Correct?
Okay, but from our side, it is perfect, sir.
You could see me?
No, sir, we cannot see you. We can see the presentation.
Only presentation. This means
yes, sir.
Either the image or the presentation.
So the whole presentation.
Okay. And if I intend to switch to the interaction mode?
No, sir, there is no changes as such.
Okay. So I keep this. So shall we have some discussion before the talk start?
Sure, sure.
This means I shall switch back to the interaction mode.
Okay, sir.
Okay, I try this because
sure, sure.
I didn't do that before. So I stopped the sharing mode.
Okay, sir. Yes, sir, it has stopped.
Okay. So I open the.
Now we can see you.
So you can see me now?
Yes, sir.
Okay, good. Then when I close the camera and then I open the sharing.
Yes, sir, we can see the presentation.
I got it. Okay, good. Now I understand how to make this.
Okay, sir.
Okay, so I switch back.
Okay.
Switch back.
Yeah, now the presentation is stopped.
Yes. So now open the camera. Okay.
Yes, sir, now we can see you.
Okay, good. Test complete.
Yeah.
So we have still some time.
Yeah.
But I could not see you.
So we don't have a camera in our desktop. We are using desktop.
Ah, okay.
We'll wait for some more minutes for others to join.
Yeah, we have still time. We have.
Yes, sir.
In my clock, now it's still 7 minutes.
Yeah, yes, sir.
Yeah. And how is normally how is the period for the discussions?
Discussion, it can go up to as much as you want.
Oh, okay. But we have continuing program. So
yes, sir.
Right. So this must be okay.
So it can extend after 2 also. There is no problem.
Excuse me?
You can extend your talk after 2 also. There is no problem as such.
Well, it's better I keep the time. The other program could continue on time.
Yes, sir. Yes, sir.
Mm.
Professor Wang, this is Amadeus.
Hello.
Yeah, good afternoon.
Good afternoon. Yeah.
So let us wait for the session chair. He will be joining soon.
Okay, good. One moment. Okay. So it's a pity I could not see you.
No, here camera is not there.
Okay.
So I thank you for attending the inaugural function.
Oh yeah, thank you. Thank you for your invitation. It's my pleasure. And I have just tested, and it sounds quite straightforward and smooth.
Okay, very good.
Yeah.
Yes. Professor Ramji Repaka has joined.
Oh, good.
So still we have 2-3 minutes. After that, we'll start.
Okay.
Good morning, Professor Wang. Good morning, everyone.
Hello. Yeah. Professor Repaka, how are you?
Yeah, I'm joining 1 minute.
Oh, yeah. It's only a pity I could not see you.
1 minute, 1 minute.
No problem.
Hello.
Hi.
Hi. Hi, Professor Wang.
Oh, yeah, now I see you.
Yeah. Okay, now it's the time 1:30 IST. So we'll start, Professor Wang. Just before that, I would like to give a small introduction about the speaker. Okay, welcome you all to this keynote talk by Professor A.B. Wang from National Taiwan University, Taiwan. He is going to speak on one step further research from the basic fluid mechanics to its modern biomedical applications. Okay, Professor Wang is presently a distinguished professor at National Taiwan University, Taiwan. He served as the director of Optomechatronics Education Research Center and also the chairman of the Display Technology Education Program and counselor of Advisory Office, Minister of Education, Taiwan. He has been honored with the 2013 Distinguished Engineering Professor Award granted by Chinese Institute of Engineers, Taiwan. From 2014 to 2016, he was elected as Vice President of International Society of Coating Science and Technology. His current research interests include advanced coating, 3D printing technology, microfluidic platform for biomedical and industrial applications, optomechatronic systems, and biomimetics. Yeah, Professor Wang, a very warm welcome to you to this conference and for this keynote talk. So please take over, please. Thank you, Professor.
Yeah, thank you, Professor Rapata, and also the invitation of Professor Adela. And now I'm trying to switch the mode to share my slide. Okay, could you see it?
Yes, Professor Wang.
Okay,
yeah,
good.
visible.
Okay, now I start to talk about
yes.
the okay.
Professor Wang, it is 25 minutes, so that we will have 5 minutes for question and answers followed by your talk.
Okay, thank you.
Thank you, Professor. Please go ahead.
It's not far, actually, from Guwahati to Taiwan. Yeah, and NTU is in Taipei, in Node, and the Institute of Applied Mechanics has sometimes at the NTU, and this is my research topics divided by the thermal flow control, microfluidic system, and the applications. And my outline will be the introductions, and the part one will be examples for the experimental setup with better performance. This is especially for the young student of faculties. And the part two will say some interesting the contradictory examples, and in order we could have some progress later on for the deeper understanding of the fluid mechanics research. And then I mentioned some microfluidic platform for the biomedical applications and concluding remarks. So this is the first part. And always for setting up the experimental setup, you need some idea. And it comes from always, if you're setting up, you need to have the idea. And so it is often the best or the key for determining your final outcomes. And the first one I mentioned about the very low speed wind tunnel. Normally we have low speed wind tunnel, but if you want to have very low, this is always if you have a Gaussian distribution. If you have very fast or very, very low, and this is always difficult, but challenging and interesting. And as you see here, this is my first assignment when I come back to NTU, and this is test sections size, and the velocity is about 70 meters per second. But this is a low turbulence wind tunnel. Okay, and so for building this is up, we could make different kinds of application for military or for MAV and so on. But if we come back to see, because this is a low turbulence intensity, so we think about probably this is it's already big, and we build it up a model wind tunnel. This is a scale 1/4, and so we build it up a big tech section, but the velocity, maximum velocity is only 2 meters per second, and the resolution is 0.003 meters per second. And turbulence intensity is quite acceptable, and uniformity is also good. In this case, we could testing the very low speed, and also for us, we're using testing for instance, very traditional flow around a cylinder case. Normally, we testing for the flow around a cylinder. We thinking this is a two-dimensional configuration, and it could not always generate two-dimensional flow. As you see here, this is cylinder and this is flow. Flow around cylinder generate the 3D wave flow, and so people trying to control the edge effect to generate two-dimensional flow. So different kinds of methodology have developed, and this is all made in the water, because for low speed air wind tunnel, we could not have so low speed to generate laminar flow, and therefore we produce our methods here and making this in the air wind tunnel. As you can see here, we're making this wind tunnel and testing it, and this is the traditional method. They're making this. This is wet. Cylinder is here, and you see excellent. The laminar wake could be photographed as shown in this picture. And the next one, I introduce another test facility is reliable test for viscoelastic fluid. And for viscoelastic fluid, this is a fluid material that exhibits both viscous and elastic properties. And if you want to tackle this is very commonly used in the pressure sensitive adhesive. We call it PSA, and this is very, very commonly used in our for instance, our mobile phone or the TV and many displays. And mechanical test is the first step for the property of material. And many testing must be done. And for instance, shear test, pier test, and probe test. There are many advantages, but also have disadvantages. And here I'm talking about the probe test here. This is simple, quick, but the main problem is repeatability and reliability. And for this case, I just show you what is the probe test. Probe test, we have a probe here, and probe contact and compress. This is the force, and this is the time, compressed, and then probe drilled, and then we draw it up, and we have the tension, and then the debonding and the force will decreasing. And in this case, normally there is a big problem is the poor reproducibility. And for this, and we are trying to see what is the problem. For instance, we noticed the surface roughness of the probe will generate the different curves, and the higher the surface roughness decreasing, and you got the higher stress curve. And so the surface roughness must be well controlled for such kind of experiment. And the second one is the incomplete contact. Although we always very carefully, but the misalignment is unavoidable. Even very small contact angle, for instance, here is 0.14 degree, because the thickness of film is very, very thin. And then you got the problem of the non-contact area. Of course, you got the problem of your data that could not be trusted. And also, because you have contact, then you have the trapped air between the contact surface. You see, you have different trapped air, and that will influence our result for the experiment. Based on this, so we need to develop the surface roughness have a well control. So we're using the silicon wafer. This is well controlled. And for the complete contact, then we make it very, very small. And then for the small contact area, of course, you got better contact. And also, to overcome the trapped air, we make the contact. We make an angle, and then purposely we have the time to release the air, as you shown here. You could see very, very good without the air entrainment has been developed. So the problem could be solved just by thinking one step further design, and then you could build up a quite good experimental result afterwards. And the third one I share with you is the meniscus-free interface. This is published in the Physics of Fluid last year. As you see here, the interface of meniscus is unavoidable. And as you can see here, if you have a meniscus, either concave or convex, you have, when light comes, and you have a meniscal interference area. And for this case, it causes a commonly problem. And normally people think, for instance, this black zone and the black interference zone are commonly considered this is unavoidable in the interface experiment. But this problem can be solved by just understanding the dynamic contact angle and just one step for the action, as I will show you afterward. And here you can see this is a water rise in a PMMA tube. And you see, originally you have a big dark zone, but when it's moving, and the dark zone could disappear. And based on this, you can see the PMMA, the static contact angle and advancing contact angle, you could adjust them. Just like here, I show you. Here, this is the interference caused by the meniscus. And the meniscus, if you're testing this, then we're using the dimensionless dynamic contact angle. This is divided by the advancing contact angle. And if this is 1, this means this is the interface start to move. And we're starting from this measuring the contact angle, and we also measuring the interference high HM, and also this the black line. This is the flow rate we control. We give flow, and then we stop the flow, for instance. And then we could see what we got from this. We we have the inflow, and then we relaxation, and then we could also have the outflow, and then we could achieve flow. Okay, I just skip this. We could achieve the flow. We could get no interference meniscus, and this is one thing that could bring into our society when we're making the drop impact. We could get quite good, because normally people very care about the interface, the instant through the interface, but always we have a black zone there. Now we could achieve this just easily. And then we come to the second part. I show you some examples from the contradictory, but from the contradictory, we got a deep understanding in our fluid mechanics research. And so normally we sometimes when we face the inconsistent of the simulation and experiment, and actually we might think this is the bad news, but actually it could also become a good news for you. So the first one I talk you about here is the most common case in the textbook of the separation angle of the flow around a circular cylinder. And as you can see here, very interesting. We combine different kinds of experiment and simulations, but for this is the separation angle. We define the theta s. And theta s, and with the relation to Reynolds number, like you can see, we have two groups in our literature. But actually, people don't show this. When you compare, when you make simulation, and then you compare the consistent one, that is good for your simulations, or reversely. But now you see so big difference. This is not come from your bifurcation, or this not come from the blockage effect or supporting method, what we mentioned before. And so we're starting for the different kinds of experiment. For instance, this is towing tank, and then you could have the measurement, and you could measure your separation angle. And also we're using the different towing tank method. For instance, you have just release the die and to measure the die, and we also making the simulations. Okay, this is a different timing, and you see the oscillation of the separation angle. And furthermore, we're making the soft film method to measure the separation angle, because the soft film is so thin, this could be considered as a two-dimensional flow. And we're using the fast cam to measure instantaneous the separation angles. And then we come to our result. This is our result is a solid circle. You see, actually, because the oscillation, you could got the two groups, and this could matching to the two groups. And so this is actually something that not discussing before. And here is another case, is the dripping drop from a nozzle. This is also very commonly discussed before, and people think this is well known. But this is published also in the last year in the Lung Review by Dr. Tsai. And this is what is this? For the dripping drop, as you can see here, the liquid released from the nozzle, and you have the primary drop, and you have a satellite. And by changing the liquid feeding rate, you from the low to high, and you could have the dripping mode and transition, and then you got the jetting mode. This is well known. But from the predictions models, as you can see, this is already more than 150 years. The text derived the very simple equation. The drop diameter could be predicted by the nozzle diameter, 1/3 power. And this is very simple. Of course, people like to have some more because they're too simple. Then people adding different terms. But actually, this is complicated, but of course, it could improve the accuracy for the predictions. And furthermore, this is in this century and from the Passerans group, they make a simulation and derive these equations also a very simple format. As you can see, from the simple to complicated and switch back to the simple formula. But if you can see this, you see from the relationship, the nozzle diameter increasing, the drop diameter must be increased monotonically. But this seems not the case when we make the experiment. This is the nozzle diameter. This is the drop size. And this is based on the dimensionless outer diameter. This is dimensionless inner diameter, all divided by the capillary length. And you see, in the front part, there's no existing model can correct the predicted. This is all what I mentioned to you, the models. And you see, in the front part, this is the three models seems to better. But here, as you can see, bigger nozzles could be predicted by the inner diameter. And all existing predictions could only partially correct. Okay. And so one part is outer diameter is better, and one part is inner diameter is better. Okay. And so we're testing 100 nozzles, different liquids, different material, and using high image. And now we notice, actually, one thing was not mentioned before. This is weighting. As we could see, this is water through the nozzle. If we define this as a D weight, and you see when it's pinch off, and we define it as DW, it's the weighting diameter. From the weighted region to the weighting diameter, you could see the change could be over 20%, quite big. And the drop diameter could be reduced for large nozzles due to the reduced weighting area. This could be the problem, what we mentioned in the previous slide. And also different relationship between the weight DW and the DI and DO could shown in these three cases. Based on this, we could go back to see what happens and what can we do. And so we notice, actually, we also mixing another characteristic length, except DI and the outer diameters. And here, as you can see here, this is when you have the experiment comes out, the liquid, and then the liquid will weight the nozzle surface. And until one position, we call it a critical diameter, then it's stopped. And no more advancing for the contact line. And for this, then we have derived the critical diameters based on the static pendant drop theory. And this is theoretical result and the experimental result, they matching quite well. And then we analyze by the weighting diameter with respect to the inner diameter. We got the result like this way for for the water PMMA nozzles. And we testing different nano materials and also different fluid. We got the similar trends. And we notice there are critical weighting diameter as the red point. And this is, I skipped this. And the maximal diameter of the DW start here. And then we could classify the dripping drop as the following. This is the inner diameter, and this is the outer diameter. And so you could see we could classify them, and this part less than the critical diameter, this is inner diameter independent region. And above this is the inner diameter dependent region. So that we saw the larger diameter, we are depending on the inner diameter as we show in the experiment result. And also we classify different formula in different regions. And so now when we define our weighting diameter as shown here, weighting diameter, and then we could finally classify the all result in the one curve. And this is the increasing the weighting diameter, then you got the increasing of drop diameter, drop size. So in the last part, I will introducing the microfluidic platform for the biomedical applications. And in our lab, we have developed different kinds of microfluidic. From the beginning, we developed the microfluidic components from the valve, pump, mixer, and flow meter. And then we integrate the component for different applications. And here I introduce the micro-sequential control case here, as I show you here. This is the gravity-actuated microfluidic chip for the point of care urine creatinine detection. And for the testing, always this is for the testing creatinine. And this is what is measured. You need, the first step is for the metering from the 3.6 microliter, 6.60 microliter for different samples. And then you need to mixing them and waiting and mixing again and waiting and then detection. This is a process. And for us, we're developing for the chip and design the valve. And then by using different angles of the chip, we're using the gravity to control the chip opening of the valve. And then when we're testing and compare the clinical methods, as you can see here, this is what we're using. This could be done without any electricity, just the battery inside, and then you could use. And this is a clinical methods. And as you can see here, the result shows quite consistency and within the acceptable errors. This is for the microchip we have designed. And for the second example I show you here is we're using the thin film direct coating method. And in order we could detecting for instance, we're using for the Western blotting. Okay. And what we are discussing about for the biomedical detection, because biomedical fluid have the characters of generally they are very expensive or even very limited. And also they are strictly needed for the precisions. And based on this, we are developing for the Western blotting. Probably not many people knows about the Western blotting, but the process looks like that way. This is a sample preparation and through the electrophoresis, and then we need the transfer and then labeling and making the detection analysis. And because this is based on the antibody antigen interactions, so it could show quite consistent results through the interactions. But there are three key points. The first one is the high consumption of expensive antibodies. As we show, antibodies is very expensive, and long operation time, and many possible errors due to the human errors. So what we developed this part, and I show you here. Actually, this part consists also a lot of process as shown here. But through our process, we introduce our methods here, and we could produce this. The first performance is time saving. As you can see here, this is conventional method result. This is the result from our experiment. And as showing here, the time consumption. This is traditional one. and here is what our method have. And for the cost saving, you can see here, this is a traditional method, and this is our methods. But the consumption for the antigens, this is 0.4 microgram. This is 0.04 microgram. This is 1/10 less. But signal, it shows quite stronger than that. And also, you could see the cost. If you compare the antibody consumption, this is only quite small part, about 1% is consumed. And for the accuracy, that's more the medical operator most concerned. You see, there is some unexpected from the control, but here you got a quite good result. And so you could see here the comparison from the traditional one and the existing product. Our result shows quite good. The consumption rate is most less, and operation time is also the most less. And so I come back to my talk is the education is not the learning of the fact, but the training of the mind to think. This is from Einstein. And so I say education is not only the reading and the writing papers, but the training of the mind to think and do to benefit our society one step further. Hopefully this talk can be a bit helpful or useful for you, especially for the young student or scholar. And I acknowledge many my students, and also like Dr. Dekar is now by me, and for Professor Bispas, and also financial support from the government and the industry. And you're welcome to visit Taiwan and also make research in Taiwan. Thank you for your attention.
Thank you, Professor Wang, for your timely conclusions and then the talk illustrating research profile. Thank you so much for enlightening our audience about your research activities and your research profile. So thank you so much. And we can take a couple of questions before concluding the session. So I request all the participants, if you have any question, you can put the question straight. Yeah, please, Professor Akhilesh Kumar Sahu. So I request the organizers to allow him to speak.
Okay.
Yeah, I can turn it on. I can turn on my mic now.
Okay.
So my question is related to that flow separation around circular cylinder.
Yes.
So you said there are two types of results, right? There were two curves. So maybe I missed it. What is the possible reason behind those two curves?
Okay, I try to go back to the diagram. Okay. So.
Yeah. 32.
Okay.
Slide number 32.
So it actually, for instance, I take the example from the experiment. If you taking different methodology, and as you see here, you have the seeding particle, okay? And so seeding particle will go that way as recorded the track line. As you can see here, some particle was trapped inside the recirculation zone, and the particle will go with the liquid. But as we know, the separation point there, the very last particle comes in. So we normally we follow the particle, and then we say this is what we can see, and then so the particle is, we assume the separation angle is here, okay? But actually here you could not see, this is a dark region, you could not see any particle there. And so, and if this means by these methods, the separation angle is from the front side to this point. So you got higher overestimate for the experiment. And for instance, for the color tracking methods, and if you change the angle of release angle, you have the problem, because the release position is inside the wake, and inside the wake the tracking color could not go upward to the separation point, and so you also overestimate such kind of methods. But if you reversely release the color from the upstream, and then the dye could not go to the downstream, and then you will underestimate the separation angle. So this is from the method of the experiment, and this is simulation. Of course, this is quite accurate simulations. And as you can see here, this is more accurate because this we do not have the edge effect from the both supporting side, and because the film is so thin, and then you got a real two-dimensional flow, as we assume for the cylinder flow. And so, but normally people do not have the possibility to making the soft film to testing the cylinder flow and obtain the separation angle. So we combine different methodology, and then we combine all the simulation. So at the end, we could get the result. And we also got the confidence to say both of them are partially correct. Is it okay for you?
Yeah, okay. Thank you.
Thank you, Professor Wang. And in the best interest, keeping in the times issue, anyone is having any other question, please? Okay. So thank you, Professor Wang, for your nice presentation. And on behalf of FMFP 2020, so we thank you very much for your time and the way you answered the questions. Thank you, thank you so much, Professor.
Okay, thank you. Goodbye, everybody.
Bye. Have a nice day, nice time. So we are concluding the session, this keynote session.
Thank you, Professor Wang, and thank you, Professor Ipaka. Now we move on to our next presentations. So this session will be chaired by Professor Sukumar Pati from NIT Silchar. Over to you, Professor Pati.
Thank you. So please check whether all the presenters have joined or not. There will be 8 presentations in this session. The name of the presenters are as follows: Supro Shankar Kalita.
Yes. Yes, sir.
Okay.
Yes, sir.
The next presenter is Hemant Chandra Bhamsi K.
Present, sir. Present.
Okay, very good. Then the next presenter will be Jadava Mahanand.
Yes, sir. Present, sir.
Okay, thank you. And then Bikram Shukla.
Yes, sir. Present.
Okay. Then Arnam Mukherjee. Arnam Mukherjee have.
Yes, sir. Present, sir.
Okay, very good.
Present, sir.
Good. Then Hitish Gormode.
Yes, sir. Present.
Okay. Then Uritha Rai Choudhury.
Present, sir.
Okay. Then the last presenter is Mudata Srinivas Rao. Okay, that is all the presenters have joined. So as per the guidelines, video presentations will be run one by one, and once the video presentation will over for one presentation, it will be followed by 2 to 3 minutes live interactions. So there will be question answer session. All the audience will ask questions as well as myself will ask. So whoever is the volunteer. One more request, that's all the audience are requested to mute their microphone during the talk. And after the talk, when the question and answer session will be there, please audience are requested to raise their hand to the button that is available in the MS Teams. Okay, so I think Amresh, should we start or?
Okay, sir, we can start now.
Okay, you please start the video presentation of Subra Shankar Kalita and Professor Anup Kumar Das.
Okay, sir.
The paper number 195.
Hello everyone, I am Subra Shankar Kalita. The title of the presentation is Multiple Stable Solutions for Two-Sided Lid-Driven Cavity Using Multigrid Accelerated Stream Function Velocity Formulation. Moving to the overview, I will start with the computational methodology, then I will briefly discuss the strategy and the formulation of the present work, and finally I will move to the results and discussion section. So moving to the computational methodology, I will briefly talk about different solution strategy of Navier-Stokes equations, then the equations of primitive variable method, and then briefly the stream function vorticity method. The Navier-Stokes equation can be solved by different solution approaches. One of the popular approaches is primitive variable or velocity pressure method, popularly known as UVP formulation. The second approach is stream function vorticity method or psi omega formulation. The third one is a relatively new approach known as stream function velocity formulation or biharmonic or psi v formulation. The non-dimensional governing equation of primitive variable or velocity pressure method is as shown in equation 1, 2, and 3. It accurately represents the fluid flow phenomena, but the pressure terms that arise in equation 2 and 3 makes the solution procedure difficult. In order to avoid the pressure terms for two-dimensional problems, the stream function vorticity formulation is widely used. Here I am taking the top lid-driven cavity flow as an example. The non-dimensional steady-state equations for stream function vorticity formulation are as shown in equations 4, 5, and 6. Here at the boundaries, the stream function is constant, but the boundary conditions for omega, that is the vorticity, has to be derived using equation 4. And for its derivation, we need to carry out numerical approximations. For the lid-driven cavity flow example, as I have shown in the previous slide, here the equation 7 is the discretized equation for the stream function, and the equation 8 is the discretized equation for the vorticity. For the lid-driven cavity flow, this is the left, right, bottom, and top boundary conditions for vorticity. Now moving to the discussions of the present work. I will briefly start with the stream function velocity formulation, then I will briefly discuss about the multigrid method. Equation 9 is the biharmonic equation for a Dirichlet type problem. Here f, g, m1, m2 are functions of x and y. Now in order to derive the biharmonic form of stream function velocity formulation, we are revisiting the governing equation of stream function vorticity formulation. Now in equation 12, if we replace the vorticity term from equation 11 and after some simplification, we arrive the biharmonic form of the stream function, which is equation 14. Now in order to discretize the above equation, we are using 9-point compact stencil, and the discretized equation is second order accurate. Equation 15 is the discretized equation for a stream function, and equation 16 and 17 are the discretized equation for the velocities. The details can be found in the paper of Gupta and Kalita. Now moving to the solution procedure of stream function velocity formulation. Most widely, equation 15 or the stream function equation is normally solved using biconjugate gradient stabilized method. And then the velocities 16 and 17, they are solved using tridiagonal matrix algorithm. And since equation 15, 16, 17 are coupled equation, we keep on repeating the above steps till convergence. In the present study, we are using multigrid with Gauss-Seidel smoother to solve the stream function equation, that is equation 15, and the velocity equations 16 and 17 are solved using tridiagonal matrix algorithm, and they are repeated till convergence. Multigrid uses a sequence of grids or levels with increasing fineness, and those grids constantly interact with each other. In the picture, I am showing two grids, one fine and one coarse grid, and in the coarse grid, the distance between two grid points is twice that of the distance between two grid points of a fine grid. The multigrid requires four essential components. One is the sequence of grids from finer to coarser. And next is the intergrid transfer operators. There are two types of intergrid transfer operators. One to transfer the variables and residuals from fine to coarse, known as the restriction operator. And the next one is the transfer of variables from coarse to the fine grid, which is known as the prolongation operator. And also we need fine and coarse grid operators AH and twice H. And we require a smoother, which is an iterative solver, for example, Gauss-Seidel, weighted residual, etc. There are different multigrid cycles. Here I am showing V cycle, W cycle, and full multigrid cycle. In V and W cycle, we initially start in the fine grid, and we gradually move down to the coarse grid, and then we move up to the fine grid. But in FMG cycle, we initially start in the coarsest grid, then we gradually move up to the finest one. This is the algorithm of multigrid V cycle in its recursive form. At the finest level, we solve the equation in the form AU is equal to F with some initial guess. Here it is denoted as VH. And we solve, we give only small number of iterations to solve it, and we keep it less than equal to 3. It is called pre-smooth, and here it is denoted as U1. Then we calculate the residual, which is F minus of AV, and this residual is transferred to the next coarser level using this restriction operator, which is IH to twice H. Then at the next coarser level, we initialize the variable to 0, and we invoke the, we call the same function recursively. When the variable is solved at the coarsest level, we correct it back, we prolong it back using the, this prolongation operator, I twice H to H, and it is added to the solution variable at the finer level to correct it. And after its correction, we give another small number of iterations known as post mode. We also keep it small, less than equal to 3, and here it is denoted as U2. So moving to the results and discussion section. This is a computational domain for two-dimensional non-facing lid-driven cavity. Here, the top wall is moving from left to right with unit velocity, and the left wall is moving from top to bottom with unit velocity. And these are the solution parameters. We are using one multigrid V cycle to solve the stream function equation, equation 15. And we are using 5 multigrid levels, and the finest grid is 129 by 129, and the coarsest grid is 9 by 9. Gauss-Seidel is used as multigrid smoother. At the coarsest grid, we are giving 50 constant iterations, and we have found that this particular parameters yield the fastest result. The pre-smooth and post-smooth are set as 1. The velocities are solved using tridiagonal matrix algorithm. And this is the system where the simulation is being run. This is streamline contours for Reynolds number 100 and Reynolds number 500. This is the streamline for Reynolds number 1000, and after Reynolds number 1073, which is a critical Reynolds number, we get 3 different solutions for each Reynolds number. Here I am showing one asymmetric result for Reynolds number 1075. And this is the asymmetric streamline contour for Reynolds number 1500. And this is the symmetric case for Reynolds number 2000. This is the first asymmetric streamline contour for Reynolds number 2000, and this is the second asymmetric streamline contour for Reynolds number 2000. This is the comparison table with the published result of Wahba. Here I am showing the left primary vortex value and right primary vortex value for the 3 different solutions. for Reynolds number 2000. And from the table, it can be seen that our result is in good agreement with the published result of WAHBA. And we are using 129 by 129 grid, and WAHBA used 200 by 200 grid points. This table shows the time taken by the multigrid method for the two-sided lead-driven cavity flow at various Reynolds number. In the table, we can see the time taken by multigrid for Reynolds number 100 is 0.76, for 500 it is 1.35, for 1000 it is 12.3, 1500 it's 13 seconds, and for 2000 it's 18.17 seconds, which is very fast. If we compare with biconjugate gradient, we can see BICC step for Reynolds number 100 takes 58 seconds, and for 500 it takes 66 seconds. For Reynolds number 1075, the time taken is greater than the other Reynolds number values. It is because 1075 is near the critical Reynolds number 1073, and after 1073, we start to get multiple solution for different Reynolds numbers. Moving to the summary and conclusions, we have successfully taken the advantages of fourth order Brownian form of Navier-Stokes equation and its 9-point compact discretization. And we have accelerated the stream function velocity formulation with the help of multigrid and successfully obtained multiple solutions for non-facing two-sided lead-driven cavity. And when comparing with biconjugate gradient stabilized method, we have found out that multigrid performs very fast. And the results obtained in the study is in good agreement with the published results of WAHBA. And coupling with multigrid, we got a computational procedure which is not only accurate, but also time competitive. Thank you.
So, thank you, Subra Shankar Kalita, for your nice presentations. And also, congratulations for as the paper has been selected and now you have presented. So now it's time for the session, open the session for question answering. So I request all the audience. So if you have any question, please raise your hands, and then the volunteer, I request the volunteer, please allow them so that they can raise some questions. So the audience. Any question from audience? Okay, I have a couple of questions.
Yes, sir.
Yeah. So bro, so first of all, could you explain what are the limitations of that stream function vorticity formulation?
So vorticity,
or alternatively, you can say what are the major assumptions that you have taken while formulating the stream function vorticity method. That is basically you have solved three equations, continuity and the two momentum equations.
Yes, sir.
So what are the assumptions that you have, major assumptions that you have considered?
Sir, is it vorticity or stream function velocity formulation?
Yeah.
Okay.
So just that means that for any kind of flow, whether it can be formulated or not, just like for incompressible flow, for compressible flow, for two-dimensional, just you have solved only the two momentum equations. You have not considered the three momentum equations for whether it can be applied when the flow is three-dimensional, flow is compressible or not.
Yes, sir. Actually, for two-dimensional problem, it is easy to apply. But I have seen some papers where the authors have extended it to three-dimensional flow. So that part I haven't gone deep on that. Normally for stream function vorticity formulation also, since we vorticity is defined for normal cases 2-dimensional. So that is also the limitation of both stream function vorticity and stream function velocity formulations. In normal cases, it's restricted to 2-dimensional. But sir, I haven't thoroughly gone through how to extend it to 3-dimensional problems, sir.
And basically, just try to realize that here what you have done, whatever the pressure gradient term that appears on the right hand side of the momentum equation, simply through cross derivative of the momentum and y momentum equations, we have eliminated the pressure gradient terms.
Yes, sir.
But if it is a 3-dimensional, then it becomes complicated. Okay.
Yes, sir.
And what's about if the flow is compressible instead of, you have considered the incompressible flow? Am I right?
Yes, sir.
So what happens if the flow is compressible? Okay, so another question is that you please check, is there any influence on the dimension of the cavity? Just you have considered the dimensionless form of the governing differential equations, just like on the right hand side 1 by Re, then the diffusive terms is there. So is there any influence of the dimension of the cavity? That means simply if I take 1 centimeter by 1 centimeter, or if I take 1 meter by 1 meter, or if I take 100 meter by 100 meter, that's the dimension of the cavity. Is there any influence on the result? Keeping the Reynolds, maybe keeping the Reynolds number same.
Normally we solve using a non-dimensional. We can convert the problems to non-dimensional case.
Yeah, I understand. I understand, Subro. First of all, let me clear you. We are not physicists. We are engineers. So without the real dimensions, so I believe that you will realize that without the applications, whatever, fine, algorithm is fine. So, but it should have some applications, some real applications, where the dimensions of the cavities, the physical dimension of the cavities should have some real value. Am I right?
Yes, sir.
So at least in future you take just look into this matter. So if the dimensions of the cavity has changed, so what is the influence of the dimension of the cavity on the results that you are reported? Fine.
Okay, sir. Thank you.
And one more thing that you have mentioned that you got some critical Reynolds number like the 1073. Am I right?
Yes, actually that has been reported by Wahba in his paper that after 1073 we get for this particular configuration 3 multiple solutions. So we try to produce that. Yes.
Oh, that's fine. My question is that's 1073 fine. So, but what is the physical significance with that Reynolds number? That's since we know that's the critical Reynolds number. Whenever you consider flow through pipes or something, internal flow, there is some physical implications. So what is the physical implications of the critical Reynolds number as far as the lead-driven cavity is concerned? That's a 1073 if it is less than 1073 and if it is greater than 1073. Okay, fine. That's you please check. So otherwise
so here is like that with the same set of initial conditions and boundary conditions. If we try to the sweeping directions, if we try to reverse it, or like normally in sweeping directions, if we started from the bottom left corner and we lexicographically move up to the top right, then we get one asymmetric solution. And if we start with the top right and we come down, so it's basically with the same flow structure, with the same boundary conditions, those two stable solutions are stable. Also, the symmetric solutions are also stable. So he tried to find out the criteria after which numerically we tend to get the stable solutions.
Fine, so below, stable solution that again, as you have shown, one is the solution is symmetric, another is the solution is asymmetric. Am I right?
Yes, sir. Yes, sir. Two asymmetric and one symmetric. Yeah.
Yeah, although for both the cases the solutions are stable, but maybe it is on the basis of whether the stable solution, whether it is symmetric or asymmetric. Okay, so but anyhow, but from my side, it's very nice presentations, and once again thank you to you. And if is there any questions from the audience, please 1 or 2 questions we may take. And if there is no questions, the volunteer, who is the volunteer, please?
Yes, sir. We'll go to the next video.
Yeah. What's your name? What's your name, please?
Shantanu Das.
Shantanu Das. Okay, Shantanu. And once again, thank you, Subro, for your nice presentations.
Thank you, sir.
So please proceed to the next. Please verify whether Hemant is available or not right now.
Sir, I am present.
Okay, so once the presentation is over, the video, whatever you have shared, then we'll again start the question answering session. For the timing, please mute all of you. Okay. Shantanu, please start the next presentation.
Greetings, everyone. I am Hemant Chandramamsi. I will now present our work on high-order differential equation-based wall distance solver. I worked on this project with Professor Nagbhushan Rao Varlamani, and we are from Department of Aerospace Engineering, IIT Madras. The outline of the presentation is like this. Firstly, I will give a brief introduction about what is wall distance and why do we need to calculate it. Then I will describe the methods available in the literature to compute wall distances. It will be followed by a brief description of numerical setup that was used to build this solver. Then I will present the results. Firstly, I will present the results corresponding to the baseline solver, which employs the commonly used upwin scheme. Then I will present the results corresponding to the enhanced solver, which uses higher order schemes. I will highlight the benefits of using higher order schemes in the place of upwin scheme using a test case. Results corresponding to the unsteady cases will also be presented, and finally I will close the presentation with concluding remarks. First of all, let's see what is wall distance and why do we need to calculate it. Wall distance is basically the location's minimum distance to a wall. For example, in this image, this is a wall and this is a point somewhere above it. The wall distance at this point is the shortest possible distance to this wall, which in this case is a perpendicular distance. Wall distance has several applications. It is used in turbulence modeling techniques such as RANS models and detached eddy simulations. In the adjacent image, we can see the wall distance field around a wing and body of an aircraft. Wall distance is also necessary in peripheral flow applications like multi-phase flow. It also comes up in computer-aided design and automated machine. Now let's look at the methods to find wall distance. Well, there are two classes of methods available to find wall distance: search-based methods and differential equation-based methods. Euclidean distance and projection approaches are two main search-based methods to find wall distances. They are very crude. It basically consists of computing wall distance at all nodes in the computational domain to all nodes on the walls, and then searching the minimum among all those values. It's very inefficient process and leads to a lot of inaccuracy, particularly when the grids are non-orthogonal or unstructured, which in many cases would be true. On the other hand, differential equation-based methods are great. They provide fast and accurate results. Here we find wall distance by solving a differential equation. There are three classes of differential equations available in literature. The first one is the Eikenholt equation. It's the exact governing equation for the wall distance. It's important to note that it's a nonlinear hyperbolic equation. Solving this would require artificial dissipation in some form. Otherwise, it will lead to convergence issues. The second one is the Poisson equation method. It's an approximate equation to find wall distances. Solving this equation is numerically quite easy and the convergence is quite stable. The third type is Hamilton-Jacobi equation. It's basically a hybrid between Eikenholt and Poisson equation. It's very similar to the Eikenholt equation if you observe, but it consists of an additional Laplacian term on the RHS to enhance stability, which also acts as a source of error. Inclusion of this term is just the price we pay to get stability. Now let's briefly look into the numerical setup. We have used finite difference schemes for discretization. All the governing equations are transformed into generalized curvilinear coordinates and then solved. For example, Eikenholt equation. The equation is expanded and the individual terms in it are rewritten as the derivatives of psi, eta and zeta, which are the coordinate directions in the curvilinear space. To estimate these derivative terms, commonly upwin schemes are used, because upwin schemes are dissipative and they can efficiently handle the nonlinearity present in the governing equations. But upwin schemes have downsides too. They are difficult to implement, especially in the context of curvilinear coordinates, and they are relatively slow. Our idea is to why not use high order schemes with some dissipation through filtering instead of upwin schemes, because high order schemes are widely used in CFD solvers these days and they are simple to implement and faster than upwin schemes. That's where the aim of this project was established. So to broadly give a picture of this project, the aim is to build a simple to implement, fast, stable and accurate wall distance solver using high order schemes, which can be incorporated into the modern day CFD solvers easily. So there are two things here, the baseline solver and the enhanced solver. For spatial discretization, the baseline solver uses first order upwind scheme and the enhanced solver uses explicit and compact higher order schemes. Here E2 and E4 stand for explicit second and fourth order schemes, and C4 and C6 stand for compact fourth and sixth order schemes. 10th order filter was used to suppress the non-physical high frequency oscillations that were originating from the non-linearity present in the governing equations. And at the boundaries, distillate and Nyman boundary conditions are available in the solver. To converge towards the final solution, we have used pseudo time iterations. For that, a pseudo time derivative was added to the LHS of the governing equations, and the resulting equations were solved using Ranjagooda fourth order time integration. And to handle unsteady cases where geometry inside the domain is moving, for example, the moving cube that you are seeing, we have simply computed wall distance at each instant separately by feeding the geometry at that instant into the solver. Basically, there is no physical time involved in the governing equations, but the physical time is only present in the algorithm. Moving on to the results, firstly I will present the validation of baseline solver using two test cases. The first one is two-dimensional box case. It's basically a square domain surrounded by four walls. The wall distance contour for this case using Eikenal equation is like this, and for Hamilton-Jacobi it's like this, and for Poisson equation it's like this. As expected, lower values at the walls and high values at the center can be clearly seen in all these three contours. Since this is a canonical case, we were able to analytically find the exact solution, and we have compared that exact solution with these three computed solutions, and we got error contours. These are error contour for Eikenal, and these for Hamilton-Jacobi, and these for Poisson equation. If you see the error contour for Eikenal equation, it looks very bluish, which means the errors are very low. The error contour for Hamilton-Jacobi equation are not as good as Eikenal equation, but the errors are pretty low, especially near the walls. Even for Poisson equation, errors close to the wall are low, but errors rose very quickly as we move away from the walls. At this point, it's important to note that for most of the turbulence modeling strategies, it's sufficient to have accurate wall distance close to the walls where the viscous effects are dominant. In which case, these two Hamilton-Jacobi and Poisson equation solutions are acceptable. Now, when we have plotted wall distance along these mid-vertical dashed lines, we got this. The black line hiding under is the exact solution. The blue dots corresponding to the Eikenal equation can be seen to coincide with the exact solution very well. The next best solution is from Hamilton-Jacobi in green, and Poisson equation solution stands to be least accurate. Moving on to the next test case, we have tried to compute wall distance between these complex geometries engraved into the domain. These are the results we got for Eikenal equation, Hamilton-Jacobi equation, and Poisson equation. This particular results demonstrates the robustness and performance of the solver in treating complex geometries. Now, having validated the baseline solver using upwind schemes, we have attempted to solve the same differential equations with high order schemes. Now, let's see those results. Let's first see the effect of high order schemes on Hamilton-Jacobi equation solution. The two-dimensional box case is considered here again. Wall distance and the wall distance error along the mid-vertical line passing through the domain are shown here. At the center, around y by L reference is equal to 5, the wall distance estimate corresponding to the high order scheme is a bit close to the exact solution in comparison to the upwind scheme solution. And from the error plot shown on the right, it can be seen that the errors corresponding to the high order schemes are lower than the errors corresponding to the upwind scheme at the edges as well. To quantify these errors, RMS errors were computed. They are listed in this table. Here the RMS errors corresponding to the upwind scheme is in the order of 10 power minus 3. But whereas the RMS errors corresponding to the high order schemes is of the order of 10 power minus 4, which is one order lower. So high order schemes are more accurate. And one more important benefit that we got out from the high order schemes is the economy in computational time. The CPU time elapsed for 100 iterations for upwind scheme is around 5.78. But whereas for explicit higher order schemes, it's 1.68. For compact, it's 2.82. Now let's look at the effect of high order schemes on the Eikenal equation solution. These are the wall distance and the wall distance error plots along the mid-vertical line passing through the domain. In the first plot, it can be seen that the wall distance values corresponding to all the schemes are all coinciding with each other. But if you look at the error plot shown on the right, we can point out that the Eikenal equation solution has suffered with dispersion errors despite using the 10th order filter, because of which accuracy of the solution is lost. Unlike the Hamilton-Jacobi equation solution shown in the previous slide, the RMS errors are higher in comparison to the upwind scheme here. On a brighter side, the CPU time consumed by the high order schemes is still lower in comparison to the upwind scheme. 3.33 minutes for the upwind scheme and 1.65 and 2.78 minutes for high order schemes. The solver was also extended to compute wall distances in unsteady geometrical environments. Let's see some of those results. Firstly, the oscillating cube case. In this case, there is a cube present inside the domain which sinusoidally oscillates with time according to this equation. Explicit fourth order scheme was used to simulate this case. And this is how the wall distance varies with time according to various differential equations when the cube is moving inside the computational domain. Now let's track the Hamilton-Jacobi wall distance at this probe location. When the wall distance at this location is plotted with time, it looked something like this. The solution can be seen to be coinciding pretty well with the exact solution here. A similar analysis has also been done on the bouncing cube test case. In this case, a cube is dropped from the center of the domain and it falls freely due to gravity accelerating at 9.81 meter per second square. When it collides with the bottom surface, it loses parts of its kinetic energy and bounces back to a lesser height. When the wall distance at this probe location is tracked with respect to time, the following plot was obtained. It's very well coinciding with the exact solution except for the part that was circled there. This is due to the Hamilton-Jacobi nature of the equation. Hamilton-Jacobi equation always underpredicts the wall distance away from the walls. And that's exactly what we are seeing here. We have also simulated the wall distance evolution inside a solid rocket motor. This is an image of a real solid rocket motor. Basically, there is a combustion happening at the core of the motor due to the burning of the solid propellant, because of which the grain burns and the grain surface moves towards the casing. So the wall distance evolution inside the combustion chamber is simulated here. The wall distance evolution, it looks something like this. This will be useful when studying fluid flow inside the domain using RANs or detached eddy simulations. To summarize the presentation, we have developed a high order differential equation based wall distance solver. We have validated the baseline solver which uses upwind schemes on simple and complex geometries. Then we have demonstrated the potential use of high order schemes in solving wall distance differential equations. It was observed that while solving the Hamilton-Jacobi equation, high order schemes outperform the upwind schemes in terms of both accuracy and speed. But while solving the Eikenal equation, the high order schemes have suffered with dispersion errors due to Gibbs phenomena. The solver has also been extended to handle unsteady cases. The unsteady solver has been validated with oscillating cube, bouncing cube, and solid rocket motor test cases. Thanks to the organizing committee of FMFP for this great opportunity.
So thank you, Hemant, for your nice presentation. Yeah. Now it is open for the question answering session. So again, I request all the audience, please, if you have any question, please ask. Please raise your hands, and so that the volunteer will allow you to ask the questions. Any question from audience? Okay, I have a couple of questions. Okay.
Yes, sir.
So you have mentioned you have considered three equations. Am I right? One is the Poisson equations and
Eikenal equation. Yeah.
And you have mentioned so one is the exact equation, another is the approximate equations, another is the hybrid equations.
Yes.
Am I right?
Yes.
So on what basis you have mentioned those equations, whether it is an exact or approximate or the hybrid equations?
So Eikenal equation. So for wall distance, Eikenal equation is the exact solution. That's the exact governing equation. If we get the exact solution for that, there will be no error in that solution. But these other two are not exact equations. The Eikenal equation has a particular derivation, which I didn't show it in this presentation. If we go through that derivation, we can see that it's an exact equation.
No, what my question is the prior to get the result, is it possible to claim that whether those equations are exact or approximate or hybrid, or after getting the solution, that you can claim whether the equation is exact or approximate?
Yes, sir, that is an exact equation. Eikenal equation is the exact equation for finding wall distance.
Okay,
and it is documented.
Okay. So now for the solver that you have considered there are two types of boundary conditions, if I am not wrong. One is the Dirichlet boundary condition, another is the Neumann boundary condition.
Yeah.
Yes.
Yes.
There are several applications in the context of the fluid dynamics, where many times we have used a combination of Dirichlet and Neumann, whatever the mixed or Robin boundary conditions. Just like if you consider at the wall, instead of no slip boundary condition, there is a slip boundary conditions, where the velocity itself is expressed in terms of the gradient of the velocity.
Yeah, actually, finding wall distance is not relevant to the fluid flow. And wall distance is not only an application for CFD, it's also applicable in CAD and mesh generation. So your question is, what is your question?
My question is, you have used two type of boundary condition. One is the Dirichlet and Neumann. Whatever solver that you have developed or used. So can it be extrapolated if we use, instead of Dirichlet and Neumann, if we use the mixed boundary conditions at the wall, can it be extrapolated?
We should not use mixed boundary condition. We should always use Dirichlet boundary condition if we are finding wall distance. There is no concept of mixed boundary condition. It's always a Dirichlet boundary condition. Wall distance will always be equal to 0 at the wall.
No, just you have mentioned that whenever you consider the range or something, that's in the context of the turbulent flow over some surface.
Yeah.
Yeah.
Even though we are, no matter what boundary condition that we are giving in the CFD simulation near the wall, it's always Dirichlet boundary condition when it comes to finding wall distance.
Okay. And then you have mentioned that there are the two schemes. One is the higher order scheme, another is the compact higher order scheme. And what basis you claim whether one scheme is higher order or one scheme is compact higher order?
So here the higher order, in the sense the upwind scheme is first order, and the second, fourth, and sixth order schemes are, I'm calling them as higher order schemes. And in higher order schemes there are explicit and compact. Explicit actually uses more number of grid points than compact schemes to attain same level of discretization error. So on that basis, we are calling the schemes, differentiating the schemes between explicit and compact.
No, is it something related to the whatever the governing differential equation is there? So whenever we go for the discretization of those governing differential equations, is there any difference when you consider it's a compact higher order and when you consider only higher order scheme? Maybe the higher order of fourth order accuracy or the sixth order accuracy, whatever may be the accuracy level, is it related to any discretization?
Yes, sir. It is related to discretizing, how we are discretizing the mesh.
Yeah.
So in compact schemes, we are making use of less points to attain high level of accuracy. That's why it is compact. But in explicit,
how do we assure that whether it is a more number of grid point or less number of grid point? I think that's it comes from the concept of the discretization.
Concept of, yes, exactly.
Yeah,
so all these schemes are already well documented in a paper that I have referred in my paper. It's from this, but so on those schemes, this solver has been built.
Let me add to Hemant's point. This is Nagabhushan. I'm a co-author of that paper. It's a well-known fact that, like if you are using an explicit scheme, the derivative at a given point, if you are differentiating any function at that given point, it is related to the functional values around that point. Simply the functional values around that point. Whereas in compact differencing, the derivative at that given point is also dependent on the derivatives at other points. So it's a coupled equation which you will come up with. You will have to solve a tridiagonal matrix to actually solve that. So these are the two, well-known schemes, right? So that is what has been implemented. And because we solved the TDMA, if you notice the time as well, when compared to explicit, explicit was taking 1.6 seconds for say 100 iterations, whereas compact was taking slightly longer time because it's a coupled equation, right?
Yeah.
Hope that clarifies.
Yeah, at least that's why whatever I intended to know from him. And thank you for the answer. At least the audience should get benefited from it. So at least they should understand what is the higher order, what is the complex higher order scheme.
Sure.
And thank you for clarifications. Thank you, Hemant and Professor Nagavasan Rao. Am I right?
Yes, sir. Yeah, that's right.
Yeah. And thank you for your presentation. And this is So the Santanu, now we should move to the next presentation. Before that, you please whether Edava Mahanand is available or not.
Yes, sir. Yes, sir. Present.
Yeah, you are available. So Santanu, please run the presentation of paper number 65.
Hello, all respected members. I am Jadab Mahanan from National Institute of Technology, Rourkela. I am going to present my conference seminar on numerical investigation of transverse inverted T-section rebref and solar air heater. These are the outlines of my presentation. Introduction. Increase in energy demand, depletion of fossil fuels, anthropogenic climate change, and explosive population growth. All these problems are propelling the current scientists to focus on renewable energy sources. Solar air heater is one of the most effective, efficient, and practical mechanical device that has been used to convert the solar energy into useful heat energy. Generally, the conventional solar air heater has poor thermal efficiency due to the lower thermal conductivity of the air. So, use of artificial roughness on the surface of the observer plate in the form of wire ribs, fins of different shape, size, and orientation is one of the most effective way to enhance the heat transfer through the solar air heater. These are the some of the literature review I have gone through. The objective of the present analysis is thermohydraulic performance evaluation for an inverted T-rebref and solar air heater. Computational details. The physical problem consists of a rectangular solar air heater duct of length, height, and width of 640 mm, 20 mm, and 100 mm respectively. The ratio of the width to height of the duct is considered as 5, which is a large quantity. Therefore, it is safe to neglect the changes in the flow quantities along the width of the duct. So, the three-dimensional flow situation is converted into the two-dimensional flow situation. The length of the test section is considered as 280 mm, and the length of the entry section and exit sections are decided as per the SRA standard given here. The observer plate is placed with the arrangement of transverse inverted T-ribs on this surface and is imposed with a constant and uniform heat flux of 1000 watt per meter square. This table presents the geometrical and operating parameters for the computational analysis. These are the assumptions considered for the present analysis, and this table represents the thermophysical properties of working fluid and observer plate. Mesh generation. Non-uniform structure grids with fine meshing near the wall surfaces have been considered for the present analysis. Grid independence test for the present analysis has been done by varying the number of computational cells in 5 steps. From the table, it has been observed that after 3,90,986 number of cells, the variation in the Nusselt number and friction factor is less than 1%. So, domain with 3,90,986 number of cells is used to predict the numerical results of the present analysis. Governing equation. The flow phenomenon in an artificially roughened solar air heater duct is governed by the steady two-dimensional form of continuity equation, the time-independent incompressible Navier-Stokes equation called momentum equation, and the energy equation. And now transport equations used for the RNG K-epsilon model to determine the turbulent kinetic energy and the energy dissipation rate for the computational analysis are given in these equations. Boundary condition. The inlet of the fluid domain is specified by a uniform velocity and it is calculated from the respective Reynolds number. No slip condition for the velocity in solid surfaces is assumed. The observer plate is subjected to a constant and uniform heat flux of 1000 watt per meter square. At the exit, the outlet boundary condition is specified by a fixed atmospheric pressure, that is 1.043 into 10 to the power 5 Pascal, and the other walls of the fluid domain are assumed to be adiabatic. Solution method. Finite volume method has been adopted for the discretization of the fluid domain. Second order of wind scheme has been applied to handle the convective terms involved in momentum and energy equations. Central difference scheme is used for the diffusive terms. Simple algorithm, that is semi-implicit method for pressure linked equation, has been used to coupling the pressure and velocity. Absolute convergence criteria of 10 to the power minus 5 for the residuals of continuity equation and 10 to the power minus 6 for the residuals of other governing equations have been adopted for the numerical simulation. There are some well-established correlations such as Ditus-Boulter correlation, Blasius correlation, used for the calculation of the Nusselt number and friction factor for the smooth duct. The Nusselt number and friction factor for the roughened duct can be obtained by using these relations. The provision of the transverse inverted T-ribs on the surface of the observer plate significantly enhances the heat transfer rate by creating turbulence in the flow. At the same time, an increase in the friction losses also observed. So, a parameter which is a cumulative function of Nusselt number and friction factor used to evaluate the thermal performance of the solar radiator called thermohydraulic performance parameter, and which is equal to the Nusselt number enhancement ratio to the friction factor enhancement ratio to the power 1/3. The selection of the turbulence model for the present study has been done by comparing the Nusselt number obtained from the various turbulence model with that of the available Ditus-Boulter correlation. From the figure, it has been observed that less than 10% variation in the Nusselt number is achieved in RNG Kapsalon model with that of the Ditus-Boulter correlation. So in the present study, RNG Kapsalon model is selected to simulate the fluid domain on the basis of its closer results to the Ditus-Boulter correlation. Heat transfer analysis. The arrangement of transverse inverted T-ribs as the roughness element on the surface of the observer plate causes increase in the heat transfer through the solar radiator. This figure shows the effect of Reynolds number on average Nusselt number for the inverted T-ribs with relative roughness pitch of 7.14 and relative roughness height of 0.042. From the figure, it has been observed that the enhancement in the heat transfer due to the inverted T-ribs is much greater than that of the smooth duct. It is also observed that the average Nusselt number increases with increase in the Reynolds number. Increase in the Reynolds number suppresses the thickness of the viscous sublayer. The increased turbulence generated due to the increase in velocity create vortices around the top surface of the inverted T-ribs, which transfer heat from the hot observer surface to core cold fluid. The arrangement of the inverted T-ribs on the surface of the observer plate disturbs the development of the boundary layer. This causes increase in the turbulent kinetic energy and turbulent intensity, which ensure the enhancement in the heat transfer through the solar radiator. This figure shows the effect of Reynolds number on the average friction factor for the relative roughness pitch of 7.14 and relative roughness height of 0.042. The provision of the transverse inverted T-ribs as the roughness element on this observer surface create obstruction in the flow. This results in high pressure drop due to the boundary layer separation and reattachment. From the figure, it has also been observed that the friction losses encountered in the roughened duct is higher than that of the smooth one. It has also been noticed that the friction factor decreases with increase in the Reynolds number. Higher velocity causes suppression of the viscous sublayer and hence the friction factor decreases. Thermohydraulic performance analysis. The presence of transverse inverted T-ribs on the surface of the observer plate interrupt the viscous sublayer due to the flow separation and reattachment. This reduction in the thermal resistance in the flow increases the heat transfer through the solar aerator. However, the use of the artificial roughness also increases the pressure drop, which in turn leads to a greater pumping power requirement. So to get a maximum heat transfer with minimum penalty of pumping power, the turbulence must be created in the region that is very close to the surface of the observer plate. A parameter defined by Webb and Eckert, known as thermohydraulic performance parameter or THPP, which provides the overall performance of the system under consideration. The value of the THPP more than 1 indicates the usefulness of the artificial roughness on the surface of the observer plate. From this figure, it has been observed that a maximum thermohydraulic performance parameter of 1.87 is achieved for the relative roughness pitch of 7.14 and relative roughness height of 0.042 for the Reynolds number of 15,000. Conclusions. RNG Kapsalon model agrees well with the Ditus-Boulter equation for a smooth solar aerator as compared to the other turbulence model. A maximum thermohydraulic performance parameter of 1.87 is achieved using the transverse inverted T-ribs as the roughness element on the surface of the observer plate with relative roughness pitch of 7.14 and relative roughness height of 0.042 with a Reynolds number of 15,000. For higher values of Reynolds number, it is observed that the Nusselt number for the solar aerator with transverse inverted T-shaped ribs is moderately higher than that of the semicircular and square ribs. These are the references. Thank you.
Thank you, Jadab Manand, for your nice presentations. So now it is open for question answering session. So I request all the audience, whoever is present over here, please ask whatever doubt or whatever question that is there in your mind. I believe that's you have some questions, but you are not. It is just feel free to ask the questions. So otherwise, whatever is the objective of doing this conference, that will not be successful until and unless you have asked the question. Anyone?
Hello.
Yeah, yeah.
Good afternoon, sir.
Good afternoon. Please ask.
Yeah, actually, heat flux is assumed as a constant, like 1000 watt per meter square or kilowatt per meter square. I have not observed, sorry. And like, which place you have considered? Means, have you taken experimental results from anywhere in India or other countries?
There are so many experiments have already been done in India also, sir. There are so many papers. Actually,
okay, in which region? Means northeast region, it's like a low heat flux we used to get, and it depends on the place. That's why in which area you are considered.
Obviously, and there are
what's Sarij asking, that's how you have selected some physical dimensions of the computational domain. Similarly, you have taken 1000 watt per meter square as a heat flux. So what is the basis of selection of those? So you have not mentioned any reference of whenever you have considered or whenever you have selected that 1000 watt per meter square. Similarly, the physical dimension of the computational domain. So what is the basis for selection of that 1000 watt per meter square as the heat flux or the other physical dimension of the computational domain? Am I right, Mr. Rao?
Yes, sir.
Yes, actually, what happens in many experimental works, the intensity of the solar is varying from nearly 9,900 to 1100. That's why in many numerical papers also they are considering 1000 as the constant solar intensity to do numerical works.
So that's fine, but definitely it varies from the location to location. That means even from country to country, from within a country for different locations, different let's say whatever the northeast, whatever is the south, or whatever the north India, it may vary.
Yes, sir. It also varies, sir. Actually, it varies. But sir, the thing is, when the experimental work has been done in NIT Jamshedpur, the papers were considering the solar intensity of 1000 watt meter square only, sir.
Okay, that's fine. That's fine. Whatever sir has asked, that's fine. If you cite some reference, that's yes, it is on the basis of experimental results of X and Y.
Yes, sir. I actually forgot to mention that one.
Okay,
yes,
okay.
Yes,
That's
yes.
Yeah, Professor Rao, is there any question from your end?
No, sir. Actually, these solar air heaters mainly used for the mostly like in our country is in northeast region only. As I have completed my master's in NIT Meghalaya, so because all like average temperature is 18 degrees centigrade. So like if you consider that heat flux, then it will be more applicable for the like to implement or to reproduce some device to switch it will be applicable to that region that.
Yes, sir. Actually, it can be used for the preheating of air in thermal power plant also, sir. It increases up to 10 to 15 degrees centigrade. The temperature of the air. That way we can use in industrial purpose.
Yeah. Actually, I'm working in industry also, and I can see here like lot of exhaust gases are available, which we can increase that 15 degrees centigrade and up to 50 degrees centigrade. That will be negligible for the industrial case. Like it will not matter, and size of this thermal aerator is very big. If you want to apply in that cases like industrial cases.
Yeah.
So it will be like
that may be actually.
Any questions from any other audience? Then Jadava?
Yes, sir.
I have a couple of questions. So your another author, Dr. Senapati, is here or?
No, sir. Yes, no.
Okay. So I have some couple of questions regarding the presentations. So number one is just whatever the governing differential equation that you have presented. So I think you have, as per the governing differential equation, you have considered flow as compressible or incompressible?
Incompressible one, sir.
Okay, then you please verify the governing differential equation, like the continuity equations you have presented.
Yes, sir. Hello. Hello, sir. Am I audible, sir?
Yes, you are audible. I think.
Yeah.
Professor
Yes, sir. Actually, I'm not getting. Sir. Yes, sir.
Yeah. Am I audible right now?
Yes, sir. You are audible
yes,
right
sir.
now.
Yes.
Yeah. Just the continuity equations, whatever you have presented, that is true for compressible flow. So that is not correct for the incompressible flow. You please verify. I believe that whenever you simulated, you have considered the correct equations.
I will check. Yes, sir.
Yeah.
Definitely.
Since that is the divergence of the velocity vector, or del u j del x j equals to 0 is the correct form of the continuity equation for an incompressible flow. But you have considered del x j of rho u j that equals to 0. That is not the things.
Yes.
And number two is that you have validated or you have selected different turbulence model through a comparison with the results of the Dita-Spoilder equation. Am I right?
Yes, sir. Yes.
But what is the Reynolds number that you have considered for that selection of a turbulence model, RNGK epsilon, whatever turbulence model that you have chosen?
Yes, sir. Actually, for higher Reynolds number, it is used as the RNG epsilon model, sir. Hello.
Am I audible?
Yeah, yes, sir. Yes, sir. Okay, sir.
So my question is, what is the Reynolds number that you have? Yes.
Actually,
Hello?
sound is disturbing. Actually, sir.
Okay, now I think I am audible. Yes.
Yes, yes.
No. So my question is, what is the Reynolds number that you have considered? Since for your case, the Reynolds number you have varied from 3,800. Am I right?
Yeah, 3,800 to 18,000, sir.
18,000. But whatever the Dittus-Boelter equations that you have validated, but the limitations of the Dittus-Boelter equation is that the Reynolds number should be greater than 10,000. And that too, the Dittus-Boelter equation is applicable for turbulent flow through pipe having Reynolds number greater than 10,000. Am I right?
Yes, sir. Yes.
But for your case, the Reynolds number is
Reynolds number 3,000. It is 10. Yes. Actually, sir, for to encounter the number is also considered, sir.
No, say so. What my suggestion for you, not for right now, so at least you check once more validations before selecting the turbulence modeling. Okay.
Yes, sir. Yes.
And one more thing, that's I believe that's whatever the boundary condition that you have used may be all not sufficient. I think that you have used some commercial software. Am I right?
Yes, sir. I have been using the ANSYS ones.
Okay. Since I have not seen any boundary conditions for the turbulence kinetic energy, that is without boundary conditions, whatever the inlet boundary conditions for the turbulent kinetic energy, I believe we cannot solve the governing differential equations.
Okay, sir. Then I will check, sir. Actually.
Yeah. I believe that during simulations you have given, otherwise you cannot simulate. Since just first you have to verify what are the number of boundary conditions that is required, and until and unless the sufficient number of boundary conditions, whatever is needed that you have imposed, you cannot proceed for the simulation. Okay. Anyway,
yes,
that's a good.
Yes.
It's a good.
Yes.
And
yes,
if
sir.
any question is there from audience, so one or two more questions we can take. Otherwise, thank you once again, Jadava Manand and Dr. Sanaput.
Thank you, sir.
Okay. So we can move to the. We can move Antanu.
Yes, sir. Yes, sir. We are moving to next.
Yeah. First, verify that's whether Mr. Bikram Shukla either available or not.
Yes, sir. I am available.
Okay. Then Santanu, please. We start the presentation of Bikram Shukla. Yeah.
Everyone, my name is Vikram Shukla. I am working as a scientific officer at Bhava Atomic Research Center, Mumbai. My presentation is on the CFD evaluation of the effect of inlet gas conditions on the efficiency of passive catalytic recombiner device. Let us begin with a slight introduction to the topic. In nuclear power plants, during certain severe accident scenarios, there is a possibility of release of large amount of hydrogen, primarily by metal water reaction between the zircaloy fuel clad and steam at elevated temperature, and by a slower process of radiolysis of water. This hydrogen gets non-uniformly distributed in the reactor containment. The reasons for that are its positive buoyancy due to its light weight, the prevailing thermal stratified conditions during severe accident scenarios, and the presence of condensing steam which causes turbulence. All these factors lead to non-uniform hydrogen distribution and formation of hydrogen-rich pockets inside the reactor containment. These hydrogen-rich gas mixtures are detrimental for the integrity of the reactor containment because of the large flammability limits of hydrogen both in dry air mixtures as well as in steam-laden scenarios. Owing to this, various mitigation technologies have been studied and developed worldwide. Some important among them are mixing, inerting, controlled venting of the atmosphere, deliberate ignition, and passive catalytic recombiner devices. These passive catalytic recombiner devices, or simply the recombiner, consists of a rectangular box which is open from top and bottom, and it has got a stack of parallelly placed catalyst plates near the bottom, and has a chimney sort of arrangement at the top region. So it involves catalytic recombination of hydrogen on the surfaces of these parallelly placed catalyst plates along with the oxygen from the air present in the containment atmosphere. The hydrogen generated rises upwards due to molecular diffusion, jet momentum, and buoyancy. When it comes in contact with the catalyst plates, it gets absorbed and reacts on the surface of the catalyst. The formed steam rises upwards due to getting heated up by the exothermic nature of the reaction. This causes the formation of a natural convection loop around the recombiner box. Since high temperatures are involved, heat radiation also plays an important role, and the presence of steam causes condensation, and this also affects the distribution of hydrogen around the recombiner box. The advantage of using these recombiner devices are they are passive in nature, they do not require any external power or operation intervention, they are very easy in construction and have very low maintenance. They promote homogenization and mixing of the region around the recombiner box, and they promote continuous depletion of hydrogen until the concentrations fall well below the dangerous levels. This recombiner is modeled using CFD, and the figure here shows a pictorial representation of the model. Here the catalyst plates are modeled as a solid region, and the gas space around these catalyst plates is modeled as the fluid region. The interface between the solid nodes and the fluid cell is used to assign the reaction, the surface reaction. Here the source and sink terms for the species involved in the reaction, they are assigned to the first fluid cell at the interface, while the exothermic heat of the reaction is assigned to the solid nodes. The heat conduction takes place between the nodes of the solid region, while the heat gets transferred to the fluid region by convection. Since the plate reaches higher temperature, the thermal radiation is also modeled. The data exchange between the finite element based solver for the solid region and the finite volume based solver for the fluid region takes place by conjugate heat transfer at the interface during each time step of the simulation. So these are the set of equations used for the model. Here we can see that the mass, momentum, energy and species conservation equations have been solved along with their respective source terms. The reaction has been modeled using this indigenously developed reaction kinetics for the Indian recombiners. The phase changes are accounted for since the steam is involved, and these are modeled by homogeneous equilibrium model. The thermal radiation is also modeled using the equation shown here. This model has been validated against the experiments carried out for the evaluation of the reaction kinetics used for this model, and then the validated model has been used to carry out a parametric study. So for this parametric study, this is the geometry selected here. 4 catalyst plates have been taken. The dimensions of these plates as well as the pitch between them has been kept the same, exactly the same as the one used in the actual recombiner box. The central channel here represents a typical channel of a recombiner box, since it is neighbored by another channel on its either side, and hence it is a representation of a typical channel in the actual recombiner box having multiple parallel channels. For modeling this, the mesh has been selected based on a grid sensitivity study. This table shows 4 different types of grids having different element sizes in the directions parallel to the flow as well as in the direction perpendicular to the flow. The graphs show the change in concentration of hydrogen as well as the gas temperature along the height of the channel. Here we can see that the grid sizes 3 and 4 give more or less the same results, and hence grid 4 has been selected to carry out further parametric studies. So these are the various inlet gas conditions used for the parametric study. Here we can see different velocities, hydrogen concentration, steam concentration as well as inlet gas temperatures have been used to generate a wide data matrix. And here the efficiency or the conversion efficiency, has been defined as the ratio of the difference in inlet and outlet mass fractions of hydrogen and the inlet hydrogen mass fraction at the recombiner, and when it is multiplied by 100 it gives the efficiency. These figures show the typical contour plots for a case having 40% steam concentration, 8% hydrogen concentration, having a inlet velocity of 1 meter per second and a gas temperature of 105 degrees centigrade. Here we can see that as the gas rises upwards, the temperature increases. This is due to the addition of exothermic heat of reaction along the channel height. Since this density is inversely proportional to the temperature, it decreases with increase in the temperature along the channel height, and this decrease in density also causes the rise of fluid velocity to balance the mass along the channel length, and hence the fluid velocity increases along the height of the channel. So these are the contour plots for hydrogen concentration, steam concentration and oxygen concentration. Here we see that hydrogen concentration decreases along the height of the channel while the steam concentration increases. Similarly, oxygen concentration, as it recombines with hydrogen, it also gets slightly decreased along the height of the channel. The results of the parametric study are shown in this graph. Here we can see that with the increase in steam concentration, there is no change in the conversion efficiency for various hydrogen concentrations. Hence, we can conclude that the conversion efficiency of the recombiner is independent of the inlet steam concentration up to 60% steam. Further studies were not carried out because after that the gas mixture becomes inert and hence the recombiner itself is not required. The right graph shows that hydrogen concentration causes a very sharp rise in the conversion efficiency. This is because at increased hydrogen concentrations the reaction rate increases, causing better conversion efficiency. Similarly, here we can see that with the increase in the inlet velocity between the channels, the conversion efficiency decreases. This is due to the fact that the resistance time between the parallel channels decreases as the velocity increases, thus the absorption possibility of the hydrogen decreases, and this leads to lesser conversion efficiency with rise in inlet velocity. On the other hand, the conversion efficiency increases with rise in temperature. This is because of the fact that the reaction kinetics is highly dependent on temperature, and as the temperatures rise, the reaction kinetics or the rate of reaction improves, causing a better or faster conversion efficiency. From these studies, we can conclude that the conversion efficiency of the recombiner is almost independent of the steam concentration for non-inert gas mixture, while it is highly dependent on the inlet hydrogen concentration. It is also increases with increase in the inlet temperature because of faster reaction rate at higher temperature. And for keeping all other parameters constant, if the velocity of the gas mixture increases along the recombiner, the efficiency decreases due to lesser residence time for the absorption to take place. These parametric studies are vital to understand the quantitative effect behavior of recombiner, and hence can be developed further for an empirical correlation for the same. Thank you.
Thank you, Bikram. So it's a nice presentation. So now the session is open for question answering. So I request the audience to please raise your hands through the Microsoft Teams if you have any questions. Bikram is available to answer those questions. Anyone? Any question from the audience? Bikram?
Yes, sir.
So,
hello. Sir, your video is stuck actually. Hello. Hello.
Yeah, am I audible?
Yes, sir. Now you are audible. Actually, your video got stuck.
Yeah, I understand. So my question is, number one, have you used your own code or you have used some commercial software to solve the governing differential?
Sir, actually, this commercial CFD code Fluidine, it was used actually. That is a general purpose code, and therein this recombiner model was built by us.
Okay. And as the recombiner model is built, so what is the purpose? You have mentioned that the finite element method is used to solve the equation for the plate. Similarly, the finite volume equation is used for the solution of the whatever the governing differential equation in the fluid domain. Can you tell me why these two separate methods? One is the finite element and another is the finite volume. What is the logic for?
Sir, see, this is actually a special case. Here, the problem is that it's a surface reaction happening on the catalyst plates, which are solid in nature, while the reactants which involve, they are gaseous in nature. So when this device is modeled, both of the domains, the solid plates as well as the fluid gas space has to be modeled. So then there a fluid solid interface gets created. So and since it's an exothermic reaction, heat is also liberated during the reaction. So during modeling, based on various literature studies and as well as our own experience, there are options to assign this heat liberated either directly to the gas or to the solid plate. Since it's a surface reaction, so it's a typical choice. So for that particular issue, so this finite element method also comes into picture, as the heat conduction equation has to be solved within the solid catalyst plate, as well as it is in interaction with the gas space. So this heat gets dissipated to the gas by convection also once the temperature of the solid plate rises. So both at each time step, both these solvers, they run parallelly, and then at each time step they exchange the heat fluxes based on the temperatures of the fluid and solid domain, and thus this solution gets progressed.
Okay, I understand, but my question is there any limitations to use the finite volume method to solve the governing differential equation in the plate, so that we use the two models, one is the finite element and the finite volume together, and again whatever I understand, that it creates the problem more complicated. If you use the either the finite volume or the finite element method to solve the governing differential equation both in the fluid as well as the solid domain. So whatever the complex cases, that will be little bit less.
Yes, sir, that is also a choice, but since I was using this Fluidine software and so they are yes,
this
sir,
is in the software, I understand. So now one more question, sir. What about the mass conservation equations you have used? You have written on the right hand side there is a source term. I don't understand what is the source term or the mass conservation equations, but in the equations, whatever equations that you have written in the mass conservation equation, there was no source term. But on the right hand side, you have written some source term for the mass conservation equations. Either those are typos or those are correct.
No, sir. Actually, that is for the momentum. It is the tabulation has been a bit staggered, so that's why it is a bit confusing. But actually, it is for the momentum, and as well as for individual species, there is this mass conservation for the species. Since it's a chemical reaction, so hydrogen gets consumed and all that way.
Yeah. And what's about the governing differential equations that you have solved in the plate?
Sir, this it is basically this conduction equation, heat conduction equation is solved by this finite element method, and since these high temperatures are also involved, this thermal radiation has also been accounted for, and for that this discrete ordinates methods has been used.
And what's about the thermophysical properties? Those are temperature dependent, independent?
Yes, sir. They are temperature dependent.
Okay.
Then for the gases, since this conductivity, hydrogen is involved, so conductivity is quite an important factor here, and the temperatures also vary in a wide range. So temperature dependent, these properties have been selected, and based on the temperature of the gaseous space as well as the solid, each time step they check for it, and then they take the property. The solution takes the properties accordingly.
That means within the governing differential equation, some more equations are there where the thermophysical properties both within the liquid as well as the solid domain that varies with the temperature. Am I right?
Yes, sir. Yes, and since these phase changes are also involved, so this equation of state have been slightly tweaked, and there is a this slide one term this time lapse has been taken to account for this supersaturation and those things. And that's as you rightly told, some more set of equations have been plugged along with these equations which I have shown.
Yeah, and what's about the boundary conditions? What are the at the interface or?
Yeah, sir, I will tell you. Since this model is actually intended for a larger scenario where closed domain, there are these recombiner devices are located at some locations, but I have considered only it as a standalone case. So here I had to give the inlet and outlet boundary conditions, the wall of the side, the box which is the central part is the catalyst plates, but the side walls are they are inert. So they are that no slip adiabatic boundary conditions I have taken, and on the catalyst surface also this isothermal boundary conditions for this isothermal no slip boundary condition I have taken, so that this heat flux gets exchanged based on the temperatures.
Yes. And the last question from my side, let's say you have presented some nice results, but how many concentration of hydrogen that you have considered?
Sir, actually, yeah, I'll tell you. This is a part of a larger study, so where actually I conducted around 50 cases, and that was done to develop a data matrix to generate an empirical correlation for this recombiner. So those set of inlet conditions, as you asked this about the hydrogen, I took about it is 0.5%, 1%, 2%, 8%, 4%. So these hydrogen, and similarly steam, and similarly the velocities, expected velocities. So based on our other studies, parallel studies, so the expected since it's a standalone thing which I have presented, but actually it is meant for an integrated case. So there all these things come automatically based on the transient of the this containment atmosphere. So based on the expected values, I have taken certain set of each parameter like hydrogen concentration, steam concentration, the inlet velocity, and the temperature.
Very good. So just again, if anyone has from the audience, if any question is there, I will take one or two more questions. Otherwise, we will move to the next one, next presentation. Is there any question, Santanu? Is there any raised?
No.
Okay, then once again, thank you, Bikram Shukla, for your nice presentations. So, the next presenter is the Arnab Mukherjee. Are you available?
Yes, sir.
Yeah. So, Santanu, please start the presentation of Arnab Mukherjee.
Good morning. Today, I, Arnab Mukherjee, going to give an seminar on the topic, the effect of surface radiation and conduction of funnel on IRS device. We'll discuss what is an IRS device. The IRS device is usually positioned at the exhaust of a gas turbine in a warship and helicopter to reduce the temperature of the exhaust gases. Then why we need an IRS device? If the high temperature from the exhaust gases is allowed directly to the ambient, it may act as a source of infrared radiation. However, this is not desirable since it may be tracked by enemies in some special regions of the sea sky by the help of infrared detector. Then what is the working principle of IRS device? Basically, when the exhaust gas from the gas turbine, this is the gas turbine, is discharged through the IRS device, this is the IRS device, is discharged through the IRS device at a high speed from the turbine, a low pressure zone is created inside these funnels. This pressure difference produced by the presence of low pressure region helps to induce cold ambient airs. These are the cold ambient airs from the interfunnel space within the IRS device. Due to the turbulent nature of the flow, this results in good mixing of hot exhaust gases and cold ambient air produced inside the system. As a consequence, the exhaust temperature decreases to a safer temperature. These are the few IRS device. This has been designed by DRDO India, and this is an IRS device designed by European Union, their agencies. Then these are some of the advantages and disadvantages of the IRS device. It is very simple, cost effective, minimum maintenance and less noise. Disadvantages is that it is a passive cooling technique. All the gases could not be cooled, and its applications are it is used in frigates and ocean liners. Literature review. These are some of the few literature review I have shown in this slide. From this literature review, we have found a research gap, and we will discuss in the next slide. From the literature review, it is found that no study has been reported to have a complete picture of flow, heat transfer, and mass entrainment of a real-scale IRS device. This is a schematic diagram of an IRS device with conical funnel. The IRS device consists of 5 conical funnels are mounted one over another. All the walls of the funnel are conducting and having some width. The hot air is entered into the IRS device with some velocity and temperature through the turbine exhaust or nozzle. The hot air combined with the ambient air and helps to reduce the overall temperature of funnel at the exit. These are some of the dimensional parameter which has been shown in this figure. The boundary condition, the computational domain has been taken into consideration, and outside this funnel everything has been taken as pressure outlet boundary condition. A uniform velocity at the exhaust of the nozzle means velocity inlet boundary condition has been implemented, and exhaust temperature varies at the range of 400 to 600 Kelvin. The Reynolds time average equation for mass, momentum, and energy in initial reference frame has been expressed, means continued equations, momentum equations, energy equation, radiation equation, and conduction equation shown in this slide. The present numerical scheme has been validated with some of the established experimental data from the literature. However, the mass entrainment of IRS device with conducting funnel and radiation effect is considered a new research field. The present numerical scheme is validated with Ganguly and Das. The mass suction ratio matches with the experimental data. In the next slide, we will discuss about grid independent solution. The figure demonstrates the grid independent test for the current numerical scheme for the case funnel overlapping height equal to 0, nozzle overlapping height equal to 22%. Initially, a few number of grids taken in the computational domain. There is gradually increase in number of cells in the domain so that entrainment ratio become independent of the cell. We have considered 1,13,000 cells as a grid independent domain. The impact of number of funnels on the air entrainment for various wall boundary conditions of the funnel has been discussed in the first resultant discussion. The three type of boundary condition for the funnel wall has been considered. One is adiabatic boundary condition, conducting wall boundary condition. Second one, conducting wall boundary condition with surface radiation. The figure reveals that mass entrainment into IRS device goes up with number of funnels and achieve a peak at funnel having number of funnel equal to 5. The average mass suction increases around 100% when number of funnel increases from 2 to 5. This increment rate with number of funnel because the pressure inside the system decreases with rise in number of funnel. And secondly, among the three boundary conditions for funnel wall mentioned in this figure, the conducting funnel with surface radiation has maximum suction ratio. It is around 7 to 8% higher than the adiabatic funnel. This is because the conducting funnel also dissipate heat to the ambient, so the air in the intermediate surrounding of the funnel will have a more substantial temperature, which makes a drop in air density. Thus, the cooler air from the far stream moves towards the device, result in mass augmentation. The variation of IRS device outlet temperature with number of funnel has been shown in this figure. As the number of funnel increases, the average temperature of the system reduces at the exhaust. Around 20% drop in temperature when the number of funnel increases from 2 to 5. The static temperature contour at the outlet of IRS setup for various different number of funnel has been displayed in this figure. It is noticeable from this contour plot that temperature slowly decreases with rise in number of funnel. The maximum temperature occur at the center of IRS device, gradually reduce in the direction. We can compare from the 2 and 5 funnel that 5th funnel having lowest temperature at the outlet. This figure indicates the variation of mass entrainment with nozzle Reynolds number for different wall boundary conditions which has been discussed in earlier. This phenomena occur due to a reduction in device inside pressure with rise in exhaust velocity. We can see that as the Reynolds number increases, the mass suction also increases. For adiabatic case, there is a less increment, whereas there is more insignificant increment for other cases, which has been earlier discussed. From this figure, it is observed.
Thank you.
Thank you, sir.
Thank you, Arnav, for your nice presentations.
Sir,
So we'll take,
there is a hand raised.
yeah. Please take the questions.
Okay, sir.
Santanu? Yeah.
Hello, this is Amaresh.
Yeah.
So you can take the question from. You can see, right, raise hand.
Yeah.
So you can ask him to.
Hello, sir. Am I audible?
Yeah. You're audible.
Yes, sir. So first of all, it's a good work. Sir, this question is to the presenter. Could you quantify that the heat dissipation by radiation and conduction with funnel to without funnels? Means without device to with device.
Without device, it is directly coming to the surrounding. Means if the enemy try to detect through a detector or thermal detector, he can detect you directly. If our temperature is around 600 Kelvin, then it comes to the surroundings directly, means 600. If you are using IRS device, it comes around dropping around 30 to 40%. So it's quite a significant. 30% means around it comes around 500, 400, around 480 or 4 Kelvin.
Okay, what is the detectable range of temperature using an IR system? So by using this IRS device, can we avoid the detection from the enemies?
Any hot surface can be detected by a thermal detector from a satellite scanner, or it is around 400. It starts from 400 Kelvin onwards.
400 Kelvin, around 100 degrees centigrade.
100 degrees centigrade.
So by using this IRS device, we can escape from the enemies.
Yes.
It is warships. If it is a warship.
Yes.
And could you quantify that the radiation dissipation percentage and the conduction percentage by using this IRS device? Which one is more significant?
I have actually not calculated this. I have only calculated how what is the shape of this IRA device so that we can reduce the temperature. Actually, I have not calculated what is the radiation emission or conduction emitted from this device. I have
Is it a
only
good idea
quantified.
to calculate those?
Sir, I am not getting your point.
Is it a good idea to quantify those?
It is a good idea, but my work on is how to design a IRS more efficient IRS device. My idea is to devise a more efficient idea.
Yeah, that's so whenever you go for better design, you must consider what's the contribution of diffusion heat transfer as well as the radiation heat transfer. Only better design is possible.
Okay, sir. I will.
Yeah, Amores.
Yes.
So, thank you, Arnav.
Thank you, sir.
Nice presentation. Amores, anything you would like to share?
No, thank you. So next presentation, if you tell, then we'll go.
Yeah. The next presenter is Kshitiz Gormode. You please.
Yes, sir, I'm present.
Yeah, Antonu, you please start.
This is Kshitiz Gormode from IIT Bombay. I'll be presenting my work on numerical study of electromagnetic braking of the molten steel flow in a continuous caster. This work was done under the supervision of Professor Avishek Ranjan. Most of the steel production in India and worldwide is done using the continuous casting method. The processes involved in this method are complex, involving turbulent flow, heat transfer, solidification, etc. With an increasing demand, it is expected that steel manufacturers will aim to increase the production by increasing the casting speed. However, this can introduce turbulent fluctuations in the flow of molten steel. A suitable method to mitigate these unwanted fluid fluctuations and thus provide high quality cast slabs is electromagnetic braking. With EMBR switched on, the Lorentz force arising due to the interaction of the magnetic field and current density can control the flow so as to minimize the defects and achieve the required quality of steel. The coupled effects of the magnetic field and its influence on the flow come under the ambit of magnetohydrodynamics. In this paper, we perform numerical simulations using open foam where the governing equations for mass and momentum are solved along with the potential-based MHD equations. Governing equations for a Newtonian and an incompressible fluid are the continuity and the Navier-Stokes equations. FL bar denotes the Lorentz force per unit volume, and the term FL bar by rho has been added as a source term to the Navier-Stokes equation. Now, for a liquid metal MHD problem, the magnetic Reynolds number is less than 1, which implies that the diffusion phenomena dominate the advection effects. So, the total magnetic field capital B bar can be approximated by the imposed magnetic field B naught bar. Next, a Poisson's equation for the electric potential phi is obtained as follows. So the Poisson's equation is del square phi equal to del dot u cross b naught, where u is the velocity vector. Now to solve this Poisson's equation, an electric potential based solver EPOT foam given by Tessone was integrated in open foam for our study. Now the turbulence in our problem has been modeled by using the standard K epsilon turbulence model, and the fluid properties are mentioned in the table below. So this is the geometry used for the purpose of simulations. So the cross-section dimensions in the XY plane are 218 mm cross 1300 mm, and the depth is 2600 mm. So this is the submerged entry nozzle, and the nozzle dimensions and the submergence depth are mentioned. So the nozzle ports make an angle of 15 degree with the horizontal axis, and all the plots and images which will be shown subsequently are taken at the midplane of the geometry with the normal in y direction. A gradient independence test was carried out to determine the computationally most efficient mesh, and the parameter in consideration for this test was the averaged surface velocity at the top surface, which is the meniscus. So the test was implemented using 3 meshes, and the results are shown, and according to which the 21 lakh element mesh was chosen. So the boundary conditions for the turbulent quantities at the inlet ports have been evaluated using relations for fully developed channel flow. Also, no slip velocity boundary condition has been applied for all the solid walls except for the meniscus at the top, where free slip boundary condition has been imposed to depict the free surface of the fluid. There are certain assumptions involved. The velocity profile is assumed to be uniformed across the nozzle inlets. the solidification of the steel along the mold walls is neglected, and the mold is assumed to be a perfect insulator. So this translates into a Newman boundary condition for the electric potential phi. So this is the magnetic field profile. The image on the left has been taken at the mold midplane, and only the top half has been shown. As we can see, the two rulers of a magnetic field are clearly visible. So in the red region, the value of magnetic field is plus 0.25 Tesla, and in the blue region, it is minus 0.25 Tesla. So this variation is visible in the line plot as well. Since two distinct rulers of magnetic field are formed, this configuration is known as double ruler EMBR configuration. So these are the computational details. In all, 6 computations were performed for 100 seconds for 3 velocity magnitudes of 1, 1.5 and 2 meter per second, and the average was carried out over 400 seconds. So these details are summarized in the table below. Let us now discuss the effects of EMBR on velocity. Figures A and C show the velocity magnitude at t equal to 3 seconds for a jet inlet velocity of 1 meter per second. So in figure A, in the absence of magnetic field, it is clear that the jet is straight and no significant fluid motion is observed at the meniscus. However, in figure C, in the presence of magnetic field, the jet is pushed upwards and inwards due to the presence of Lorentz force, and some fluid motion can be observed at the meniscus. So these figures show the values of turbulent kinetic energy for the same cases at the same time. So in the absence of magnetic field, we can see the TK values at the walls are quite high. However, once the EMBR effects are switched on, so the TK values at the wall decreases. So it can be inferred that the magnetic field suppresses turbulence in the region close to the walls. However, due to jet curling, some turbulence is also observed in the region above the ports. We'll now discuss the effects of changing the jet inlet velocity when EMBR is present. So the figure above shows the velocity magnitude plots at t equal to 2 seconds for the 3 EMBR cases. So in figure A, the jet inlet velocity is 1 meter per second, in B it is 1.5, and in C it is 2 meter per second. So you can clearly see that as the jet inlet velocity increases from figure A to figure C, the penetration of the jet, the meniscus velocity, and the tendency of the flow to curl upwards increases. So in this plot, we have plotted the meniscus velocities for the previous 3 cases in solid lines, and the dashed lines represent the cases in which EMBR was switched off. So we can comment that due to EMBR, jet curling occurs, and this increases the meniscus velocity in the presence of EMBR, and this increases largest when the inlet velocity is 2 meter per second. We can also see that the maxima of the velocity magnitude curve shifts towards the inlet ports when EMBR is applied, and this shift is more pronounced when the inlet velocities are smaller. So this is probably due to a lower x momentum in the flow for smaller inlet velocities. So these 3 figures show the vorticity plots for the previous 3 cases, and we can see that the circulation in the fluid seems to be largest for 2 meter per second inlet velocity. Also, vorticity is high at the ends of the jet in all the 3 images due to the presence of shear, as there is a velocity gradient across the edges of the jet. So these 3 figures show the turbulent kinetic energy variation for the previous 3 cases, and we can see that turbulent kinetic energy is again relatively larger at the edges of the jet, again due to high shear and vorticity present in this region. However, in case C3, we can say that the turbulence is present in the region close to the walls, and also in some region between the inlet ports and the meniscus. However, in case C1, turbulence is mainly confined to some region around the inlet. So we'll now discuss the unsteadiness in the flow. So this video compares the velocity magnitude profiles for a jet inlet velocity of 1 meter per second in the absence of EMBR and in the presence of EMBR. So on the left, where EMBR is absent, the jet penetrates the mold and hits the wall. On the other hand, on the right side, the jet is pushed upwards and then inwards due to the Lorentz force, and jet curling is observed. So at a particular time, complete jet curling occurs, and this configuration stays for about 25 seconds. On the left, we can see that there are some fluctuations in the tail of the jet, and we can also see that some jet thinning is also observed, and these fluctuations can be seen over the rest of the flow period in this case. Now let us focus our attention on the right video where some oscillations will be seen. So at a particular time instant, the left jet penetrates the mold and the right jet is suppressed. At the next time instant, the right jet penetrates the mold and the left jet is suppressed. And the same thing occurs again and again. And so these oscillations dominate the flow over the rest of the flow period. So it is clear from this video, and the time periods of these oscillations are roughly the same. So we'll now study the variation of oscillation frequency with the inlet jet velocity. So the three cases in this video correspond to the cases with inlet velocity of 1 meter per second, 1.5 meter per second, and 2 meter per second respectively. Now we'll move on to the time where the oscillations actually begin. So if we just count the number of oscillations over a period of 100 seconds, we'll find that the number of oscillations are 4, 9 and 14 respectively. So this suggests that the oscillation frequency increases as the inlet velocity is increased, and hence the frequency is proportional to the Reynolds number. This plot on the right shows the time averaged velocity magnitude at the meniscus over 100 seconds for all the cases. So the mean plots are symmetric to a great extent. In the absence of EMBR, there are two maxima in the mean velocity plot. However, in the presence of EMBR, there are four maxima in the plot, two near the mold walls and two near the nozzle. It is also interesting to note that the velocity becomes zero at some distance from the wall as the velocity changes direction in the case with EMBR. So from the plot, it can be concluded that EMBR slows down the fluid close to the mold walls and accelerates it in the region close to the nozzle. Discuss the conclusions. So EMBR pushes the jet from the nozzle upwards and inwards towards the ports, which results in the curling of the jet. The turbulent fluctuations are suppressed by EMBR as reported by Sarkar and associates. We also observed some flow asymmetry in the non-magnetic case. However, periodic oscillations were prevalent when EMBR was applied and the frequency is proportional to the Reynolds number. So this asymmetry has not been reported in the work by Sarkar and associates, where symmetrical velocity distribution across the nozzle has been observed. It is possible that the Lorentz force amplifies the inherent fluctuations which result in the periodic oscillations. The future work would involve the investigation of the possible modifications of the turbulence model to incorporate the MHD effects like the one by Smolensk and associates. Thank you for your attention.
Thank you, Ketis, for your nice presentations. So just we will take one or two questions if anyone has questions from the audience. Just one or two questions we will take. I think there is no question. So just one suggestion. It's not a question. It is just I believe that you have solved the fluctuating components of the velocities and everything. Yeah. So whatever the governing differential equations that you have presented, it's better if you present in terms of the fluctuating components. So that's whatever is the necessity of turbulence modeling, that will be reflected in the governing differential itself. Okay.
Okay. Yes. Okay.
Yeah. So thank you once again. So Santanu, just we'll move to the next presentation. Our next presenter is the Oritto Raichodhuri. Oritto, you are present here?
Yes, sir, I am present here.
Okay. So Santanu, you please start.
Distinguished guests from academia and industry and my fellow research scholars. My name is Oritto Raichodhuri. I am a research scholar at IIT Madras, and today I am going to present a paper on evaluation of turbulence models for an offset planar wall jet with heat transfer, which is authored by me, Priyesh Kaka, also a research scholar at IIT Madras, currently working at General Electric, and our advisor, Dr. Kameshwararam Anupinji. I would like to begin the presentation with a brief introduction to offset jets. The offset planar jet is a complex fluid mechanics problem with distinct flow regions, mainly the recirculation, reattachment, and the wall jet region. It has applications in heating and cooling of surfaces with a jet where the jet nozzle cannot be in contact with the surface. For example, wet paint or a moving surface, or a very hot or cold surface which can damage the nozzle of the jet. For applications of controlling the path of the jet or to divert the path of the jet using a solid surface adjacent to the jet exit can also be modeled as offset jet. Offset jet comes up in applications that need upper surface blowing, for example to create a fluid film over a surface or to create a lift by blown flap method. In these cases, the flow is essentially in an offset jet setting. As we can see, there are numerous applications for offset jets, and for efficient design of equipments, a very good understanding of the flow is vital. Lots of studies have been conducted, both analytically, experimentally, and numerically, to understand flow and heat transfer characteristics of offset jet. But high fidelity numerical simulation is missing in the literature. That is, DNS or LES studies have not been done. The present study aims at comparing RANS and LES turbulence models and conclude the effectiveness of the models to predict the flow and heat transfer characteristics of an offset planar jet. This will help us choose the appropriate model for its simulation according to our requirements, also keeping in mind the computational cost. It will also help us in finding out the drawbacks of existing models and solvers and ways to improve them. Now, I will speak about the boundary conditions and the computational setup for the study. Dimensions of the 2D domain for RANS simulation is 40 by 10 nozzle width in the streamwise and vertical directions respectively. For LES, the domain is 5.5 nozzle width wide in the spanwise direction with periodic boundary condition. The left and the bottom wall has no slip boundary condition and the right boundary has advective boundary condition for velocity. In the top boundary, velocity is given, which is 4% of the nozzle outlet velocity in the negative y direction to account for entrainment. The difference in room temperature between the jet/ambient fluid and the bottom wall is 52 degrees Celsius. The Reynolds number of the flow is 11,000 and the inlet velocity profile is obtained using channel flow simulation at the same Reynolds number performed using RANS. The offset ratio is taken as h by w, that is height of the center line of the nozzle from the bottom wall divided by the nozzle width, which is 2.125. OpenFOAM and open source CFD software is used for simulating the flow, and buoyant business simple foam or based incompressible flow is used. Models tested are Smagolinski model with band driest wall function, standard K epsilon model, and low Reynolds number K epsilon model. Schemes used for LES model is second order upwind in space and Crank-Nicholson for the discretization in time. For RANS models, second order upwind is used in space and Euler for the discretization in time. The statistics is collected for 12 flow through time. The governing equations solved for incompressible flows are given below. The first one is the continuity equation, next is the incompressible Navier-Stokes equation, and the third is the energy equation. Now I will speak about the different turbulence models in short. The standard K epsilon model belongs to the RANS family of turbulence models, and in this model the eddy viscosity is solved using two additional quantities, K, the turbulent kinetic energy, and epsilon, the turbulent dissipation rate. The two quantities are solved using the equation given below. This is the transport equation for K, and this is the transport equation for epsilon, or the dissipation rate, where capital P is production term, sigma and capital C are empirical constants. The eddy viscosity is obtained using this equation. The low Reynolds number model is similar to standard K epsilon model, but in addition to solving the two transport equations, damping functions is used to correctly calculate the flow inside the viscous sublayer. The eddy viscosity is obtained using this relation. The extra terms in the model, the damping function f nu, f1 and f2, and the extra source terms capital D and capital E are only active close to the solid walls and make it possible to solve K and epsilon all the way down to the viscous sublayer. Now moving towards large eddy simulation. Unlike RANS models, which averages the flow field in time, LES filters the flow field. That is, it computes explicitly for the larger eddies and models the smaller one. After filtering operations and applying Bouguen's hypothesis, the following equation is obtained for the momentum equation, where the over bar represents filtered quantity. Here we can see an extra term, nu t, which represents the SGS viscosity or the subgrid scale viscosity, and Smagolinski model computes the nu t using this formula, where delta is filter width, capital CS is an empirical constant,
capital Sij is the strain rate tensor. The energy equation after filtering operation yields this equation. Now coming to the results. The results of the study is compared with experimental results of Burke and Newman, Lund, Nasser and Lai, Song et al. And numerical results of Nakavi et al. The variation of normalized mean streamwise component of velocity in the wall normal direction is presented at two locations in the streamwise direction at x is equal to 20 and 30 nozzle width. It can be seen that the profile obtained using the LRN model as well as the LES model show a good match with the experimental results, whereas the standard K epsilon model fails to predict the profile correctly and a mismatch in the near wall velocity gradient is evident. Next, variation of normalized mean temperature profiles in the wall normal direction is presented. At x equal to 25 nozzle width, the temperature profile is evaluated by comparing the results with DNS results obtained by Nakavi et al. It can be noted that the temperature profile obtained using LES is quite accurate when compared with the DNS profile. The RANS models do capture the trend of the temperature profile correctly but fail to predict the correct magnitude. The temperature profiles in the wall normal direction are plotted in the recirculation region at x equal to 4 nozzle width. It is seen that K epsilon model fails qualitatively, whereas the LRN model is close to the LES result. Next, the turbulent kinetic energy is plotted at two different locations in the streamwise direction, and it can be noted from the plot at x equals 30 nozzle width that the K epsilon model cannot predict the turbulent kinetic energy correctly, and the LRN model shows a better performance qualitatively. The Smagorinsky model as well as the LRN model compare well with the direct numerical simulation data obtained by Nakavi et al. In the recirculation region near the inlet at x equals 4 nozzle width, it is observed that two peaks are obtained with a higher peak near the wall and all the models are able to capture those peaks qualitatively. Now coming to the evolution of pressure coefficient and a Nusselt number in the streamwise direction. It can be seen that for the pressure coefficient obtained using LES is matching with the experimental results obtained by Burke and Newman and Song et al. The peak value is correctly predicted by LES, while the RANS models fail to obtain a correct peak for the pressure coefficient. LES captures the trend of the pressure coefficient well as compared to the RANS model, which underpredicts the magnitude. The shift in the peak predicted by LES and RANS models could be because of the difference in the offset ratio between the simulation and the experiments. From comparison of wall Nusselt number, it is seen that the LES model and the K epsilon model captures the profile qualitatively, but the K epsilon model severely underpredicts the magnitude. The IDS model has a slight overshoot of the peak close to the inlet compared with the experimental data. But both the profile collapse downstream of x greater than equal to 12 nozzle width. The Nusselt number profile captured by the LRN model is close to the profile of the LES model, except near the reattachment point where the LES model shows a large dip in the heat transfer and thus fail to predict the peak. Next, the decay of maximum velocity is compared with Nasser and Lai experimental results, which show that the decay is well predicted by the LES model, whereas the RANS model fails to predict the dip around x equals 7.5 nozzle width. Next is the normalized mean streamwise velocity profiles in the recirculation region for different turbulence models is compared. It is evident from the comparison that in general both RANS models differ when compared with the profiles obtained using LES model. The RANS results show a more diffusive nature and strong backward flow at locations x equals 1, 2 and 3 nozzle width. Upon reattachment at locations x equals 8 and x equals 9 nozzle width, the velocity profile obtained using LES shows a flattened streamwise velocity closer to the wall when compared to that obtained using RANS. In comparison to the standard K epsilon model, the LRN model shows a better match with the LES profile at locations after reattachment point, that is at x equals 7 through 9 nozzle width. Finally, the maximum pressure point at the wall and the reattachment point is compared with experimental results, and it can be seen that in calculation of this length, LES Smagorinsky model has the least error and the standard K epsilon model has the most. Now coming to the summary of the study, it is evident that LES model captures the flow characteristics such as velocity decay, mean streamwise velocity profile, turbulent kinetic energy,
profile and the execution of pressure coefficient in the streamwise direction better than the two Ranks models. Among the two Ranks models, the low Reynolds number model is superior and can capture velocity profiles qualitatively. The LES model predicts the streamwise evolution of Nusselt number better than the Ranks model, and LRN model failed to predict the Nusselt number, while the standard K-Fallon model underpredicted. From these observations, it can be concluded that even though LES is computationally expensive, it is a better tool to capture the flow and thermal characteristics of retouching offset voltage, and LRN model performs better than the standard K-Fallon model. Now, to conclude the presentation, the outlook of the study is to better understand the turbulent kinetic energy and Reynolds stress budgets in the recirculation region to better understand the flow, and to simulate a three-dimensional offset jet to study the characteristics of heat transfer and flow in the span-wise direction. I want to acknowledge the Vargo High Performance Computing Facility in IIT Madras and MHRD Government of India for NS scholarship, without which the study would not have been possible. Thank you for your time and opportunity to speak at this platform. Any questions and feedback?
So thank you, Aditya, for your nice presentation. So we'll take one or two questions from the audience. So now it is open for the question answering. So from audience, if you have any questions, we will take one or two questions. Since we are running late, the next session will start from 4:15. So Ritu, it's a nice presentation, and as usual, that's whatever results that you obtain using the K epsilon model. The difference is the maximum because there is, although the Reynolds number is less, that is 11,000 that you have considered, but still because of the formation of the recirculation region, whatever the predicting capability of the epsilon model, that is not good once the recirculation zone is formed.
Yes, sir.
Yeah, and obviously the LES model gives a better performance.
Yes, sir.
Yeah. So thank you. So Santanu, just will move to the last presentation for this session.
Thank you, sir.
Yeah.
Okay,
Thank
Professor. Professor Poti, just I will announce once. Professor Amit Dhiman, just we have another presentation left. So next session will start from 4:30. Professor Dhiman.
Okay. Good afternoon.
Okay. Good afternoon. So please wait for 15 minutes, and I request.
Good afternoon.
Professor Dhiman, this is Sukumar Poti.
Okay. Thank you, sir. How are you?
Fine, sir. Fine. So many times Professor Barauni told me that's whenever actually we used to work together right now, Professor Barauni and myself.
Okay, we'll meet. I think sometime.
Yeah. And every time he said, "What's about the Dhiman?"
Okay. He's a nice person.
Yeah,
so
he's a nice person.
Professor Dhiman, you please.
I'm logging out.
No, you please be there. No problem. You please be there.
I'm here.
Okay, thank you. Professor Poti, hi.
Yeah.
Okay, you please.
Please start.
Santanu, please start the presentations. First, you verify whether the Srinivas Rao is available or not.
Yes, sir, available, sir.
Okay. Then Santanu, please.
Now I would like to give a presentation of my submitted paper, that is prediction of Pulfar flame characteristics using numerical simulation. Today's my laptop presentation is follows like this. Introduction. When a flammable fluid spills onto the ground and it forms as a pool of fuel, and if any external head of heat come into contact with it, and the layer of the fuel start burns, and it follows the process, the layer by layer of the material burns, and it is called pool fire. The pool fires are the most commonly occurring fire hazards in the process industries. So it is very important to understand the impact and its strength to take some pre-planned precautions, so that it will so that we can reduce the impact of the fire on the equipments and buildings and some nearby human lives. So the pool fire characteristics like flame length, shape, temperature, heat flux distribution, radiations are typically used to define the extent of the fire and its impact. So the main strength of the pool fire is the wind velocity and the surrounding temperature and surrounding the temperature. So by taking all these references, I have gone through some literature review. Athar et al. In 2019 conducted experiments on three types of liquid pool fires, that is kerosene, gasoline, and TBBP. And among all these three fuels, TBBP is having more higher effect on the surroundings, and it is also found that the flame height is 3 to 4 times larger than the other fuels, and also found the safety distance for the each pool fire with the different diameters and fuels. And Vasant et al. In 2013 implemented 4 different turbulence models using ANSYS Fluent, using species transport combustion model. So he finally ended with the minimum error is 17%. And Sun et al. In 2014 simulated LNG fire station to find the safety distance between the AAV tanks and walls, and it was found that it was less and suggested to increase that. And Topisikin in 2019 also conducted experiments on hydrocarbon pool fires, and also the same validated using the CFD solver, that is fire dynamics. Rengel et al. In 2019 found investigated capabilities of CFD modeling tools, that is flask fire and FDS, using diesel and gasoline pool fires and with different diameters. And he analyzed the how the burning rates are changing with respect to the wind velocity. And Chen et al. In 2019 carried out experiments to study effect of the lip height and cross flow air speed on the burning rates. And he measured with different wind velocities the ratio, that is height to diameter of the pool is found. Lin et al. In 2019 investigated flame geometry by conducting experiments of the propane pool of square size 8 cm, 10 cm, 15 cm, and 20 cm. And he was found height and horizontal length and tilt angle of the flame. And is also found that 2 regions, that is region 1, which is similar to the boundary layer, and in second, where the buoyant forces are not dominating, and in second region buoyant and inertial forces are dominating. So for the analysis of the flame in the region 2, an integrated model is required to study the combined effect. Many works has been performed in this area and experimentally, and some works also performed through the simulations, but no one done any detailed analysis, that is flame characteristics, that is height and length and flame tilt angles. The flame characteristics are the main primary parameters for the calculating any affecting aspect on the surrounding. So I was I am motivated to find the flame characteristics, but to conduct experiments for the large pool fires on this is very difficult, because it requires it is related to many pollution aspects and requires costly equipments, measurement devices, and it also requires large space. So I'm motivated to find this all the characteristics using some modeling technique. So for the analysis of any combustion modeling, 5 modeling techniques are available, that is point source model and solid flame models and field models, integral models, and zonal models. Among all the models, for field models are the mostly more accurate for the analysis of any combustion problem. So field models are is also known as CFD models, where detailed local information of velocity, temperature, flame characteristics, combustion phenomena is obtained. So my objective is to develop and validate detailed pool for CFD model and apply it to predict the CFD flame characteristics. So these are the equations which I have solved for the analysis of the pole fire. Who used a standard K epsilon and 4 different turbulence model used for the validation, and followed by got standard K epsilon model is performed well with a non-premixed combustion model. For solving any CFD problem, validation is mandatory to see our methodology is that correct or not. So I have considered the same which is already done by Vasant et al. In 2013. So I have implemented 4 different turbulence models and using 2 different radiation model with non-premixed combustion model. I have also considered the burning rate which is given by Chartis et al. 2001, and for the same fuel and flame who considered for the validation maximum temperature measured by Castle et al. 2013. So I have analyzed using two-dimensional diesel pole fire having 165 meter length and 100 meter height of a 3 meter diameter of the pole size. So it was found that and discrete ordinate radiation model with standard K epsilon discrete ordinate radiation model with standard K epsilon turbulence model using a non-premixed combustion model is performed well. So the same methodology I have of the pole fire, and for the detailed analysis of the pole fire I have considered Linatal experimental setup, and with respect to that only I have created same mesh using ANSYS measure only with good properties of mesh. And these are the operating conditions. The operating operating condition 0.0 meter per second to 6 meter per second inlet air velocity in the interval of 0.5 meter per second, and the fuel inlet with 0.02 meter per second of size 0.1 meter, that is 10 centimeter, and the outlet boundary conditions all sides are given as 0 absolute pressure conditions of and 300 Kelvin. So I have also done the grid independence test, and I have only done for the single simulation with the 3 meshes, and it was found that there is no larger difference in the results, but there is a larger difference in the number of nodes. That's why I have considered the less number of nodes to decrease computational time. It will lead to the computational decrease in the computational cost. That is mesh 2. And for the analysis I have considered the plane which is going through the middle of the air inlet as well as fuel inlet, and I have also considered the ISO clip at 550 Kelvin to measure the length of the drag of the flame, and to measure length and height of the flame considered ISO clip at 900 Kelvin. Accordingly I have used the same for all the remaining. And the flame length, as velocity increases, the flame length is increasing up to 4 meter per second. After that it is decreasing. It is because of the forward position of the air increasing, and which is dominating the, and it is trying to increase the dispersion rate of the fuel. And as we are considered at 900 Kelvin to measure height length of the flame, that's why it is decreasing. And as well as the flame height also decreasing continuously as increasing up. And the flame drag length, it is related to the buoyancy and viscosity and inertial forces from the up to 4.5 meter per second. As air increases, air velocity increases, the drag length increasing. After that it is start decreasing, and after that is constant. It is also the same. The buoyancy forces and inertial forces are overcoming the base drag that is coming from the viscosity, that is a boundary layer related. So, and after that flame tilt angles accordingly calculated from all that. This is the flame temperature contour by taking the reference for all the like images at 800 500 850 Kelvin for all the temperature contours, and it can be easily seen that as velocity increasing, the flame length is increasing, flame height is decreasing, and followed by the dispersion rate is increasing, but as we are measuring with the temperature at 900 Kelvin, that's why it is decreasing, length is decreasing. So the conclusions and the detailed analysis of industrial purifier is done using ANSYS Fluent and using discrete ordinary radiation model and non-premixed combustion model, standard capsule model, and having a maximum error of 6.6%. These are my references. Thank you.
So thank you, Mortada Srinivas Rao, for your nice presentations. Again, it's open for question answering. We will take only 1 or 2 questions from the audience.
Hello, sir.
Hello.
Hello, am I audible to you?
Yeah. Tell me, sir.
Yeah, shall I ask you a question?
Yeah. You can ask me.
Yeah, am I audible?
Yes.
Yes, sir.
Yes, sir, you are audible.
Yeah, just one. Some typos is there for the momentum equation. One plus sign should be there in the left hand side. Please check.
Yes, sir.
What's about whether you consider compressible flow or incompressible flow?
Sir, incompressible flow. Actually, I have not included like in that equations.
Yeah, then again in the continuity equation, please, there is some minor mistake. Please, there is a typo that rho term should not be included in the continuity equation. Verify.
Yes, sir.
And what's about the outlet boundary condition? Consider zero absolute pressure or zero gauge pressure?
Sir, atmospheric pressure, sir. It is like atmospheric pressure.
Then it should not be zero absolute pressure. It should be zero gauge pressure.
Yes, sir. Zero gauge pressure.
Yeah. Otherwise, it's a nice presentation.
Sir, I have few questions.
Yeah. You can ask me, sir. Yeah, you can ask me.
Yeah, am I audible to you, sir?
Yeah. Tell me.
Yeah. In your validations, you have done with a diesel pool fire with 3 meter. Am I correct?
Yeah. I have done with diesel pool fire meter, 3 meter diameter, and
yes, I read that. And that is the liquid fuel diameter. How your validations are being justified with the current study you have done? You have performed the validation with 3 meter diameter.
Yeah.
And your present work is related to 0.1 meter.
No, actually, that 3 meter diameter was that is 2-dimensional one. By considering a line, by considering the same computational work which is performed by Vasant et al. In 2013.
Yeah, understood. I have gone through your paper, but you are not using same diameter here. You have performed validation with some diameter, and your present work is related to some other diameter. And one more thing, you have used flame-based drag isoclip 550 Kelvin, and for flame height, you are using different isoclips. Why it is so?
Sir, actually, while we are measuring through infrared cameras, they were like linear experimental setup. While they were conducting, they were measured by considering by adjusting the temperature in the infrared camera at that same temperature only. That's why I have taken at the same temperature, and I have considered for all the simulations like 0.5 meter per second to 6 meter per second.
That's what I'm asking. Your flame drag, one isoclip for flame drag and one isoclip for.
Yeah, actually, I have done that same work experimental work done by Lin et al. 2019, and they were mentioned that while calculating this flame drag length, base drag length 515 Kelvin, they were considered for the calculation to measure the length, flame base drag length, and to calculate length and height of the flame, they were considered 900 Kelvin.
So there is no particular explanation regarding that from your side. Just they have followed those kelvins and symbols. Sorry, particular changes you have taken those. And one more thing, you have validated your simulations with liquid purifiers and you are using gaseous purifier in Popine with constant fuel supply rate.
Yes, sir. It is that Casalettel given that like performed experiments. They were given that like burning rates. At the same burning rates I am giving here.
Okay, and one more last question. You have validated your case studies with using maximum temperatures, not with temperature trends. I suppose it should be matched with temperature trends. The validation should match with temperature trends, not with maximum temperature.
Actually, I'm sorry. I have not mentioned here. I have also taken a line which is on 10 meters above the ground. Okay, and I have compared that one also, but that validation because of this phases, no, I have not mentioned here.
I suppose it should be validated with temperature trend, not with maximum temperature. Anyone can achieve maximum temperature, but trend achieving is important thing in validation cases.
Yes, sir. Yes, sir.
But you have shown that I have got 1400 Kelvin maximum temperature, so my validations are correct. How it can be justified?
No, sir. Actually, I have compared with the velocity as well as at 10 meters height at length. Also, I have taken for the validation, and I have also done grid independent test using the like 4 different turbulence model, and I have not included here, and also implemented different turbulence models also to see the behavior.
Okay, and regarding that isoclips, you are saying that wrong thing that you are attributing to this explanation Lin et al. That is not Lin et al. That is Vasant et al.
No. Actually, Vasant et al. 2013 Vasant et al. done on what this one diesel purifier. This Lin et al. is recently done experimental setup that is 0.
Vasant et al. Has not performed any experiment. They are simulation guys. Okay, they are simulations. Okay, so they performed this isoclips at the range of 900 Kelvin. But you have taken, you are supporting that Lin et al. Has performed. Lin et al. Has not used any IR camera in their experiments. Before this presentation, I have gone through your back.
Actually, I have.
That explanation clip is actually this much. This is like this. At 323 Kelvin, you can see proper flame heights. So for that, you are using around 600 Kelvin flame clip. But regarding this flame height and the drag, that 900 Kelvin, you are saying that less than 900 Kelvin, not range. So that is the wrong thing. I have been using. Sorry. Please.
Sir, can you 1 minute? 1 minute. I have contacted that Lin et al. That journal paper, that guys, and they were supposed to be like if you are fixing some temperature for particular measurement like flame height or flame length or whatever, you have to continue for all the
Yeah, that is the crux of this work. You have to fix some temperature. The basic. How can you fix that particular temperature? Saying that 550 Kelvin.
Sir, if I am maintaining different temperature for at different velocities, then it will be problem. Like if I am maintaining at constant, like as we cannot use here like IR camera and all. No, in like to simplify that, and I have taken basis as these 2 temperatures for the measurement in all the simulations.
Yeah. One more thing, you can't fix the temperatures of the flame. You can't fix that by for a particular propane gas flow rate. The temperature and velocities rate, temperature will change. You can't fix the temperature. That is not in our hand. Okay, temperature we are output variables. Those are output variables, not input variables.
Yeah, and also the temperature only affects like 1 minute, sir. And my study on like my final goal is to like study on the heat flux, that is safety distance, which is entirely related to the temperature only. That's why I played with temperature here.
Yeah, that's what you are not giving temperature as input condition. You are measuring the temperature. That is output variable, not input variable. Okay, with different crosswinds, the temperature also changes.
I'm sorry, 1 second, please.
For a particular crosswind velocity, temperature also changes.
That is depends on the diffusion rate by the forward pulsation by the air only. That's why I have taken that's why that flame length also increasing continuously up to 4 meter per second, and followed by it is decreasing as I have considered 900 Kelvin, because the diffusion rate is very high at high wind velocity. That's why.
Okay. My final comment is that simply one thing. Your validations are different. Your present work is different. You have validated with some diameter and some liquid fuel and some maximum temperature, not with friends. And your
I will
present,
not mention it.
your present work is with gaseous fuel, small diameters, and fixed mass flow rate. That's what your validations are different. Your present work is different. Your validations are not anymore. Thank you.
Sir, let me, sir, 1 minute, sir. Let me clarify. Actually, pulper happens after from the liquid, liquid directly it will not burn. First it will vaporize, layer by layer material vaporize. Okay, after that combustion process occurs when some external heat aid come into contact with that. Okay, that's why.
But it will change with respect to time. It follows three trends: growth period, steady state period, decay period. Yeah, I have been working in the pulper area for 4 years from IIT Dharwad.
Okay, I'm working from the last 2 years in this area only, and I have contacted with that Linetel also, and they were proposed me to do to fix 2 temperatures, and also
Again, you are saying you are fixing the temperature. You are measuring the temperature from the shell socket.
Yeah, by fixing temperature, I'm just measuring for the all contours. If I'm if I'm applying the different temperatures at different wind velocities, then it is problem.
That's my problem. Fix.
Yes, sir.
Just we have to wind up since the next session will start immediately. So once again, thank you. That's we can discuss it later on. Okay. Once again, thank you all. That's a presenter and the audience. And I'd like to thank the organizer, especially to Professor Amadesh Salar, for giving me the opportunity to chair this session. So Santanu, we'll stop here right now for this session and let it be started by Professor Dhiman. Okay.
Thank you, Professor Pati.
Yeah.
Now we move on to the next session of computational gas dynamics. This session will be chaired by Professor Amit Dhiman from IIT Roorkee. Over to you, Professor Amit.
Okay. Good afternoon to all of you. So we are having 5 papers in this session, and I think we are already late. We'll start. So first presentation by Birju Naik Yagnik, Ramesh Bhornia.
Yes.
So who will present here?
It's me, sir, Birju Yagnik. Am I audible?
Okay, so you will be talk about on effect of 4 body shapes on the hydrodynamic characteristics of axisymmetric boundary layer.
That's
right?
correct, sir. That's correct, sir.
So you are having 10 minutes for your presentation and 5 minutes for the question answers. So please stick to the time. Thank you. Start.
Sure, sir. Sure, sir. Hello, everyone. My name is Birju Yagnik. I am the presenter of this paper. Along with Ramesh Bhorania, I authored this paper named as Effect of 4 Body Shapes on the Hydrodynamic Characteristics of Axisymmetric Boundary Layer. My paper ID is FMFP 2020-087. So let's start with introduction. This paper presents the effect of the axisymmetric 4 body shapes on the hydrodynamic characteristics of axisymmetric boundary layer. The development of the viscous boundary layer on the near edge of axisymmetric body start from the stagnation point as a steady laminar flow growing in thickness along the streamline direction. Suction over the hydrodynamic characteristics like this and shear stress. Objectives. What are our objectives? We considered 3 basic shapes for the forebody. One conical, second parabolic, and third is the elliptical shape. And we will study the effect of the boundary layer characteristic like velocity profile, shear stress, drag force, etc. We have studied the effect of the forebody shape along with the variation of fineness ratios. TFT analysis. To study the effect of different forebodies on the hydrodynamic characteristic of axisymmetric boundary layer, we have taken the variations like this. The second will be fineness ratio FR. FR of the bodies are taken as 2 and 6, which is 2000, 4000, 6000. Here Reynolds number is based on the inlet velocity. And the fourth percent, 4 cases of the uniform is applied, and this percentage are of inlet velocity. Total number of cases for the study will be 27 as shown here. The variation of the different forebody shape, different FR and Reynolds number is shown here. Problem formulation. A circular cylinder with a radius, body radius A is considered in a stream of an incompressible fluid. 3 different forebody shape named as sharp cone, paraboloid or ellipsoid will be considered for the to study the effect of hydrodynamic characteristics. As we know that the ratio of forebody length to the diameter is known as FR, and the inflow velocity component is parallel to the axis of the cylinder, hence the base flow is axisymmetric. The fluid taken here is incompressible with density and kinematic viscosity. The velocity and the linear dimension are normalized with the free stream velocity u infinity and the cylindrical radius a respectively. Reynolds number is defined for the flow is computed as the given equation. The various forebody shapes defined here: the sharp cone, the parabolic, and the ellipsoid shape, along with the origins x and y coordinates in x direction and the radial r direction. For an example, I have shown the shapes with fineness ratio of 6, as fineness ratio is the length to the diameter ratio. The boundary condition are given as origin as will be here, and the forebody shapes, the main body, and all the region around here. We have applied axis boundary condition here, inlet boundary condition, velocity inlet boundary condition. There is the free stream boundary condition and the outlet pressure outlet boundary condition. We have calculated the grid independence test for 2 different locations as 0.5 and 0.12, and another location is 1.5, 0.12. So for the different grid size 1001 and 125, 2001 and 225. We have calculated the value of axial velocity, radial velocity for both the locations, and then calculated the percentage error, that is the change between these two in percentage. So we have found that this grid size having the minimum amount of the error in both of the velocity profile and both of the different locations. So we have taken that 2001 and 251 as the ideal grid size for our meshing and the calculation purposes. Results and discussion. The following study is the comparison between 3 different forebody shapes, which are cone, ellipse and parabola. With the same fineness ratio of 2 and Reynolds number as 2000, the graph which are coming following will show the various velocity profiles which is extracted from the MATLAB. Shows that the velocity profile has been significantly affected by the shape of different forebody. U versus R graph clearly deduces that in the case of sharp cone, the velocity profile is a flat type profile, whereas for the case of ellipsoid, it is fully developed. V versus R graph shows that the radial velocity V for all the 3 of the shapes will be higher in the sharp cone and lower in the ellipsoid form. From the graph, we can understand that the conversion of the axial velocity u into the radial velocity v is maximum in the case of sharp cone shape, while it is having minimum in ellipsoid shape. It suggests that the streamwise variation is base flow. Thus, the clear observation from the figure, it is observed that the radial velocity v increases at the expense of axial velocity u in the highest in sharp cone shape, while it is the lowest in the ellipsoid shape. This one presents the graph of du by dr versus r and du by dx versus r for the Reynolds number 2000 and three different body shapes. Now this graph of du by dx versus r graph suggests that the change in the axial velocity with reference to the x direction x-axis is higher in sharp cone shape, while it shows the lower value in ellipsoidal shape. So from the above figure, du by dx versus r figure, we can say that the axial velocity decreases at the lower rate in case of ellipsoid shape, while it decreases at a higher rate in case of a sharp cone. This graph, dv by dr versus r graph, suggests that axial velocity u with reference to radius r decreases at a higher rate in case of sharp cone shape for body. That suggests while using the sharp cone shape for body, the fluid flow is non-parallel, which means at the same location we got different velocity while moving towards the radial direction. These results will be helpful in the further studies of the shear stress and drag force. The graph plotted here demonstrates the local value of shear stress over the cylindrical main body area. All the values are in non-dimensional form. This figure shows the comparison of shear stress for various Reynolds number for ellipsoid for body shape having fineness ratio of 4. The effect of increasing the Reynolds number eventually increases the shear stress for the case. The viscous drag force also increases while increasing the Reynolds number. This graph shows the comparison of shear stress for various fineness ratio for ellipsoid for body shape having Reynolds number 2000. The effect of increasing the fineness ratio eventually decreases the shear stress for the case. The viscous drag force also decreases when increasing the fineness ratio. This figure represents the comparison of shear stress for the various four-body shape for fineness ratio 4 and Reynolds number 2000. The maximum shear stress occurs at parabolic four-body shape, while the minimum shear stress occurs at the ellipsoid four-body shape. The uniform suction effect will be introduced. The uniform suction is applied over the main body is taken as 2.5%, 5%, 7.5% and 10% of the inlet velocity. The uniform suction has significantly affected the shear stress and the viscous drag force over the length of the main body. A detailed comparison study has been carried out and found out that the case with the non-suction has a lesser shear force and a viscous drag force spread over the entire length of the main body, while increasing the percentage amount of the uniform suction eventually increases the shear force and the various viscous drag force simultaneously. This figure shows the effect of applying uniform suction over the main body. The graph represents the axial velocity u varying with the in radial direction for various suction cases. The comparison shows that the increasing in the suction amount, boundary layer is compressed over the body, increasing the viscous effect between the layers of the flow. Besides, it also suggests that the flow over the body gets shrink gradually with the increment in the suction percentage. This graph shows the behavior of the four-body shape over the inlet flow when the uniform suction is applied. This figure represents the effect of the uniform suction over the du by dr versus r graph. The result suggests that increasing the suction percentage will decrease the rate of change of axial velocity in the radial direction. This graph helps deduct the nature of the shear stress and viscous drag force. This graph is comparing suction and non-suction cases. This figure shows the shear stress comparison for the uniform suction and non-suction cases over the length of the main body. It concludes that for non-suction cases, the shear stress is lesser. As we increase the percentage of the uniform suction, the shear stress also increases simultaneously. Thus, the uniform suction affects the shear stress of the main body by increasing the shear stress. This graph shows the viscous drag force comparison for the uniform suction and non-uniform suction cases over the length of the main body. It concludes that non-suction cases for the viscous drag force is lesser. As we increase the percentage of the uniform suction, the viscous drag force also increases simultaneously. Thus, the uniform suction affects the viscous drag force of the main body by increasing the shear stress. Thank you so much for your attention. Myself, Birju Yagnik, along with Ramesh Baronia, signing off. Thank you.
Okay, please, Birju Yagnik, thank you
Yes,
very
sir.
much for your nice presentation.
Yes, sir.
So I will ask audience now for some questions. If audience has some questions, please ask. Okay, I think I will take some questions. So first of all, about your presentation. So in various slides, I can see that some informations are missing. For example, if you just see grid independence result.
Yes, sir.
So it is, if you just go to the grid independence test, slide number 12.
Yeah.
So I cannot see at which Reynolds number you have performed that study.
Okay, sir. Yeah.
Okay. And similar such type of mistakes, or you can say the over seen happened at various slides.
Okay.
Okay.
Yes.
What is the significance of this fitness ratio?
Fitness ratio? Hello?
You have defined FR, fitness
Yeah,
ratio.
it's fineness ratio, sir.
Okay, sorry, I'm sorry. Fineness ratio. What is fineness ratio?
Yes, sir. Fineness ratio is actually practically defined as the length divided by the diameter we have taken as a four body shape. And for the numerical purposes, for the effect of the FR is calculated, and that is why we have taken this 3 FR in order to study the effect of FR over the drag force.
If I consider FR as 1, then what will happen?
It will behave near to the blunt the shape.
Okay. So you have considered 3 situations.
Yes, sir.
So among 3 shapes, which is the best and why?
Among 3 shapes, sir, according to my results, the ellipse shape is best shape according to my results because it shows the very minimal amount of the drag force over the length, over the entire surface body, and the higher the fineness ratio, the better it one will be.
Okay. So those are my questions. So now we can take up 1 or 2 questions from audience. Okay. Okay,
Yes.
thank you,
Thank you
Birju
so
Yagnik.
Yes, thank you so much, sir, for giving me such a wonderful opportunity, sir. Thank you so much.
Thank you. You are most welcome. Thank you. Now we come to the second presentation of the day. Uttam Singh Rajput.
Yes, sir. Yes, sir.
Krishna Mohan Singh.
Yes, sir.
Okay, so you will talk about a modified alternative weighted essential non-oscillatory scheme for inviscid compressible flow.
Yes, sir.
So you are having 10 minutes for the presentation and 5 minutes for the question answer. Please start now.
Yes. Hello, everyone. Myself, Uttam Singh Rajput, and my topic of the presentation is a modified alternative weighted essentially non-oscillatory scheme for inviscid compressible flow. This is the present outline of the work: introduction, governing equation, numerical flux evaluation, modified alternate value scheme, the present scheme that we have developed, numerical results, and the references. Now, introduction. This work is related to development of high order shock capturing method. As shown in the figure A, As you can see, there's supersonic flow over an aircraft. There are oblique lines. These oblique lines are basically the discontinuities. These discontinuities can be a shock wave, can be a rarefaction wave, and can be a contact discontinuity. Similarly, in the figure B, there is a four-body diagram of an aircraft. There is a highlighted portion, which is the air breathing system. The enlarged view of the air breathing system is shown in the figure C. There are three parts: diffuser, burner, and nozzle. As you can see in the diffuser, there is a zigzag pattern. This zigzag pattern is basically the shock wave reflection. Now there is also shock boundary layer interaction occur inside the diffuser. So this complex physics and phenomena is difficult to measure experimentally. If we model the conservation equations or the PDEs by using some high order shock capturing method, we can easily predict the complex physics inside these phenomena. Now governing equation. Two-dimensional form of inviscid compressor flow is shown in equation 1, where U is the conservative variable, E and F is the convective flux or the numerical flux, where E and F are further dependent on this conservative variable reconstruction. Our work is related to the reconstruction of this conservative variable. Now discretized form is shown in the equation 2, and for the time advancement we have used third order TVD, total variation diminishing third order Rangakutta method. Numerical flux evaluation. Consider one-dimensional form of Euler equation where V is the conservative variable and F is the convective flux, which is a function of the conservative variable. Discretized form is shown in the equation 4 where F bar I plus half is the approximated numerical flux. Now Schumacher has proposed alternative form of the approximate numerical flux using Taylor series expansion as shown in the equation 5. Now for P is equal to 3, the fifth order accurate approximate numerical flux is shown in equation 6, which contained Fi plus half, which is the convective flux, then second and fourth order derivative. The second and fourth order derivative is evaluated using the center difference schemes, and Fi plus half is evaluated using one shock capturing method. Now second and fourth order derivative of the approximate numerical flux is shown in the equation 7. Now Fi plus half, the convective flux evaluated using HLLC shock capturing method as shown in the equation 8. Now this in this shock capturing method, the numerical flux is separated on the basis of the type of the discontinuity, that is if it is a shock wave or rarefaction wave or contact discontinuities by using these wave speeds. S minus is the left wave speed and S plus is the right wave speeds and S star is the intermediate wave speeds. Now one of the drawback of this shock capturing method is they are first order accurate. In order to increase the accuracy of the shock capturing method, we need high resolution scheme which is incorporated in this shock capturing method, and the complete method is known as high order accurate shock capturing method. In this work we have proposed modify alternative Vano high resolution scheme which is used with the shock capturing method. In the proposed scheme, the reconstruction of the left F minus and the right F plus states of the numerical flux is based on the primitive variable, that is U and P, rather than the conservative variable. Now the conservative variable component produces spurious oscillation in pressure and velocity field as compared to the primitive variable U and P. This is the reason is due to that the primitive variable are much more closer to the characteristic speeds of the compressible flow, and they provide a consistent reconstruction among the continuity, momentum and energy equation. Now to describe the reconstruction procedure, let us consider smooth scalar function Vx, and the left reconstruction value of Vi plus half is shown in equation 9. Note that the procedure step required to evaluate the Vi plus half is directly applied to the left reconstructed value of the numerical flux F minus and symmetrically applied to right reconstructed value F plus of the numerical flux. Now I shown the equation 9, it is a combination of the three substances 0, 1 and 2. So it is a dynamic combination of the three third order polynomial which make the Vi plus half as a fifth order accurate. This is the magnitude of the V1, V0, V1 and V2 based on the three substances. Omega naught, omega 1 and omega 2. For omega k is basically the non-linear weight which is dependent upon the smoothness indicator beta k. Dk and epsilon are the constant value. Dk is as shown here and epsilon is taken as 10 to the power minus 6. Now beta k is the smoothness indicator which is depend on these substances, substantial 0, substantial 1 and substantial 2. Now more the value of beta k, if there is a discontinuity, then in that stencil the beta k value will be large. Similarly, therefore the non-linear weight omega will be small. So that stencil will be discarded and the numerical flux is evaluated on the basis of other smooth stencil so that the smooth solution should proceed. Numerical results. We have taken 3 test cases, 3 one-dimensional test cases and 2 two-dimensional test cases, and also compared the computational efficiency of two-dimensional test cases. One-dimensional accuracy states that consider one-dimensional Euler equation as shown. We have compared the proposed scheme M105 with the other 2 high-resolution schemes. The computation will perform up to time t is equal to 2, and we have evaluated L1 error and convergence rate RC. 105 is a traditional Venn scheme, and A105 is another high-resolution scheme based on alternative numerical flux. As you can see that all the 3 schemes are fifth order accurate, but the magnitude of the L1 error in the proposed scheme is less as compared to the other schemes. Therefore, our scheme is more accurate as compared to the other high-resolution schemes. Short test is also one of the standard test cases. As you can see that the amplitude of the oscillation is higher in other high-resolution scheme as compared to the proposed scheme M105, but the frequency of the oscillation is more. So this frequency of the oscillation can be further reduced if we use the different smoothness indicator in the present scheme. Shock entropy wave interaction is one of the standard test case to assess the robustness of the numerical method. In this, shock wave of strength 1.1 interacts with the high frequency oscillating density field, and as you can see that as compared to the reference solution is generated using 6000 grid point by using the present scheme. So the proposed scheme M105 is more accurate as compared to the 105 and A105 scheme. Gas dynamic problem is one of the standard test case to assess the fine scale structure. Now this is the initial conditions, and the zero gradient boundary condition is applied on the square domain of the problem. This is basically the results. As you can see that the proposed scheme M105 in the figure 5C is more accurate and capture the more fine scale structure accurately as compared to 105 and A105 scheme in figure A and B. The reference solution D is generated using high mesh resolution 1200 points. Now the forward facing size is one of the standard test cases. The reflecting boundary condition are applied at the top and bottom. The supersonic outflow boundary condition at the right, and at the inlet condition are continuously feed with these initial conditions. So as you can see in the diagram that the present schemes captures the flow physics accurately. Moreover, across the shear line there are more number of rollers, so it captures the fine scale structure or small roll-ups more accurately as compared to the other high resolution scheme. The reference solution is generated by using the higher mesh resolution point 1920 cross 640 mesh. Now comparing the computational efficiency or the computational time, so we can see that both the M105 and A105 schemes take the 10 to 12% more computational time than the traditional 105 scheme. The reason is due to the evaluation of additional second and fourth order derivative. But the M105 schemes take 3% less computational time than the A105 scheme. So therefore, we can say that our scheme is more robust and capture the fine scale structure accurately, and it is computationally efficient. These are the references. Thank you.
Okay, Uttam Kumar Singh or Uttam Kumar Rajput. Thank you
Yes,
for
sir.
a nice presentation. Okay, now we are having some time for the questions. Audience, if you have any questions, please ask.
Uttam Kumar Singh, I'm Dhaval here.
Yeah,
So
yes, sir.
I have one question. That whatever the reference solution you have shown, whether
Yes,
that is
sir.
generated by you or it was taken from some reference.
Sir, it is generated by the present scheme on higher grid resolution. It is
So then if
generated
we
by
consider
me.
the
It is generated by me only by using the same scheme, the present scheme.
so okay, here we have seen that most of the whatever the comparison is there with a high resolution scheme and your scheme and whatever the reference solution you have
Yes.
generated. Whether
Yes.
any experimental validation you have complete done with the.
Sir, these are only standard test cases. Actually, one-dimensional cases that I have discussed, that reference solution is the exact solution. And the two-dimensional cases, their exact solution is not available. And I have not shown any result related to in which experiment is performed. For example, full Navier-Stokes equation flow over a flat plate. Then I can have incorporated that result. But here only the standard cases are result, because I can only either compare through more high resolution scheme or more fine mesh point. There is no experimental validation for these results.
Okay.
Yes.
Okay, Dhaval, thank you very much. Now we can take one more question from the audience. Uttam,
yes, sir.
I have one question for you.
Yes, sir.
You benchmarked or validated your methodology with the standard means problems, 1D
Yes, sir.
problems or very simple problems, or you can say this is the question continuation to Dhaval.
Yes,
so
sir.
now the question is, can this methodology be applied to the three-dimensional problems?
Yes, sir. Even this is basically in order to check that, for example, gas dynamic problem is a standard test cases for compressible turbulence. If I solve turbulence full-fledged problem on a turbulence, then it can capture the fine scale structures. So this scheme is formulated and it can be applied to three-dimensional and any compressible turbulence problem.
Have you applied to 3D problem?
I have applied to two-dimensional problems. 3D is in process.
So how you can say that it will be applied to 3D, because you have not applied?
But the other schemes from which I have compared, like Vano 5 and other alternative, they have applied to three-dimensional. So if it is accurate in two-dimensional cases, so it probably have good result in 3 dimensions.
Okay, thank you very much.
Yes, sir.
And I also can ask one more questions. At various locations you have utilized fifth order, third order, so many orders you have explained in your methodology,
yes,
but you have not explained why you have utilized it and what the lesson will audience will take from this presentation.
Sir, basically this Vano reconstruction procedure is rather than using the five points mean fifth order accurate, it's a big stencil. So instead of if you want accuracy fifth order, in this Vano scheme 3 substencil is used. That's why
Uttam, I am not saying that. You
Yes,
have to
sir.
explain why fifth order. I am suggesting, let's say you take 10th order.
Sir, if we increase if we increase the order of accuracy, then there is a chances of numerical oscillation will be produced in the solution. For example, if you talk about boundary condition points,
Again,
we cannot.
you are superficially saying something. Do you have any explanation with the literature? What are you saying?
Sir, in literature, till 11th order schemes are made and they have been applied. I have only taken 5th order accurate. We can go
That's
to
why.
7th and 9th.
That's
Yes,
why
sir.
I am asking why fifth order? Why not 11th or 12th? That was the question.
That can be a further future work, sir.
Okay. So, okay,
Yes.
now finally, thank you very much for the nice presentation, and please
Yes.
incorporate these suggestions if it all possible. Thank you very much.
Yes,
Now you
sir.
please log off
Thank you, sir.
or stop sharing. That's all. Be
Yes,
present
sir.
in the presentation.
Yes, sir.
Okay. Now we are having third presentation by Anup B. Mangarajuna Rao P. Both are available.
Yes, sir. I am Anup here. I am available, sir.
So who will be presenting? Anup.
Myself, Anup. Yes, sir. Yes, sir.
So Anup will present on simulation of sodium vapor transport in cover gas volume of reactor vessels.
Yes, sir.
So
Good evening,
Anup,
sir.
you are having 10 minutes for the presentation and 5 minutes for the question answer. Please start now.
A
Thank you,
warm
sir.
welcome to all. Myself, Anup. Today I am going to present simulation of sodium vapor transport in cover gas volume of reactor vessels. This study I have carried out under the guidance of Dr. Mangarjuna Rao, Homi Bhabha National Institute, Indira Gandhi Center for Atomic Research, Kalpaka. Sodium-cooled fast breeder reactors uses liquid sodium as primary coolant as well as secondary coolant. In a reactor, the most important sodium capacity is the reactor vessel itself, where the molten sodium in a cylindrical vessel is topped with the inert cover gas, which is argon usually. And the sodium temperature varies from 200 degrees Celsius to 550 degrees Celsius under various operating conditions. While where the warm roof concept is followed, the roof is cooled and maintained at around 120 degrees Celsius. The heat and mass transfer in a cover gas space is complex in nature. Due to the temperature difference between the sodium surface and the roof, there is a buoyancy-driven convective natural circulation in the cover gas space. So, convection and radiation are the two major modes of heat transfer from liquid sodium to the roof. Whereas mass transfer is concerned, the formation of sodium vapor and sodium aerosols in the cover gas, their transport in the cover gas and deposition on various component surfaces. These are the important aspects. The behavior of sodium vapor and aerosols in a cover gas space are associated with multiple physical phenomena and the intricate geometries you have seen in the cover gas space. In this present study, a numerical model for transport of sodium vapor in cover gas was developed. Basically, evaporation of sodium vapor from the pool surface into the cover gas is transport to the roof and finally condensation on the roof were modeled. The sodium pool surface temperature varied from 250 degrees Celsius to 550 degrees Celsius for various cases of study. And the roof temperature was maintained at 120 degrees Celsius for all the studies. The computational domain consists of the cover gas space, which is cylindrical shell of 600 millimeters diameter and height 200 millimeters. Axisymmetric model was taken for the study. The Rayleigh number for the present study varies in the range of 10 to the power 7. Hence, it is concluded that the flow regime is turbulent since the Rayleigh number is more than 50,000 for the case of a typical Bernard convection cell. Among the various turbulent models, first option considered was the standard K epsilon model with the standard wall function. But this requires wall y plus wall is above 15, so we have to go for a coarse mesh, which is not preferred here. Other model was transition simulation using SST K omega turbulence model. But this was almost converging, but giving an oscillation over the time steps. The third model considered was the transition simulation using RNG K epsilon model with enhanced wall treatment. This was again perfectly steady state converged solution. So it was adopted for the further studies. These are the governing equations used for the numerical solution. This is a continuity equation. This is a momentum equation for the turbulent flow. Since our problem is species transport This is a conservation equation for the convection deficient species. In terms of mass fraction of each species, that is Yi. So in this equation, Ri is a production of species by chemical reaction and Si is a source term. Both are 0 in our present case. And this diffusion term of the species is given by Ji, is a diffusion flux of species I. This is due to gradients of concentration as well as temperature. So defining the Ji, this is a term due to concentration gradient. This term is due to laminar part. This is due to turbulent part. And this term is due to the gradient in temperature. So in energy equation, additional term is coming because of species. That is this term due to the transport of enthalpy due to species diffusion, which is accounted in the energy equation. In case of the computational model used is that two-dimensional axisymmetric model with the quadrilateral cells were used. At boundaries, finer meshes were used with the vol y plus values around 1. Species transport and reaction module of aegis fluent is used as a computational tool. So the cylindrical wall around the cover gas space is modeled as insulated so that no heat flux and mass flux passes through this wall. So in addition to convective heat transfer, radiation heat transfer also is there, which is modeled by the surface to surface model. So the sodium vapor transport is established between the sodium pool surface and roof of due to concentration difference. So this rate of vapor transport is decided by the natural circulation established in the cylindrical cavity due to the temperature. This is a computation grid used. Here is the cover gas space. This is the central axis of the axisymmetric model. This is the side shell wall. This is the bottom sodium pool surface. Here is the top roof plate. So this bottom sodium pool surface and top roof plates are maintained at the temperature boundary conditions. The sodium vapor mass fraction at the boundary condition given at the bottom sodium pool corresponding to the vapor pressure corresponding to the temperature of the pool surface, and that sodium vapor concentration at the roof plate is decided based on the temperature of the top roof plate. So there are user-defined functions were used in this study, incorporated with the ANSYS fluent, that is for specific heat, conductivity, viscosity, and diffusivity. In addition to that, the boundary condition of sodium vapor mass fraction, the sodium surface and roof were also modeled using the user-defined functions. So these are the correlations used for the properties. This is a specific heat of sodium vapor, that is the exponential correlation is given. This is saturation vapor pressure at the specific temperature. This is a mass diffusive flux at the surface. And in a mixture of cover gas space, this diffusion coefficient is defined by this correlation. Now coming to the results of the transition numerical analysis. This case shown here is corresponding to sodium pool temperature of 550 degrees Celsius, and results are taken at the steady state at 150 seconds. So this plot corresponds to the vector plot. So we can see that a typical convective flow pattern is formed in this cell, similar to Bénard convection cells. So in lower temperatures or sodium pool temperatures, anti-clockwise flow pattern was observed, but at a higher temperature, sodium pools like 550 degrees Celsius and all, clockwise flow pattern also observed. So these are the temperature contour and sodium vapor species contours. Both are looking similar because both are following analogies. Now this is for comparison of the results. What I have taken is that to use the mass transfer analogy with the experimental correlation given by global Dropkin for heat transfer. It's a heat transfer equation. Similarly, mass transfer equation is used this one to find out the net convective mass transfer of sodium vapor from sodium pole to roof given by this equation. So this once the sodium vapor transport is found out using both the correlations as well as heat transfer also found out, and both are compared. So this is the variation of CFD results with the empirical correlations. So this is heat transfer, heat flux, and here it is variation with Nusselt number. Maximum variation is found to minus 15 to 21%. So variation in mass transfer. This is a sodium vapor flow rate and sodium surface. Here, this Sherwood number is compared with the empirical correlations. Maximum variation found was minus 10.3%.
Anup, please complete in 1 or 2 minutes.
Slide is to show that at a high temperature of sodium pool,
Anup,
the
please
contribution
complete.
of the overall heat transfer by the radiation is very
Anup, can you listen
Yes,
me?
sir. Will be. Yes, sir.
Complete in
And one
1
more
or
thing
2
to
minutes
note
maximum.
is that the
Yes, sir.
heat of
We'll complete, sir. Now.
transfer is very less, which is 4.4% of overall heat transfer at a sodium temperature of 550 degree Celsius. In conclusion, the results of the numerical model here is in good agreement with the empirical correlations available in the literature. So this validates the model for the transport of sodium vapor in the Fabregas space. However, in the actual scenario, the effect of sodium aerosols in the heat and mass transfer to be accounted separately. Open for.
Okay.
Yes, sir. Thank you,
Anup,
sir.
Anup, thank you very much for the nice presentation.
Thank you, sir.
Okay. You also have given your mobile number. Very good.
Yes, sir.
Okay.
For any contact, sir.
Now we can take up 1 or 2 questions from audience. Please. Audience, please ask questions. Okay, shall I ask questions now?
Yes,
So,
sir.
Anup, what are the limitations of this study?
Sir, this major limitation of the study is that in actual case, where is cover gas, this heat and transfer will be influenced by the presence of the sodium aerosols. So that sodium aerosols are condensation in the sodium aerosols, and that distribution of sodium aerosols, and finally carryover of sodium aerosols into the wall. Those things are not considered here. So that is one limitation of the study, because that is the next step I am going to study those phenomena. So other limitation is that, okay, I have done a 2D axisymmetric model. So that's to take into consideration of other effects like the cellular convection and all, 3D model I have to use. So this is a basic, to start with, this is a base study I have taken up this one.
Okay. So on one of the slides, 13, you have showed the deviation of your results with the literature. Okay. So deviation is too high. What is the reason for that?
Sir, okay. One reason will be this. My dimensions are because this literature value is applicable for a infinite. So this, in my case, this is a cylindrical cell. So that difference geometry and the that limits of the diameter. So that plays a role here to get the deviation from the literature.
So I think you just please correct this methodology so that you will be having very adequate or the very good match with the literature.
Okay. Yes, sir. Sure, sir. Yes, sir.
With these words, thank you very much.
Thank you very much, sir, for this
Please stop
opportunity.
sharing.
Yes, sir.
Questions.
Now we are having fourth presentation by Pagdar Dhaval Kumar, Ninish S. C. Suresh Kumar. So Pagdal
Yes,
Dhaval
sir.
Kumar.
I am Dhaval here. I am here.
So you will be presenting on thermal analysis of high pressure helium gas tank system during venting. Yes. So you are having 10 minutes for the presentation and 5 minutes for the question answers. Please start now.
My greetings to the FMFP participants and the organizations. I am Pagdar Dhawan Kumar, scientist in Indian Space Research Organization. Today I am going to present the thermal analysis of a high pressure helium tank system during venting. The co-authors for these publications are Manish S. and Suresh Kumar. Before going to the actual presentation of the thermal analysis, I would like to give a little introduction about the liquid rocket engine and why we need the pressurization system into the liquid rocket engine. Mainly the two types of a liquid rocket engines are there. One is the pressure fed piston and second is the pump fed system. The aim of both the systems is to maintain the constant chamber pressure. And if you want to maintain the constant chamber pressure, injection pressure should be maintained constant as well as the flow rate. So
Dhaval.
that in pressure
Dhaval.
fed system, the tanks itself are maintained at a high pressure.
Dhaval.
So the
Yes, sir.
directly
Yes.
supplied to the engine.
Please, I think he can increase voice.
More pressure. And to the help of the
Actually, sir, it is a autoplay presentation.
Okay, no problem, no problem.
supplied to the engine. But in both the case, the tank pressure should be maintained at a constant throughout the burn duration to meet the actual requirement of the engine. So to maintain the constant tank pressures, a pressurization system will be used. So there are various types of pressurization systems are available, but here we will discuss only the cold gas pressurization system. In cold gas pressurization system, a high pressure gas is stored inside the pressure vessel and is supplied to the tanks with the help of the regulators. In this case, we have numerically developed a model to predict the pressures and the temperatures of the gas in the gas bottles during the expansion throughout the burn duration of the tank. Now, as our point of interest here is the gas bottles, I would like to enlarge the view of the gas bottles and show the heat interaction of the gas bottle with respect to the ambient as well as the pressure in gas. So here the Pg and the Tg is the temperatures and the pressures of the gas, pressure and gas inside the gas bottle. Tv is the temperature of a gas bottle and Ta is the ambient temperature. The energy which is leaving out of the gas bottles is m dot Cp into Tg. There is heat transaction between the gas bottles and the ambient is the H out, A out into delta T. Delta T is the Tf minus Tb. Heat interaction between the gas bottle and the pressure and heat is H in A into Tp minus Tg. So here, other than the heat transfer coefficient, all the parameters are known at time t. So to estimate the heat transfer coefficient, maximum convection loss is being used. Nusselt number is equal to C into Ra raised to n. The coefficients C and the n's are derived from the literature based on the laminar regime or the turbulent regime. The literature here we have used is from the International Journal of Heat Transfer, which is published by the Winter et al. Now to derive the governing equation of the numerical model, we have divided this gas bottle into two controls. First control volume is the control volume of a gas, and the second is the gas bottle is considered as the second control. So now by using the conservation of energy and the mass, continuity equations and the energy equation which is derived, which shows the rate of change of mass of the gas inside the pressure and gas and the rate of change of the temperature of the pressure and gas. And to consider the compressibility effect, ideal case law is used with the compressibility effect. Here the compressibility is Z is equal to 1 upon 1 minus B, where B is a coefficient 2.673 into 10 raised to minus 3. Similar way, the governing equation for the control volume of a pressure vessel is derived. dmB by dt is equal to 0, and the rate of change of temperature of the gas bottle temperature is mentioned here. And these whole equations are being solved by using the fourth order Runge-Kutta method. Now, before going to launch vehicle directly, to validate the model, a same experimental study which is published by the Winter et al. Is being used, in which it consists of two reservoirs. One is the supply reservoir and second is the receiver reservoir. The volume of a supply reservoir is 190 cc and the receiver reservoir is a 658 cc. And both the reservoirs are connected by the 40 having the size of a 0.5 watt angle. They have performed the three experiments. The first experiment, supply reservoir is kept at 300 psi. Second, it was kept at 3000 psi. The third, it was kept at 6000 psi. During the experiment, to maintain the constant outer surface temperature, it was being cooled by using the cold water inside the jacket of the pressure vessels. Now here we have shown a comparison of the experimental data, a net flow solver data which is developed by the Winter et al. And our solver data for all these three experiments. Figure A and the figure B shows the comparison of the pressures and the temperature inside the supply reservoir at initial condition of a 300 psi. Whereas figure C and figure D shows the comparison of a temperature in the supply reservoir initial condition of a 3000 and the 6000 psi. So by getting there is very good validation with respect to the experimental data or the net flow solver data, now we have move forward to apply the same solver for the launch vehicle pressurization system. Here the pressurization system is a pressure fed system as mentioned earlier. So the heat interaction diagram of the pressurization system is also shown here. It is the same as I have explained earlier. Initial condition of the gas bottle and the pressure and gas is mentioned here. Initial pressure is 30 bar absolute and the temperature is 25 degrees Celsius. Here a single pressure vessel is used, a multiple pressure vessel is used having a 34 liter initial capacity, and based on the mission it may be 2, 3, 4, 5 we will be using into the launch vehicle. The thickness of the pressure vessel is 8 mm and the diameter is 400 mm. And the working medium or the pressurized gas is the Indian gas. And as mentioned earlier, by solving the governing equation for the gas bottle as well as the pressure and gas, derived pressures and temperatures by using the model as well as the actual pressures and temperature in the flight which is measured by the probe inside the gas bottle is compared here in the two figures. You can see that pressures and temperatures are very well matching with the actual flight measured data. Now to understand the importance of a heat transfer, energy equation of the pressure and gas is rearranged and shown here. Here the rate of change of temperature is divided into the two parts. One is the term 1 which represents the rate of change of temperature due to the mass expulsion, whereas the second term is represent the rate of change of temperature due to the heat transfer between the pressure and gas in the gas bottle. So if we plot this both the term 1 and term 2 over the entire one duration, you can see that the heat transfer as well as the mass energy change due to the rate of change of temperature due to the mass expulsion, both are equally important. And by chance, if you would have neglected the heat transfer between the pressure and the gas bottle by using the adiabatic assumption, then the variation of a pressure or the entire one duration is shown by the blue line. You can say that marginal error would be produced if you would have assumed the adiabatic expansion throughout the one duration. Now, on the ground experiment, the heat transfer between the external as well as internal surface of the gas bottle are important. But in case of the space, the systems are operated around 300 to 400 kilometers above the Earth's surface when the atmosphere is very thin. So if we would have compared the Nusselt number at the internal and the external surface of the gas bottle with Nusselt number at internal surface in order of 400 to 600, whereas at external surface it is less than 1. So in the space, if you would have neglected the heat transfer at the external surface, then it would not produce any marginal error. Now, so in this experiment, we have generated a numerical model by using the conservation of the loads and the energies, and we have developed a numerical model by using the conservation laws of mass and the energy. And this model is validated with the open literature data and the ground experiment they performed by the Inter-8 course. And the same model is being used to predict the pressures and temperatures of the pressure and things inside the pressure ratio for the launch vehicle pressurization system. It gives a very good match with the launch vehicle data also. And also the budget of the rate of change of temperature shows the heat transfer inside the pressure and gas as well as the rate of change of temperature due to the mass explosion. Both are equally important. And if we would have neglected the heat transfer inside the pressure ratio, then it would have produced a marginal error, and as per our calculation, we would have overestimated around 17% of pressure and gas quantity required, and this would have cost around 10 kg of the payload mass. And each kg of payload mass in the payload mass in for the launch vehicle is cost 20,000 US dollars. So we all can estimate the amount of all can estimate the cost of the adiabatic assumption for the pressurization system if we would have assumed. Thank you.
Okay, Dhaval. Thank you very much for the nice presentation. So now we can take up one or two questions from the audience. Okay, Dhaval. I will ask one or two questions.
Yes, sir.
So have you considered two-dimensional study or a 1D study?
Sir, our main aim was to match our predicted data with respect to the whatever the flight measured data. And the flight measured data was just single probe. So that's why we have considered the one-dimensional study, and whatever the validation we have done, that was also one-dimensional studies.
So what deviation you got with the literature?
Okay. Compared to literature, that was a literature and their experiment for the one-dimensional study, it was exactly matching, and error was less than 2%. But if we compare actually whatever the volume, like 34 liter, as I said, and the literature volume was around in terms, it was a in terms of some 300 cc. So volume was different. So that's why if we, in case of our actual problem, there may be some temperature gradient, but here we are not interested much in the temperature. We are interested in how much quantity we can utilize for the pressurization system. So that's why that was our like can say limitation of this model. Like for a higher volume during the depressurization, there will be the temperature gradient that cannot be simulated by using these one-dimensional studies.
Okay. What numerical methodology you have used here?
Here we have used like a ordinary differential equation solved by the fourth order Runge-Kutta method.
Okay, so you solved which equation?
Like continuity and for the like as I have mentioned for finite by using the finite volume method, continuity and energy equation is derived for the gases as well as the gas bottle, and the heat interaction between gas and gas bottle is modeled by using the natural convection, that also I have mentioned in one slide. So that all four equations are all ordinary differential equation are solved by using the fourth order Runge-Kutta method, continuity and energy equation, and natural convection model, it is like a algebraic equation.
Okay, thank you very much, Dhaval. Thank you again.
Okay, thank you, sir.
Now please stop sharing. Okay, now we are having a final presentation of this session, and presented by KNV Adi Narayana.
Yes, sir, I am here.
And he will be talked about on numerical model for evaluation of single phase natural circular or natural circulation loop transients. Please start. Adi Narayan, you are
Yes, sir.
having 10 minutes for presentation and 5 minutes for question answers. Thank you.
Thank you. Very good morning to all. My name is Adi Narayana. I am working at Safety Research Institute, AERB, IGCAR campus, Kalpakam in Tamil Nadu. And today I am going to give a brief presentation on my recent work titled Numerical Model for Evaluation of Single Phase Natural Circulation Loop Transients. My presentation is outlined this way. I'll start with an introduction and followed by the mathematical model details and the validation of the mathematical model, and followed by the applications of the model, and finally conclusions. In the introduction part, as many of us know, single phase natural circulation loops have several engineering applications where the safety and high reliability are of paramount importance. So when we gone through the literature on single phase NCL's modeling, some observations were made. Those are listed here. The first thing is many of the models are based on finite difference method, and Basinski's approximation was used for density variation. Also noted that uniform heat flux at heater, constant fluid properties, that is viscosity, specific heat, etc., and isothermal heat sink conditions were considered. Also noted that very few authors have considered the wall conduction into the modeling of NCLs. Moreover, it is noted that a generalized numerical model for all heater and cooler configurations is still felt to be incomplete, so that has to be addressed. So with these things in mind, in the present paper, a generalized finite volume based numerical model to investigate the thermal and hydraulic characteristics of single phase NCLs with the different heater and cooler configurations is developed. So this slide shows the mathematical model details. The geometry considered for the model is shown in this figure. As we can see, the entire loop made into 12 sections, that is N1, N2, N3 and so on to N12. And these sections can be heater, or it can be a cooler, or it can be a normal wall. So that depending on the user input. And here one section is highlighted with oval shape. As we can see, there is a fluid inside and there is a wall, and this wall can take the heat, or it can give away the heat, or it can be as an insulator also. So these are the options available in the model. And comes to the governing equations. So the governing equation is shown in this slide. So mass conservation, momentum and energy balance for NCL fluid. That is the first three equations are for the fluid which is flowing inside the NCL. So the fourth equation, that is energy balance for wall. So that is a energy balance for the wall of the NCL. So here depending on the location, whether it is a heater section or a heat sink or insulation pipe, the energy balance is different. And the last equation is for the cooler, so which is the secondary side of the cooler. Like primary will be the NCL fluid and secondary will be the energy balance for the cooler. And these equations are discretized, and this slide shows the discretization followed. All these equations were discretized based on finite volume method. So the schematic of the grid arrangement is shown in figure 2. So this figure shows the nodes of the fluid as well as the node of the wall, and how the control volume and control volume features are arranged. So based on this grid arrangement, each governing equation is discretized. So here a sample of momentum balance discretization is shown in this slide, and a simplification of that discretized equation. And so the same manner, the remaining governing equations which was shown in the earlier slide are discretized in a similar way, and these discretized equations are solved with explicit time marching procedure. So once we develop this model, and this model was validated with respect to the 3 different experimental loops with respect to different orientations of heater and cooler configuration. So in the first case, that is case A, we have taken VHVC, that is vertical heater and vertical cooler configuration. So for this configuration, the facility taken from the literature by R.T. Dobson. So the figure is shown in figure 3. This facility made up of copper and glass, that is some part of the loop is made up of copper, some part of made up of glass. Here the objective is to simulate the mean velocity transient in the loop, also this sink tank temperature transient. So figure 4 and figure 5 shows the mean velocity and tank water temperature comparisons. So the present model and the experimental values and the results of R.T. Dobson model. So R.T. Dobson model is based on finite difference method. So from figure and figure 5, we can see that the predictions are good agreement with the experimental and numerical distribution of the experimental loop. The second case, that is case B, is HHVC, that is horizontal heater and vertical cooler configuration. So for this, the facility taken from literature is by Naveen Kumar et al. The facility is shown in figure 6. The total length of the loop is 7.23 meter. Basically, this is made up of borosilicate glass. So here our objective is to simulate the pressure drop across the heater, that is bottom section, and the loop mass flow rate transient. So figure 7 and figure 8 shows the comparison. Here we are having experimental results only for the pressure drop across the heater. So that's why we have compared figure 7, the present model predictions, Naveen Kumar et al. Model, and the experimental values. Whereas figure 8 shows the loop mass flow transients using the present model and the Naveen Kumar model. So these results gave the confidence that the present model is able to predict the flow reversals and steady state conditions quite well. And now the third case that we have taken is HHC, that is horizontal heater and horizontal cooler configuration. So for this, the facility taken from Divya et al. 2012, the facility is shown in figure 9. This loop is having 4.1 meter total length with 0.96 and 0.9 meter as heater and cooler lengths respectively. So here the objective is to simulate the temperature transients at different locations in the loop. The locations shown are highlighted here as A, B, C, D. The point A refers to the upper part of the right limb, point B is the lower part of right limb, and point C is lower part of left limb, and point D is upper part of left limb. So figure 10 shows the experimentally observed temperature transients at these 4 points, that is A, B, C, D, with respect to the time. And figure 11 shows the same points variation using the present model. So as we can compare figure 10 and figure 11, that there are slight differences with respect to the magnitude of the temperatures. However, the result shows that the present model is able to capture the trends quite well and is also able to simulate the flow inversion phenomena quite well. And when we comes to the application of the model, after comparing with 3 different experimental loops, so in this case we applied the model to study the influence of heater power and NCL wall thickness and heat sink capacity and VHVC loop, that is vertical heater and vertical cooler loop. So the vertical heater and the vertical cooler loop shown in figure 12. So for this loop, the influence of heater power, wall thickness and heat sink capacity and VHVC loop are simulated, and the simulated results are shown in figure 13, 14 and 15 respectively. So the conclusions drawn from this parametric study are listed here, that is the loop velocity and flow rate oscillations are proportional to the heater input. That is, as the heater power is increasing, the velocity of the loop is increasing and the flow oscillation is also observed to be increasing. And the second thing is that the stability of the loop and the flow velocity are proportional to the thickness. That is, as the thickness of the NCL increases, it has a stability effect in the flow. Also, the flow velocity also noted to be increasing. And the third one is heat sink capacity. It is noted that the influence of the tank capacity is not seen in the early phase of the transient, while in the later phase of the fluid velocity is proportional to the sink tank capacity. So with these studies, some conclusions were drawn, and those are listed here. The first thing is that a generalized numerical model for NCLs based on finite volume method is developed in the paper. And this model considers the aspects like wall conduction, fluid axial conduction, etc. that are generally neglected in NCL modeling that was noted during the literature review. Also, one of the key features is that this model uses equation of state rather than the conventional Bachowski's approximation for density variation and other properties of the water. And it can be applied to NCLs having different heater and cooler configurations. So this model shows that a capability of predicting thermal hydraulic transients in different configurations, that is VHVC, HHVC, and HHC configurations through validation studies. An application of the validated model to obtain VHVC transients is discussed in this paper. So parametric study shows that the velocity in the loop is proportional to the all three, that is heater power, heat sink capacity, and wall thickness. And among these, the heater power is the dominant parameter that affects the mass flow rate. A stabilizing effect on the flow is observed when the heat transfer to the wall thickness is moderate. And the influence of heat sink capacity is observed to be low during the initial phase of the transient and becomes important in the later phase of the accident, in the later phase of the transient. So thank you for your kind attention. Thank you so much.
Okay. Adi Narayan, thank you very much for the nice presentation.
Thank you, sir.
Now we can take one or two questions from the audience. Audience, you can ask questions. Okay, I think I will ask one or two questions from you, Adi Narayan.
Yes, sir.
So why you have considered single phase, not a multi-phase?
Actually, sir, our idea is to have two phase in future. Currently, the validity of the single phase model we are testing currently. So this is also having one application with respect to the moderator cooling system in HWR BRC. So this is also having one application, only single phase. That's why we have taken up single phase first. So slowly we are looking for two phase also in NCLs.
So you in your presentation you have mentioned Naveen Kumar et al, Divya et al.
Yes.
So because the audience will not be knowing about them. So what is the contribution by Naveen and Divya?
Yes, actually, sir, Naveen Kumar sir is from BRC Mumbai.
So he is a collaborator or what?
No, sir, no. I have taken his name from the literature only. So he has done the experiments on NCL during 2014-13 that time. So for validating my model with experimental results, I have taken his papers from literature only, sir. I am not collaborating with sir.
Okay, so any work on two phase is available in the literature?
Yes, sir. See, two-phase natural circulation loops models are available. So we are planning to do it in the coming days, sir. Actually, two-phase it is there in our program.
Okay, what is your contribution in this paper?
My contribution is to have a generalized numerical model for natural circulation loop of single phase, which can be applicable for different heater and cold configuration. So this was developed by me only. So this can be used for any configuration of heater and cooler.
Okay. Thank you, Adi Narayan.
Thank you, sir. Thank you.
And now I thank you all the audience present. And my special thanks to Amresh Dalal. So thank you, Amresh, for giving me such a nice opportunity. And
Thank you,
now,
Professor.
thank you all.
Okay, thank you. Now we can end the session here.
Okay, I am ending here.
Okay, sir.